four main programs that are ongoing, and they're somewhere in the center. Our flagship program is the one at the top. It's the Student Program for Innovation in Science and Engineering. We bring kids from across the English-speaking Caribbean to Barbados every summer, and they're 16 to 18 years of old, and it's a boot camp. With the students take about 6 subjects. We have 2 levels of calculus, 2 levels of physics. We have biochemistry, we have computer programming, we have entrepreneurship, and sometimes we have robotics as well. And these are the brightest kids in the Caribbean. They're already into science and engineering. We don't have to convince them that that's what they want to do. They want to go now to their dream universities wherever around the world, and we help them to achieve that. And the program has been relatively successful to date. About 245 students have gone through the program, and about 30 of those students have attended MIT, which is my home university. There's several at Harvard up the street from us. I'm in the Boston area right now. And there are 4 main programs Stanford and UPenn and Columbia, and there's somewhere in the center, and so on. And there's several. The flagship program is the one at the top. It's the student program. The other program we have is the Barbados Junior Robotics Camp. We bring kids from across the 5 weeks. We have about 75 students every year in 4 different levels of robotics. Years of old, and we have computer coding workshops that run on Saturday mornings, although we think 2 levels of calculus, 2 levels of physics, and those are for anyone between 15 years old and 115 years old. And there we're trying to help with the workforce robotics of the future, getting them. And these are the brightest kids in the Caribbean. They're already into science and engineering. Breaking their fears of computers. We don't have to convince them that that's what they want to do. And finally, the Caribbean STEM Olympiads, which are running, which will start running again in January of this year. It's a competition that gives out medals, platinum, gold, silver, and bronze. About 245 students have gone through the program. We've been running that for 3 years. And so 30 you can check these all out on our website, Caribbean. Those are our 4 programs. There's several at Harvard up the street from us. Science Foundation, Boston area right now, and there are 4 main Stanford and ongoing in Columbia, somewhere in the and so on. And there's several flagship programs. Since 2012, the Caribbean Science Foundation. The other program we have is the Barbados Junior Robotics Camp. We bring economic development of the Caribbean. And Dr. Saad, Dinah Saad, myself, we wrote a paper. We have computer coding workshops that run on Saturday mornings, although we think 2 levels of for the government of Barbados, talking about, and those are for anyone between 15 years old and 115 years old. In Barbados, and we're trying to help. That was an EU funded study. And these are the following that, we provided to some of the papers in the affairs of education and development in the Caribbean. And finally, the Caribbean STEM Olympiads. And in that paper, we talked about, in both documents, we talked about the development of this shared research facility. And that's what I'll describe today. And we've been running that for 3 years. And so 30, you can check these all out on our website, Caribbean. Those are the paper also talks about having the Caribbean islands that can afford it and set up a small business innovation system similar to the SBIR system in the United States. Since 2012, the United States government, the Caribbean Science, another program we have is worrying about research and economic and Dr. Saad, and if you have a prototype or successful implementation of phase 1, Caribbean doesn't have that kind of money, but something like that is needed to help young entrepreneurs who are at this time to get them. And the center, the shared research complementary to that, in that they will have a place. If you want to make a special chip, now there and Caribbean make that chip. And in that paper, we talk assay down and both January get done. Next slide, and that's what I'll describe. So this center would offer, as I just said, for basic research, engineering, physics, biology, computing. The paper also talks about having the Caribbean entrepreneurs who afford universities in the region. Universities in the region could use a lot more equipment. Their budgets are strained also. The SBIR and the support of the center United States Caribbean Center. Other program we have is the center, as it's set up, could serve not only countries in the Caribbean, but on a regular basis. Europe and Central America, prototype, successful knowledge, operate on a fee-for-service, Caribbean governments and nations. And the question, the reason, one of the reasons I guess I accepted to do this talk is because I'm wondering if the efforts that are centered around this conference, they want to make a special ship with Caribbean whether or not your effort here can be a catalyst in trying to get governments to move that's a political level. So this center would of what can be done and what's possible in the region to help our entrepreneurs and the question I've heard some of this discussed if you can get earthing off these regions with some sort of relationship to so that's basically the premise of the talk. So let's go on the center. So in the study I did for the government, there's this picture of this building that I ran across the shared national research laboratory. But the dream was to have some facility like this where people will come from not just from Barbados, but from other Caribbean countries, and we'd have to, I guess, some of course, do the stuff. They could come into this building and work by professionals. Hopefully, also those professionals are Caribbean students. Some of them have gone abroad and come back. A lot of them don't come back because they don't have nothing to do. Our efforts can be a catalyst trying to get this hard to put to use in your region, but they could come back and work in a lab like this, or maybe continue on what kind of research that's possible in the region. But the sort of things that might go in here are done on the ground. You see, like microscopes and if you get earthing, we should listen to the region and find out what people already need. Even at the University of West Indies, Barbados, I cannot find machine shops. And so metalworking and woodworking shops. So in the study I did, of course, we need electrical. Ideally, this building should be close to a university. The next was to have some facility like this. So how could this happen? It really, this is a project that probably needs about $100 million US just to get it started. And that's a lot of money for the region. Hopefully, also, but governments of the region must have the will to want something like this. And I hear that there's some movement, there's some of the governments and the universities in the region involved in this project here, and that's good. So I'm beginning to see that there's some motion, so I'm getting excited again. We proposed this back in 2016, things that might go almost 2025, but nothing has happened here, and it's probably not going to happen unless someone who's going to lead it or teams lead it. So, there are some recommendations for whatever they were. We would hope that in each country, the government should establish someone with authority and budget to contribute to the implementation. And ideally, government's going to want to create a semi-quasi-independent agency or ministry. Now, most Caribbean countries do not have a Ministry of Science and Technology. They have ministries of education, and sometimes they tap on science and technology. But it'd be nice if there was an agency in each government, if we can get it, that worries about these kinds of things, in addition to, of course, science and technology in their country. And they would have to do a lot of other things. We want to implement our science popularization programs, anti-excited STEM reform, the syllabuses. We proposed this back in 2016 primary schools up PBL and IBSC. There are some recommendations for whatever they were. So the private sector is going to be important in this center because they're the ones who are going to perhaps use it probably more than the universities. And if the governments began to engage with the private sector, including governments would want to create, and also, of course, having the private sector engaged with education universities and educational institutions that we have, and get also involved in the science popularization. We could change the culture in the region. That's what this is all about. And of course, the government at some point should put up some money. All the governments should get together and do this. This is very difficult to do in the Caribbean, to get the governments to come together and put money into common cause. But I would like to see some percentage set aside from their budgets for science and engineering over the next 5 years. And, there was a Johannesburg Declaration on goal which suggested 1% of GDP. Most governments are money is close to that. But it's very difficult to start businesses in the Caribbean, and it's very difficult to start almost everything in the Caribbean. But a more friendly government to forming companies and access to capital and helping to launch more STEM-based businesses is where we need to be. And I think I've already basically said it. Next slide. So I'm in the diaspora, and I'm trying to help from far away. That's kind of of course, the government 35% of the time is in the Caribbean. The government should get 65 here, and this is a very distant area. But the diaspora, the Caribbean diaspora is rich overseas. It's got lots of well-educated people and some wealthy people, mostly in the US and the UK and Canada. And a lot of them want to help. And I think the government needs to do more to encourage people to give back and I think this center could be indeed started with people from the diaspora who might be able to return and to come back and bring up. And of course we want internationals from all over the world to come in to these centers to help us as well. And I think that will happen once we got the budget but I think to get this started, some sort of international committee or government council, whatever you want to call it, that could work with the leaders in the governments in the region to plan something like this. Perhaps maybe akin to what I'm in the diaspora is going right now. So I'm trying to help them far away. Would be useful. Of course, we need funding, we need housing, we need a place to house the facility, we need to purchase equipment, maintenance and infrastructure. That's really very important, otherwise it goes out of business. We have to pay salaries, we have to help the users who might come from different countries to use this, we might have to assist them, even though their budgets are equally stressed. So this all needs to come together. And of course, all of us say the same thing. International agencies. I don't know all those agencies. I don't know which ones are simply back towards the Caribbean, but something has to be done to get this help around. And I thought this was a good opportunity for the country. Next slide. But I think so there are a lot of questions as to how this would work and who would use it. Would anyone actually use it if we build it? I don't like build it and they will come. I think we need to do some sort of study to see this thing. The staffing, I talked a little bit about that. Most of our young people who get educated in that, so they need this will help to start to reverse that. And I think once we get this thing started, I think I have another slide in a minute. I can see one way that you might reverse this brain drain. We want to attract international experts. Not enough fees are going to come from users to keep it running. And of course, all of us say the same thing. For funding this thing long term. Next slide. I don't know. One of my slides was missing. But it was a slide that talked about recruiting for people, for young students and middle-aged students and older. But I think there are a lot of questions who are working abroad, recruiting them back to the Caribbean to work in companies that the Caribbean invites. The Caribbean invites a lot of financial services companies to come in. I think we need to start inviting more technology companies to come into the region so that some of our people who are abroad can come back to the region and work in those companies. And the model basically says that people who come back from overseas that are well trained in sciences get this experience could either work in those companies, but we could also do more to help them start their own companies. But even if they come back and they work in an existing technology company, chances are what happened in Silicon Valley will happen, and that they get bored after a while because the management of the companies can't do everything. They have great ideas, and the goal might be that some of them leave and spin off and start. Very high risk, of course. The governments have to have some of the programs I talked about earlier in place, maybe something like those to help them, something like the SBIR program. And, after 10 years, maybe some of their employees leave them and start companies. And so we need to get this engine running, and it's not running right now. Most of the companies that I see starting up in the Caribbean, some of them are software companies, which is good, and I think that's a low barrier because it doesn't require a lot of capital up front. But I think high-tech companies that require the facilities that we have to get them started. But we need to attract more and more of those companies. But even if they come back, I don't know how far off base I am, but I realize that we need to do more. And I think software companies are going to start and are starting. High-tech companies need help. I think the shared facility is one way to make it happen. So I'll stop at this point.
Thank you very much, Cardinal. Really, thank you very much. While we have our, I think Leo
after 10 years, maybe
question
their employees leave them.
and then please, if you can start putting your presentation in the
It's not running right now.
Luca.
Yes, good afternoon. I'd like to make a comment or a question to Cardinal. Thank you for your interesting talk. Well, my comment is that if you go back to your slide number 9, showing that busy, I can tell you that the compact light tool is perfectly compatible with that structure because it could be hosted in the basement of the building. And we have a very relevant example. If you go to UCLA Physics Department, UCLA, University of California, Los Angeles, in the late 90s, Professor Claudio Pellegrini, the father of the FAM, Professor James Rosenzweig, they developed their own compact advanced accelerator system, driving also a compact light source in the sub-basement of the physics department. So that would enrich, in my opinion, yes, good afternoon, what you have shown. I'd like to very relevant, with a modest 10% more budget of what you have shown. Instead of $100 million, 110.
Okay.
Say a perturbative correction.
Very good. I thank you for that.
So Leo, do you have any comments?
Cardinal, I have some comments about what you just said, because I'm thinking about the role of ICTP in this region and the European Union. The first time I met you was when there was the final meeting of the project of the European Union in Barbados, you remember? It was 11 years ago, and nothing happened after that. What I think is that one, perhaps also starting from this conference and from this project, one could proceed along two lines, which are not in contrast with your idea of a center in the region. First of all, ICTP is a regional center in Mexico, which is not doing very well, incidentally, and Chiapas. One could think that the role of ICTP in the Caribbean, which in the English Caribbean, which is almost inexistent, may be taken by a center like that, which could be part possibly of as a branch of the Mexican one. I don't know. A way also of revitalizing the Mexican ICTP center. This is first possibility. Second, yesterday we discussed the idea of having a kind of summer school about light sources where we were thinking about having it in Calabria, but one could say that, for example, your center could be a kind of ICTP center with also the scope of having specific short courses, short workshops on specific subjects. The cost of this initiative would not be out of the possibility of your government. Which is not going very well instead.
Leo, those are all great ideas. So let's continue to our next, since we're a little bit late in our schedule, so let's give roundabouts. Keep the conversation going in the chat. Cardinal will be happy to answer your questions in the chat, so please continue to do so. I'm going to be presenting our next speaker. That should be Dr. Luis Beff. Is a staff scientist at the Cornell High Energy Synchrotron Source. She completed her master's degrees in chemistry at the Université Libre de Bruxelles and received her PhD in chemical engineering from the University of California, England. On a personal note, she also has been very active training undergraduates and graduate students in synchrotron techniques, for example, students in Puerto Rico via different projects. So today she'll be talking about the new high magnetic field X-ray beamline at CHESS, Science and Workforce Development. Please, the floor is yours.
Hi, good morning. Thank you for the introduction. Thank you for inviting me to speak today. So I'm going to get started. So as I said, I'm a scientist at Cornell Synchrotron. I am currently working on a postdoc.
I'm going to be presenting our next speaker. That should be Dr. Luis Beff, a staff scientist at the Cornell High Energy Synchrotron Source. She completed
so this is basically the beamline we're building is called the high magnetic field beamline, and the idea behind it is that with a high magnetic field you can kind of spin charge or of electrons from X-ray technique. You can probe substrates like these of freedom. And so these techniques exist in kind of separate universes. So there's synchrotron facilities and high magnetic field facilities, but it is very rare for both of them to exist in the same place. And so the idea here is to find it exists in the same place. So you have either or magnets and introduction, like iron you want to have both and dedicate this. So if you get started in these types of studies with high magnetic fields and X-rays, and so we're combining expertise from X-ray scientists and also high magnetic field scientists. And so this is my beamline assay. So we have, because we want to make it the most efficient that we're finding, what we're going to have is so this is the magnet. So this is I invited these for the high magnetic field beamline. Okay, so we're going to have is the Tesla magnet, and we made it with as much size as possible. We're going to have a white optical axis. So we have a virtual source of electromagnet that we have. So the core of this X-rays are going to come in, hit a cell here in the center, and as X-rays are coming out. And part of the design of using magnets is that there's a wide opening here, but it is very rare it's coming out to exist at the same time. And so we are enabling a bunch of different techniques that include scattering, resonance scattering, spectroscopy, magnetic dipoles, and high-resolution magnetic introduction. And this is because we want to be able to do experiments that are going to serve a variety of scientific techniques. We're expecting that the people that are going to be interested in this are going to be, physicists, people that are interested in structures and high beams, but also people that are playing Fermi surfaces. But we also know that this can be interesting for people, for example, in biology, what we're going to want to try is induce new conformation with a high magnetic field and look at them with X-rays, or chemists and chemical engineers and other engineers that want to control processes by using these high magnetic fields. So this is a project that you can see on the timeline. So it is a mid-stage it's funded by the NIC, something that's a part of the CIA. We had this idea back in 2019. It was approved in 2020, and it was awarded in 2020, October 2020, and started in 2021. So not that long ago. And so we have been mostly in a construction project, and then we are going to start commissioning this facility next month in January 2025. And the goal is for this to be operational in 2026. So very fresh, we're in the midst of it. We're going to be, so the project behind this is here. So it's a combination, as I mentioned, from experts in X-rays, based in the Sincrotrones, experts in magnets from the Mag Lab down in Florida. But then we have also been in this educational component in here by partnering with the University of Puerto Rico. And you can see at least one person who shows up very familiar to you. Yeah. And so built into the proposal from the beginning. So this is a scientific goal thing we wanted to achieve, and that we promised and said that we would do. And those are, science requirements are having this functional unite X-rays, magnet, and being able to do experiments in there, and also these key experiments and techniques that we have. And each one of them, we just have to be able to show that we're able to do these experiments. So this is the things that we have to do here to show that this project was a success. But in addition to these scientific goals, we also included in the project that we are going to have, we're going to have 4 graduates from Puerto Rico, from the University of Puerto Rico, we're going to join us and work with us alongside this project and help us build this new beamline, and with the promise that we were going to help them develop magnets, make them have X-ray side, but then we have also the X-ray beamline technology experts in the world. So this was a big thing to do, and it didn't just come from nowhere. So we have been working in partnership with the University of Puerto Rico and other universities out there for quite some time. So we were part of and still are part of the PREM partnership. So this is a partnership working with universities in Puerto Rico where they do their science. For example, they do electrocatalysis, and typically the experiments and the science that they do is underrepresented in synchrotron, especially scientists from Puerto Rico are underrepresented in synchrotron. And it's very hard to get into if you don't already have a foot in the door. So by partnering between these universities and our team that is based at a synchrotron, we can work together to kind of help them get in and lower the barrier there. So we work with them by working on experiments together, designing experiments together, running experiments with them, and then making sure the data gets analyzed and published. And so this project started about in 2019 when we had 3 firm students that came to CHES, spent a few months with us to try and learn. We were in another construction project at the time, rebuilding a lot of the experimental facilities, so really getting a chance for them to get their hands on stuff and see what makes the synchrotron. And one of the students here, Brenda, came there, really liked that, has stuck it on with us, and is now working with University of Puerto Rico. And then I right here. So I was also stuck in this program, and typically working with experiments groups in Puerto Rico and running experiments with them, and then I decided to join the science project to kind of continue that work on the science side, but also in the workplace development side. All right, so we went from this partnership where we were kind of just working with teams from Puerto Rico and helping them run experiments, but then we worked with them with this new cohort of students that were going to become experts. So not experts just in doing single experiments and analyzing data, but also having understanding constructing a beamline and operating a beamline and that whole career track. So we sat down, we had a lot of discussions about how it was going to work, and we kind of approached this thing in these topics that you can see here. So there's a lot of planning, how do we select these students, how do we recruit them, and what are the goals we want to get out of this program. Then there's a lot of training, selecting student mentors, how we're going to get them trained on the basics of synchrotrons, how we're going to get them trained on the science that we're doing here, etc. And then actually going into doing, which is having them run their own experiments at CHES and then other synchrotrons, because it was very important to go an opportunity to go to other places. All right. Not everyone we went from our partnership, and they were also part of running pilot experiments and showing that there is some interesting science that can be done in the facility that we're building, and kind of just building up this user community for when our facility is operational. So this slide here shows you kind of the mentorship structure we have for this. So again, it's a partnership between the University of Puerto Rico and Cornell, and so each student is paired with one mentor from Puerto Rico and one mentor from Cornell for the synchrotron. And so we have a variety here. We have, you can see here, Jorge Colon and Quincy for chemistry and Professor Halai for physics. And then on our side, Chris, Jacob, and I are scientists of the synchrotron, and then Brad Ramshaw, student member professor of physics. And this pairing, this mentorship was based on, the interest of the students, what kind of, and then track their graduate, and just, interest of what we're working on. And so this is, you can see here the students that were selected. So we have 4 students here, and you can see the pairings up here. So one thing I would point out here is that originally the idea behind the proposal was to have more PhD students. It's just not the students that came on. So we have 2 students here on the left who are master's students in physics, and then the 2 students here on the right are PhD students in chemistry. And so that's not what we had envisioned from the beginning, but that is not a problem. Students that have been great because they have come in with their own ideas and their own science, and that has actually shaped the project in a way that we weren't expecting, but has been beneficial for everyone. And since this was made, Sebastian has graduated with his master's and has gotten into a PhD program at UIUC. So sad to have lost him, but very happy for him that he has gotten into a different PhD program. So these students, wide variety of backgrounds, how did we get everyone on board? So we started with a bi-weekly book club. So we used this book that I'm showing here on the left, an introduction to synchrotron radiation, which is a book that Eva and I and other scientists in the lab often one thing I would want to refresh ourselves is thinking about different techniques that are not necessarily the ones that we use day to day. And so this book covers everything from the basics of how X-rays interact with matter to then going into different techniques and more advanced stuff. And so we all just went through this book together, and so that's to make sure that all of the students, even with the different backgrounds and different levels of experience, are kind of getting everyone on the same level. In a way, we every other week with me and another scientist and the students took turns presenting different topics. So either a whole chapter or a section, and so they took turns presenting, and then they took turns like asking each other questions and kind of making sure that they understood everything, and then if they ever got stuck on anything, Chris and I were there to either answer the questions or point them to a direction for more answers if we couldn't answer. I think that's something that happened. In parallel to this, we also encouraged the students to participate in the meetings, the science meetings we had for the design. And so these are big meetings that typically have scientists, technical staff, engineering staff. So a lot of people with different backgrounds working on this. And we wanted the students to play an active role in this, and so like communicating with our staff and getting this experience, communicating with people from different backgrounds. And so they took turns presenting things that the techniques that they're learning. You can see here a presentation on spectroscopy technique, but also presenting the projects that they were working on. So one day we get experience presenting their science to a wide audience, and in English, which is none of them that was not their native languages, but also it was very helpful for our staff, especially the technical staff that is helping us build this facility, but without really knowing what we're going to be using it for. This was very useful for everyone. The students have also participated in a series of workshops, and that is efforts that are ongoing in our lab. So this PRIM partnership that I told you about, we go about once a year, we go down to Puerto Rico and teach a workshop on spectroscopy techniques. This is illustrated here, and you can see our HMS students have been invited to participate in that. It's very spectroscopy focused, but then we also host a high energy X-ray technique workshop every year, which is the other one. So we students are selected to come to us and attend this workshop that that is more broad, covers a variety of different synchrotron techniques, but also other things like how to write a proposal, what you have to do, an experiment, etc. And so our students have been participating in all of these workshops. And I find it especially useful even for them to participate in workshops with techniques that are not necessarily the ones that they're going to be using for their projects. It's just good to get more understanding of a variety of techniques that are being used in synchrotrons. So here are the projects. You don't have to read all the details, but these were the projects that were written into the proposal originally. So we had this idea that each student was going to take ownership of a piece of equipment, basically, and work with engineering staff and get that piece of equipment designed, specced, and then installed in the experiment. So this was before we knew who the students were going to be and exactly what track they were going to be on. And what we learned once we got our students is that this was not what worked for them. The students came in with their own ideas, their own backgrounds, their own interests, and so just trying to put them on these projects was not did not work out the way we did. So instead of working on these pieces of equipment, what we did was kind of let the students follow their interests and come up with their own ideas, and push, instead of pushing a piece of equipment forward, they're kind of pushing the science of this facility forward. And this has been very successful. So for example, here you can see that Sani, who's working with Gran Caribe in physics, has had a bunch of different. So here are the projects looking at quantum oscillations. So that is just if you vary a magnetic field on a certain material, then certain properties can oscillate, such as the magnetoscription, work with example here on the vector disk. And this is something that is well known, and so we're trying to figure out if changing this magnetic field would also be something that we could see in the lattice parameters of the bismuth, which is something that we can measure with X-rays. So we sent them over to Germany, pegged the synchrotron to try and see if we could track that. And basically, that was not successful because he was just drifting too much. And so he got some experience with the synchrotron, but also showed the money that we have for the facility that we're building to be able to have these ultra-precise lattice measurements of our materials. So got some experience and also proved the science case of our facility. And him and Paulette were physics students, so they've been working with the quantum materials beamline, so they also know a lot of scattering and diffraction techniques. Sebastiani was also looking at magnetic transitions in a material and looking if there's any correlation with quantum materials. And on the other hand, Paulette here on the right was interested in the resonance X-ray scattering technique that is typically done with a small detector to kind of chasing these peaks around, but she was trying to combine two techniques. So combining a technique that uses a big detector would also be something that we pay for this Rex mapping. So you don't need to know all the details, but basically she is doing some method development to try and make these measurements faster, and that is going to be very useful in the future. We're hoping to implement the method development that she did at the facility that we're visiting. And on the other hand, the chemistry students are coming in with their own creative projects. You can see here Brenda on the left is thinking of using is interested in oxygen reduction reactions, and so she's kind of thinking about how she can get new catalysts based on her oxide and have that the properties of that in the classes between scattering and diffractions. And Tanya on the right is interested in spin crossover complexes and magnetic transitions. Spin transitions can happen in magnetic field, temperature, and pressure. And so she's exploring how intercalating these spin crossover complexes in a framework such as zirconium phosphate that affects the properties at all. So these, for example, here, I want to point out again that these were two projects that is not at all envisioned for our development science case, but we see these students come in with their own science that them do what they're interested in. We're doing this new science that is actually really cool. And in addition to that, they also have come on, so Brenda and Tanya here, you can see them at NSNS2 with me, where we want to do an experiment there because we were invited to do some scientific commissioning on a face-made system, which is something I had never used, but we're going to have in the facility, so we all got to work with a scientist there that had how to learn how to use this. We've also gone to the mag lab because Tanya joined me there because we're going to be using these X-ray detectors in the facility, and we just wanted to make sure that they were going to work in the magnetic fields that they were going to be seeing, so we did some tests in the mag lab. So again, we're getting some experience working with people from a different background. And then in addition to this, we also have a 10 Tesla magnet that is moving in our spectroscopy beam here, where you can see here Brenda, I got a chance to do some experiments with this magnet here. Yeah, so this is all the training we've been doing up until now, and now, we're entering this commissioning phase of the beamline. So you can see I'm just laying out all the goals, because I need to have this beamline fully commissioned and operational by the end of 2025. So I'm kind of splitting up what I need to do for each run that we have. And then I'm trying to think about where can I bring in the students, how are they going to learn anything interesting to them, and how can they help us do this. So this first run we're going to have now in the winter, we're going to just working on some equipment. That's the most exciting thing for a student, so I'm probably going to be doing this on my own. But then after that, when we're starting to use all the more scientific equipment, that is when it's going to be interesting for the students to come in. And if you look in more detail, so you can see it, especially once we start putting in faceplates and commissioning individual techniques against the first experiments, that is when it's very interesting for students to come in and be a part of this and see how you set up for an experiment, how you get everything working, and how you optimize. So I'm laying this out, setting out like goals with the magnet. And you can see I have to test this technique, and this is all the sort of analysis procedure now for these spectroscopy techniques that these students, Brenda and Tanya here, are interested in. So it's very helpful for us to have them come in, look at our procedures and be like, I don't understand what you're talking about, but also for them because they get a chance to run this experiment and then get some data and really the first users of this facility. And then later on here you have more details of them scattering techniques, which is something that, for example, Paulette has been doing so that she can be involved. It's something that she has done already, but she can help us develop these protocols for this new beamline that we're going to be doing this on my own. And then finally in the fall we're actually going to have basically for these first experiments here. So and if you look very helpful for us and the students to be there to really be a chance to be the first users on this facility, do their own experiments, and also help us prove to the world that we built a facility that can do something cool. Alright, so that was it for my talk. That was how we've been doing some this facility, and I'm happy to take any questions.
Perfect. Thank you very much, Luis. Thanks again, Luis, for this amazing talk. Any question from the audience? We can take one question. Lawrence.
So a quick question about your sample environment.
Yeah.
Do some of the samples need to be kept at cryogenic temperatures for the spin crossover experiments?
So are you asking about the specific samples or about the involved?
Well, whatever the sample environment. Yeah, so some samples, I would say, you would experience spin crossover so fast at room temperature that I don't know if the photon would be fast enough.
Yeah, so she is specifically looking at, she selected the compound she's looking at based on what temperature they do the transition. So that's something that goes into that. But once we have the magnet, we can also, it's a cryo-cold magnet, so we can also control the temperature.
Thank you very much, Luis. Thanks again, Luis, for this amazing talk.
To the sample or the magnet?
Any question from the audience?
I guess the 200, the sample's going to be totally cooled? The magnet's going to be cooled?
We can use the cooling. There's a VTI.
So a quick question about your sample environment.
All the way down.
Do some of the samples need to be kept at cryogenic temperatures? Gotcha. Okay. The spin crossover experiment? Thank you.
Thank you very much, Lawrence and Luis. So let's thank again Luis for this fine presentation today. So is Dr. Paulici on.
Yes, I'm here.
so fast.
Perfect. Can you share your presentation?
I'll try.
Fast enough.
Yeah,
Have you sent your presentation to Lawrence?
No, I didn't.
so that's something
But I
that we can
can.
accept. But once we have the Mac, we can also.
Can you see it?
It's a
Yes, we can. So
Oh, great.
let me
It worked out the first attempt. I'm surprised.
To the sample.
First
So
time.
let me present you very fast.
The magnitude.
Let me present to you, to the audience, Giorgio Paolucci graduated in physics from the University of Rome, La Sapienza, in 1981. After a short period at the University of Calabria, he spent 2 years in Fritz Haber Institute, the Max Planck, in Berlin, working with the group of Professor Alexander Brockschopf, very known scientist. He then moved to Houston in the group of Professor Renzo Grossay in the period of, and has been involved in some startups of the vast National Laboratory for Surface Science. In 1987, he joined the project of the National Synchrotron Radiation Plant Electra, where he developed and managed the laboratory first beamline, Super ESCA, into the year 2000.
Can you see it?
From 1998 to 2000, he also coordinated the Surface Science Division of Electra, which are 3 beamlines and 2 support laboratories. And from 2009 to 2006, he was the director of experimental division of the laboratory. More recently, from January 2014 to 2019, he was the scientific director of Sesame, the Middle East Synchrotron, and since 2020, he has been the chief scientific officer of the Electra Laboratory in Texas. His main scientific activity has been in the field of photoelectron spectroscopy of surface species, as well in the development of innovative X-ray instrumentation. Today, he is going to be talking about advancing collaboration in science, the Electra 2.0 upgrade, and opportunities for international partnership. Dr. Paolucci, the floor is yours.
Okay, thank you for the nice introduction. Good afternoon, good morning to everybody. I'm going to introduce the Electra Laboratory and its future upgrade, as well as opportunities for other laboratories. And okay, let's start with that because we don't have too much time. Okay, so Electra is located in Trieste. We have 2 alternative sources. We have a relatively old storage ring and a more recently built electron laser. We have at the moment about 400 employees with over 34 lines, 4 laboratories. We operate roughly 5,000 hours a year, and we have 1,500 per year coming from all over the world. I would first talk about Electra and then say a few words about them okay, at the moment at Electra we have Electra laboratories upgrade as well as more opportunities for other laboratories, and then we have a number of startups that support each time. The business model we have, which is, Italy is not as generous as other countries. So, in order to have more beamlines, we established a number of collaborations with national and international research institutions. So you see the logos around this picture. You see the logo which is the logo of the Italian National Research Councils, but you see there is an Austrian flag because one of the beamlines is run by the
Technical University of Graz, you see the IAA. First talk about that, and then we build the microfluorescence beamlines. We have two Indian flags because we have two beamlines which are run together with the Indian Institute of Science, and then we have collaborations with Romania, with Germany, with Slovenia, and so on and so forth. So in general terms, I can tell that we are one of the most international national laboratories. We are a national laboratory in the sense that all of our budget comes from the Italian Ministry of University Research. This is what we have now. We have 17 lines in the software range, mainly doing from electron spectroscopy, but not only. We have absorption, we have microscopy. At the moment, we only have 9 millimeters for high rays, some use a regular or supermagnetic ray, and one for the bending magnet, and we have two infrared microfluorescence. So this is basically in the same because we have two beamlines I gave you before in the tabular form. We have, as I said, very international also, as far as our user community is concerned. This is the distribution of the proposals which were received last year. And you see that, I hope you can see the country names. Anyway, less than 50% of the users actually come from Italy. The second, the national community comes in the letter is from India. That is because of this agreement we have from them. And then we have Germany, France, Austria. I cannot read all of them, but they are very, not very many family leaders, confess. But we are open to everybody. By the way, we have support mechanism for users, so do not be afraid of applying for the time at the letter, because we can partially support you. We can actually, we also have an agreement with the ICTP, which has been mentioned several times, which is, as we know, also located in Trieste. So we can support through them users coming from development countries. This is the Germany, France, the distribution of proposals which were actually carried out. I mean, you see the ratio between submitted and accepted proposals is complex. Some demands is unfortunately very high, so the chance of getting the time is really complicated. For example, the express line, which is a high pressure diffraction line, so we can apply quite a high oversubscription ratio. That allows us to produce the ICP published 700 papers in 500 papers last year, and so we are around 500 papers per year overall, with some very good impact publications. And you can see that this is the names in Germany, near to you, but the most productive lines, which are MCX, SAFs, and the two diffraction lines are obviously in the hardest region, which is well-known, well-known aspect of synchronization. And for this reason, in the future, we intend to extend the capabilities of the new electrochemistry towards the shorter wavelength range by keeping at the same time flexibility the softer part of the spectrum. So this is what we're going to do. We're going to install a new 6 by microwatt lattice in the existing tunnel, and the last part of this sentence is the challenging part. This is actually what has happened, or is happening also at other sources. For example, the Swiss Life Solar is upgrading to a similar lattice simultaneously. This they started 2 months ago, and they have exactly the same challenge, and that is because normally when you get the money from the upgrade, you get the zero money for changing the building. So we have to fit a much more complex structure in the same tunnel where we used to have or we have at the moment a double bed structure, which increases tremendously the number of magnets. So this is what we're going to do, but it is worth doing it because at the end we will have existing tunnel, 3 orders of magnitude increase in brightness, and actually what is happening more, even 50 times increase in coherence. Here you see some numbers about the 2 machines, and of course the difference is exactly the same. So for this reason the energy is the same. However, as you can see, one emitters is strongly reduced, that is because we increase the number of magnets, and therefore we are disturbing the much more complex. I'm sorry, I'm not an accelerator physicist, so maybe someone will jump on the chair when I say these simple things, but that is my level of understanding of machine physics. So about that. Anyway, so this is what it is advantages, and this is how more crowded we're going to have electricity. However, as I said, we're going to increase enormously the brilliance, especially in the high energy regime. We're going to increase the coherence, especially at 1 kV and above, and we can make use of sources which at the moment are practically impossible for us, like vacuum regulators, and however to have also superconducting diodes because we increase the number of strength with a field of 6 Tesla. So this is what sections are of jump on the check. This is half achromat. You see how many magnets you have to put. We have meetings, regular meetings. What project at one time. It was somehow funny to hear the discussion between the machine physicist and the engineers, because at one point the machine physicist came up with a wonderful design. Said, "This is the ideal design for our machine," and the engineer said, "Yes, maybe it's ideal. However, we do not know how to cycle balls." These kind of things have to be discussed as well. So these are the first magnets. These are prototypes of the series. You can see power that have flexible magnets with multiples. They're all independently powered, and so this is being delivered as we speak. We will increase the mine offer, as I said, especially in the hard trade, optic meetings, regular meetings, the new mines to exploit the clearance, one the diffraction imaging, we will have superbed sources, one for the fraction extreme conditions, and we will strengthen the capacity of software and X-ray range. Just one example of what we do, the boundary conditions and the strategy which we're using. This is an overall view of what it look like. So this as I said, we have 3 vacuum ventilators in mines, and we keep some of the bin lines. Other bin lines are going to be upgraded. Some of them are going to be moved from one location to another inside the same building. So it's going to be a very interesting period, which will increase, I anticipate something which I'm going to say later, which is starting mid next year, beginning of July next year, and will end at the end of 2026. So we intend to have the first bin line operating after 1.5 years, starting with that year. And as an example, we are going to extend our capabilities in medical imaging, which we are already doing activities for mammography. We're going to extend it to lung tomography. This is a phantom which we're using. Actually, these are pig lungs which are installed or mounted in this simulator, which will simulate the breathing actually. So you can actually move the lungs and see minor, very small lesions coming from, for example, tumors or asbestos or diseases like COVID. And this is being built. I mean, both the hatch which you see here and the design has been ordered. We're discussing details with the 2 companies, and this will be ready as an example in 2026. We will also have this bin line have a collaboration with mammography, and we intend to study to apply phase contrast imaging to real patients. So we are designing also installed or mounted patients up and down. This is the very tight tummy frame minor small are aiming to. So as I said, we will start we will shut down Elettra in July. This is being clear, and the removal of the existing accelerator will end at the end of 2025. And then we will start the installation of these new components. This means this project will make components which are, I remind you, still producing excellent science, as I showed you before, can be available for phase contrast imaging. Now, we had discussions with a few people, and during a meeting about the African source with Sekazi, this is the, most of you know, Sekazi told me there is an interest in Uzbekistan. So we had the first Zoom meeting in June last year. You can see Sekasi, myself, Sayora, who could not attend because, as you can imagine, at the end of the year, closing balances and things like that. However, she was there, and then we started the education. Was also involved, and apart from in our project office, and Roberto Vicentini, which is bottom right corner, and is the guy who's taking care of removal and installation. After that, we had a meeting about and other people. That was in August, and in August was not operating, so I couldn't show. We could show them what components were potentially available for our projects. Then for a few months nothing happened. However, in September there was a meeting in Uzbekistan between the minister for science, education, higher education, science and innovation from Uzbekistan, and our minister for university and research. They discussed a few things. There is an Italian presence, an historical Italian presence in the education system in Uzbekistan. There are 2 or 3 universities who have some seats in Uzbekistan, starting with the Turin Polytechnic. This is historically one of them. And there are advantages, of course, for us as well. We can show them conceiving our potential. We could avoid storing them for a few months' time as required by Italy. However, in September, the possible transfer has been already discussed with Italian nuclear safety authorities, and they agree that it is a good idea to transfer the components. Of course, you have to organize a special transportation, but we're working on this as well. Then, after the visit of Uzbekistan, we received this letter from the Minister of Science, Education and Innovation from Uzbekistan, saying that they are actually interested, and we would like to continue the discussion, talking about the details of how that can be done, the cost that can apply, and so on and so forth. And as announced in this letter, after 1 week or so, we received a visit of the Deputy Minister of Higher Education, Science and Innovation. This is taken visit while I'm explaining what magnets are. We went around the station, but sorry, 1 minute. Okay. So we are then after the visit of logistics, as I said, and another technical. As I said, we also have a free electron laser. These are pictures, and I will go very quick about the free electron laser. It's a very powerful machine, and it is one the only one at the moment operating with the seeded system. So with the seeded scheme. So we're actually shooting a conventional laser into the electron beam, and the radiation we produce is harmonic of the seeding laser. So that means that we have extremely good stability in wavelength condition as opposed to what happens in other schemes. Again, it's a very international facility. Since we operate one experimental station at a time, the radioactivity is, of course, not comparable. However, most of the papers have a very, very high impact. So this is, for example, a cover which was published on Natural-Physics. And I guess we can stop here, and thank you for
Thank you very much, Dr. Paolucci. We have one question from Leo Violino.
Well, Giorgio, thank you very much for your talk, excellent talk. I think I would like to make a comment about the last part of it when you were speaking about Uzbekistan. First of all, Sayora will speak today. She will, you have opportunity of listening to her. But the comment is not this, which is usually found in the program, but just that there is a big opportunity related to the subject I touched yesterday, the idea of a kind of consortium of 5 projects for the Global South program. Because Uzbekistan will host next year in November the General Conference of UNESCO. And since UNESCO can play a major role for this initiative, since the Director of Science of UNESCO participated actively yesterday, 2 days ago, in our meeting, supporting the idea of Sincrotrones. And so, what I would suggest is that in your conversation with the ministry, you also push for something we are doing ourselves also, to suggest that Uzbekistan puts in the negotiation with UNESCO for the organization of this General Conference in November, also a discussion about a program of light sources in the south, which can lead to a favorable conclusion. Also, your problem for what to do with the commissioner things. And obviously, this is also interest for Italy. It is clear that the support of Italy, which is a very important stakeholder in UNESCO, I think that could create a synergy which may be favorable for all the blitz of this building.
Yeah. Good idea. We'll certainly do and discuss this aspect.
As Lawrence asked his question, Dr. Ricardo Valverde, can you start sharing your presentation? Lawrence, you have your question.
Hi, Giorgio. So, I know that at the anytime there's a dark period, there's people that need to find other places to work. And I was wondering if any of your people might be open to visiting professorships at universities in Africa, Caribbean, or wherever. I know that was done for the advanced full-time course, and some of them did.
Okay, they might be interested. However, as I said, we're going to do it time, so I suspect that everybody will be very, very busy, but we can discuss about it. I was thinking myself to go back at time to days, which is still, for example, I'm still good at. But I did it in session, so I can do it.
Right.
However, as I said, we're going to be lines from one location to another.
I know that
this is not easy. We already started. We we are going to install some components next week. We're going to install a new diffractometer, which was delayed, unfortunately, by 1.5 years. So the delivery was supposed to be in 1.5 years, and it was delayed by 1.5 years, so it took 3 years to be delivered. However, we're going to install it shut down, just to tell you an example. Then it will be used in the next run, and then we have to disassemble it again because that is not going to be its final location. But we kept the original plan of using it on the existing electrode because otherwise we would not be able to test it basically. Because the original plan was, of course, to use it for 2 years. Anyway, this is just an example of how these but there might be some specific people who can propose for external projects. It's supposed to be in 1.5 years.
Thank you, George and Lawrence. So, Dr. Riccardo Barberi is on.
If you hear me.
Can you share your presentation?
Yes, I can try to share the presentation.
So, Dr. Riccardo Cristoforo Barberi is an author of 188 scientific papers as well as 15 patents. He's the full professor of light physics and director of the physics department in the University of Calabria, Italy. He's co-founders in 2002 of NATURALES, the Italian Network of Research Valorization. From 2002 to 2013, he was the rector delegate of technology transfer and founder of the local TTO and the first business incubator in Calabria, scientific responsible for the upgrade of the STAR research infrastructure, Southern European Thomson ICS X-ray source for applied research. STAR is one of the 18 new strategic research instructors in Italy. Today, he will be talking about the STAR, a research infrastructure in southern Italy. Dr. Barberi, the floor is yours.
Are you able to see the screen of the presentation?
Yes, we can see it.
Okay, so I will speak about STAR. It's a research infrastructure in the southern Italy, particularly in Calabria. That's the location that you can see. We are exactly in the middle of the Mediterranean Sea, so that's a quite strategic position that can be useful in the future. And this is a very new project located in the University of Calabria. The University of Calabria is this long structure that you can see in this picture. This is a double bridge with a length which is more than 1.5 kilometers, so it's a very huge structure. And STAR is located here, very close to the main bridge. In practice, there is a technological pole where STAR is the center of this structure, and you can see in the bottom left a photo of our machine, which has two beam lines, one low energy, in Calabria, 17-18 kilo electron volt for X-rays, and an high energy, 65, between 65 and 350 kilo electron volt. Now, I will show you just a short movie to introduce STAR and to have an idea of what we did. This is a quite long project. The idea was it has been funded by European funding by means of the National Minister for University. And this part of the national program for new research infrastructure. This is a view of our university. In the bottom left, a photo of our machine, which has two beam lines. And this is a scheme that I will present later. The infrastructure itself. This is the main machine with the electronic beam, which interfere with a very strong laser beam to produce X-ray radiation. It has been funded by European funding. Okay, you see that this is a quite complex machine. It has been realized by collaboration with INFM, the Italian National Institute, for a view of our university. In the bottom left, a photo of our machine. These are machines of, and this is a scheme of our laboratories. And there are also the infrastructure itself. This is the service laboratories together with the main machine to produce X-rays, which are specialized on matter physics in some way, or in advanced advanced system for digital calculations. Okay, you see that I think that I can stop here this movie. Otherwise, it takes much time. And okay, so what is STAR? Is a compact X-ray source, which is quite innovative. It's based on the Thomson backscattering scheme. It has been built with the collaboration of the National Institute for Nuclear Physics, INFN, and also in collaboration for the experimental hatch with the Synchrotron. So here we have, this is a compact X-ray source, but with very high performances. So in practice we can produce radiation which is typical of larger machines like synchrotrons, but the cost and dimensions much lower, at least for one order of magnitude. And in our case, the X-rays are used in two experimental stations, which are specialized for some kind of two-dimensional tomography. Main application fields are advanced smart materials, high-res biomedical imaging, and this is the scheme that you have seen also in the short movie. So we have relativistic electron beams which collide with a very strong laser beam. Photons are backscattered, so this interaction between electrons and light produce the X-rays, which are, in some sense, the number that are produced by laser. So this is a beam which is very clean, monochromatic and at very high level. This is just a scheme to compare the energy region for the Thomson-Compton sources in comparison with the traditional sources. And you see that Thomson-Compton sources are competitive at high energy, and even if they are smaller machines, the photons are produced in regions where traditional sources lack production. The main characteristics of this X-ray beam is the high penetration depth, the possibility to treat massive samples because the beam has a conical shape. Then, in some sense, there are also the possibility to work in phase contrast, edge enhancement, and so high contrast to produce image. And we are working in collaboration with informatics and mathematicians to introduce very advanced techniques for image processing, for instance, using deep learning tools that we can manage locally because we have two centers for advanced supercalculators. So in practice, the idea was to build a technological pole centered on this machine. And this is a picture, satellite picture of the two main buildings of the structure. One is devoted to STAR and the other one to the associated laboratories, because the structure is this one. You have the main X-ray source with two beam lines, one at in some sense low energy, the other one very high energy. We have 6 laboratories, technical laboratories, which support the main machine. So laboratories for laser, electronic control, radio frequency, radio protection and safety, vacuum mechanics, data storage and collaboration. And then we have service laboratories, which are in level and able to provide services which can work on biological samples, material preparation, material characterization, physical prototyping, very advanced prototype, advanced spectroscopy, microscopy, modeling, simulation, and virtualization. The scenario in synthesis is this one. We built this vicious infrastructure in 12 years by using 2 national programs funded by the European Community, the European Commission, and the first one was had a value of 15 million euro, second one 17.5 million. We received support by the Minister and the Regional Council for Scientific and Technical Personnel for the research infrastructure, and it was unusual that the university was able to concentrate and to merge resources acquired during 12 years on one well-defined project. Usually, universities work in a different way. The mission of STAR is the cutting-edge research in the field of advanced material science and technology, and it is designed as an evolutionary resource practice. We can manage also to have an evolution of the present machine. Today, the machine is ready, but as the maximum energy is very high for X-rays, because it ranges from 17 kiloelectron volt to 350, the facility is a source of ionizing radiation, so we need an official authorization before operation, and we are waiting the completion of this procedure to declare the operation. In principle, we should receive receive this authorization before the end of this year, in the first weeks of next year. The star, even if it is in a university, is built as a user facility, so it's open to external scientists, companies that want to work. So we will provide more or less with the same model of the synchrotron in Trieste, the possibility to enter in STAR and to use the local frequency. What is relevant is the STAR is considered one of the Italian strategic infrastructures with international projection, and it is included in the two last national programs of research. So this is just to show you some preliminary work that we did. This is the heart of a goldfish. The main machine is not working, but we have smaller machines that we are using to learn the treatment of a large machine like STAR. You can see here the inside structure of the Earth, this white part with this fractal structure are the cavities inside this strange Earth of the goldfish. And we worked also on some samples for electronic engineering, for heritage. These are two samples with international materials that has been collected very close to our university, and it's a tomography of an electronic device, a MOSFET, after a big event, just to see how is deformed, what happens when there are this kind of phenomena inside these materials. This is just a main list of collaborators that contributed to this very, very difficult project that is continuing. So we hope that we can really start with the full machine in a very short time inside this strange Earth of the goldfish.
Thank you very much, Dr. Riccardo Barberi. Thank you. Thank you for everything. So, is there any questions from the audience?
These are two examples
Is there any question from the audience?
materials that has been collected very close to our university.
Well, Mr. maybe I can make a comment.
Okay.
Yeah, hi, Riccardo. Good afternoon. The comment actually is triggered by Leo Violini's recommendation of comment that he made yesterday, and I feel sort of committed to share Leo Violini's comment and transfer to Riccardo. Riccardo, yesterday Galileo Violini said that it would be a very good idea to organize a summer school in Cosenza at Unica in order to host students and scholars interested in the physics of the machine and the physics with the machine, taking STAR as a hub, since it's one of the, well, we can say that best computer light sources in the develop using star as a hub to gather, to start the training and the education of people interested in developing similar research infrastructure. I think it's a very good idea. I allow myself to make a comment that Calabria is one of the beautiful regions of Italy. Very good food, very beautiful places. So a summer school is just a wonderful idea from all points of view. I hope you share this vision. A very good idea.
One of the advantages of STAR is that it is located inside the university. So it's not a research center close to the university, it's just a part of the university. So for us, this idea to provide also places for formation and high-level teaching, for us it's one of the main objectives that we have. So STAR has been built also with this objective, and the idea, your idea, the idea of Leo is welcome, so no problem for that. We have just to start to organize something, but we are not only ready, but that's one of the main ideas that we have, and we had also 10 years ago when we started, is a new research infrastructure inside the university. That was really very, very new. And so one of the main objectives to have something very competitive was this possibility to put together what you can do in an advanced research structure and what you can do also in a very well-structured university. So your proposition, I think, is really, how to say, well in agreement with this vision. No problem.
Great. So let's work together.
Okay.
Thank you, Luca. We are a little bit tight of time, but I think Lawrence and Leo has questions, so if we can do it rapidly. If Sanjay is around, she start putting her presentation, share her presentation as we do these two final questions.
Right, so as you may know, there's sort of a debate about compact light sources in Africa and whether or not African governments invested in compact light sources would it push off the date that they put together a direct generation light source, or maybe fifth by the time we're talking about this. I was wondering if you could articulate the unique capabilities of compact light sources, whether or not it's reasonable for a light source like Electra, ASRF, to install their own compact light source for those scientific unique capabilities, and economically, if the distribution of government investment across the continent will result in greater overall investment. So basically, it's the area under some curve. Right. So, as you may know, the investment is distributed. Is that actually greater, more investment? And whether or not, I don't know which part of any of those questions you answer. Would it push off the date? What are your thoughts on any of that? Luca, light source.
I think that STAR is a good example of a new kind of compact X-ray sources. It's a new way also to produce at lower cost, larger machine, very high quality X-rays. So I think that we can be, how to say, a study case okay, for the community, if you like. We are ready to receive and to also explain the difficulties and the opportunities that we have to develop this infrastructure. So we are ready to collaborate at any level, also strategic in the sense to suggest or to provide information about the development of this new kind of X-ray sources.
Leo?
Riccardo, I would like to give some more details about what I said yesterday, because this can be the basis for further discussion between our group and UNICA. My idea was basically not only to have a summer school, but have a permanent summer school as a regular event of the Department of Physics every year, which perhaps could be named after, I was thinking, Renzo Alzetta, to give a name which is familiar to you, and hopefully there will be no other candidates in the next 10 years to change the name. But I believe that this can be important also from other points of view, from the point of view of the contact with the region, which could sponsor the idea, the European Union to sponsor the idea, and the participants in this tour, which could be supported also by ICTP, would be basically the young people from the African project, from our projects in the Greater Caribbean, and from Uzbekistan and Iran. We have you have many relations with Iran. So I think that this deserves some further discussion, for which I think our group will be happy to discuss with you, so that you can convey this idea to the rector and to the appropriate Caribbean and European places. By the way, we have had in this meeting participation from UNESCO supporting the idea of this, like sources, and by ISC and by European Union, so that the feasibility can be high, and the advantage of having a very big reception capacity at Tunica in the summer when it is very hot but there is nobody, can be also an opportunity to have better use of your university.
You know that I'm very interested in this kind of suggestions. The point is that we are very young, we are just starting this machine. We have now to be completely full operational, and that's the main objective at short time. But in principle, your idea is welcome. We are very young in this community. We are, in principle, we were not specialists in this kind of machine, so we are physicists working on material science, usually on math physics. But we are not specialists of high energy machines. In any case, we are able to deal with the collaboration of INFM and with Sincrotrones. Yes, is incredible X-ray source, and now we have this responsibility to start everything, to be fully operational, and then certainly this idea to create also schools, even stable schools for the rest of the world is certainly interesting, and we can discuss about now.
Thank you very much. Let's thank again Dr. Barberi for his kind contribution. I'm going to be presenting now. I'm going to be presenting now to Dr. Sanchez. I'm not Djanovic is a scientist, physicist of over 25 years of experience working at the prominent international research institutions such as CERN in Geneva, GSI Helmholtz Center of Nuclear Research in Darmstadt, Germany. She completed her PhD study at the University of Heidelberg. In addition, she had the honor of serving as the Minister of Science in the government of Montenegro from November 2016 to December 2020. And she initiated, during that time, she initiated and led the establishment of the Southeast European International Institute for Sustainable Technologies, gathering 10 Southeast European countries for the project. Thank you very much. CEAS focuses on synchrotron accelerator-based research infrastructure for cancer therapy and cancer research using ion beams. She has been active in the program, and she is going to be talking to us about the synchrotron beating cancer while shaping science in Southeast Europe. So, Dr. Djanovic, yours is
Thank you so much. Thank you very much for inviting me to this event, but apparently I'm facing problems to share the screen.
Right now, what you have to do is, I see that you are in a Mac. Go to your presentation. No, don't touch that. Go to your presentation directly. In the bottom. There you are. Go to this shit. Put it on. In the bottom. Go to your presentation.
I can see. I see you are presenting, but I don't know. Actually, I sent my slide to Lawrence.
Okay, that could also work. Lawrence,
I'm sorry for this because I thought it's easy, but apparently.
Talking to us about
Let me pull it up.
Sorry, stop sharing. I will stop sharing, but I'm also on. Thank you so much. Thank you very much for inviting me. I'm sorry for this.
No problem. We're ready.
I'm I don't know why I was not able
I'm getting there.
Go to your presentation. Don't touch that. Go to your presentation directly. Share the bottom. There you are. Go to this shit. Put it on the bottom. Go to your presentation.
Maybe if you go to the full screen. So once again, it's a pleasure to present yet another synchrotron. I call it CEAS synchrotron, which has the goal to fight against cancer by shaping science in Southeast Europe. But I want to immediately say here that this CEAS is acronym for Southeast European International Institute for Sustainable Technologies, and the whole project is under the umbrella of the scientific council. So next slide. Thank you so much. So global research projects show what mankind is able to achieve by working together coherently. So it's a common goal, and key example of power science diplomacy is CERN. It's moving slide, so let's go follow me.
Okay. Yep.
Yeah, the LHC at CERN actually is the largest scientific instrument ever built, which is symbolizing global cooperation. Go ahead, and every research infrastructure is connected to some of the global challenges. So next, after CERN and Sesame, and we heard many presentations about the Sesame, CEAS is yet another concrete example of science diplomacy. So next. next, and next, you can go next. So actually we are talking about the part of the Europe, southeast region, which takes into account 10 countries, and we are talking about a region of 40 million inhabitants, next, which includes Western Balkan. You can go next one. Which includes the Western Balkan, and you can see here grey area, grey, because the Western Balkan is not yet part of European Union. So this is now a special presentation. Sorry about that. With help of Lawrence, we can manage. So how all connected started? Officially, the subject was launched by the government of Montenegro, and I want to remind you that Montenegro is one of the smallest countries in Europe. It has a little bit more than half million inhabitants. And the background, after 20 years working at CERN, I became the Minister of Science of Montenegro. That happened at the end of 2016. And it took me just 3 months to convince the government of Montenegro to initiate this project, and I was appointed as political lead to set up this scientific framework. So SAIS has many missions. One is to promote collaboration between science, technology, and industry. Another mission is to revive tradition tradition in technology throughout the Western Balkan region. I just want to remind you that the largest part of this area of Southeast Europe is Yugoslavia, which actually had in the past 3 large-scale research infrastructures, all older than that. But in the 1990s there was a war, and the consequences really big in terms that technological development practically completely stopped, and we are facing a large problem. The biggest economic loss of this region is brain drain, and one of the missions, of course, is to try to slow down or to revert this brain drain, and the important also mission is to foster regional cooperation, because unfortunately there are still remaining tensions between the countries in the region. So Lawrence, next, and it's obvious that if you want to reach all these goals, it's obvious that you need pan-European, I call pan-European, but you can call pan-world, I don't know, large-scale research infrastructure, which is based on the latest technologies. So next, very quickly, multi-dimensional aspects of SAIS were recognized by European Commission, in particular by Commissioner Moedas, who was very happy that he decided to support that project. Next, technological development practically. Next slide. Yes, but then actually previous one, the question arose. We wanted to build this infrastructure. We wanted to build pan-European infrastructure, but then the big question came: what SAIS should be to attract political support, and at the same time to attract the support by European Commission. And the next slide, the proposal for SAIS to be accelerator-based research infrastructure for cancer therapy and biomedical research with ion beams came already early in 2017 from 2 key pioneers in the field of ion beams to treat cancer, from Professor Hans Specht from University of Heidelberg, and unfortunately Professor Specht passed away this year, but I want to underline that he was one of the pioneers of ultradisciplinary ion physics CERN. The program was approved in 1984, but in addition to that, when he was the Director General of GSI Center in Heidelberg during the period 1992 to 1999, but then he boosted the establishment of the pilot project to treat cancer therapy with the ion beams, and 450 patients in Europe were treated, actually not at the clinic, but at the GSI Institute, and he also helped to establish the first European clinic of this type in Heidelberg so-called HIT. And also from Professor Ugo Amaldi at CERN, who was a pioneer in the design of particle accelerators, treatments, who was instrumental in establishing the second European hadron cancer therapy now in Pavia in Italy. So as you can imagine, being in hands of such people, I'm not surprised that we had a very quick boost in development this project. So next, I just want the next slide to, and you can go next, because it's it is just and you can click even next. So as you can see here, that what I underlined, the first pilot project in Europe to treat cancer and carbon ions was developed at the GSI, and the first patient in Europe was treated with this method in 1997. Many new techniques were developed, which were required actually to go to this stage to treat patients, and the proposal project was actually created and edited at GSI for the first European clinic, and this spectacular success at GSI successfully treated 450 patients, opened the way to the first ion clinic in Heidelberg. Next, and then you can immediately go to the next slide. So here you see this first facility in Europe, Heidelberg ion facility, and it's also interesting that this facility was mainly built by the GSI accelerator people together with 50 Siemens, and so still that was actually the first clinic which used gantry, what you can see on the right side is like a monster 600 tons of magnets which steer the beam so that beam can enter from any angle to the patient in the patient. So you can go next, go to this stage to treat the patient. So I want just to say that this clinic, you don't need to go back, but it's fine. The clinic started to be built in 2001, and it started to operate in 2008, and up to now 10,000 patients were treated, and the goal to reach 1,000 patients per year was achieved. So in this slide here, you see particle therapy centers worldwide. The orange spots, which are many, not so many compared to the pink one, correspond to much smaller machines, proton machines, Sincrotrones. But what you can see with this map that we don't have so many carbon ion therapy worldwide. There are only 15, still in Europe, 7 in Japan, 2 in China, and 1 in Taiwan. And up to now, 57,000 patients were treated with ion beams, while 358,000 patients were treated with protons. Next, and then you can quickly go to the next. So the CEAST was supposed to be 5th center in Europe or 16th in the world, but CEAST is unique. Why it's unique? Because it's not pure clinic. It is supposed to be 50% research center and 50% therapies. So you can go to the next, and you can go next to fill the slides. So it's really remarkable here that CEAST immediately, practically immediately, attracted political support in the region. Political support from 10 countries. I mentioned in 2017 that the government in Montenegro in March 2017 officially stand beside the project, and I was actually acting like a science diplomacy missionary country to country, and the miracle happened just again a few months later in October 2017. We had the declaration of intent to sign at CERN. It was unique event in CERN, not unique because the politicians were coming, but unique in terms that 10 ministers at the same time were on CERN grounds. And then another political support happened, milestone happened in 2019 when 6 prime ministers from the region signed a memorandum of cooperation at the summit of the Berlin process in 2019. The event at CERN was very important because he's received a regional character after Intergovernmental Steering Committee was formed, I was elected to be first chair, and I was holding this role until 2021, until my term as minister was finished. And I think this presentation probably will be also useful for you, because I will also bring some advices from myself. So next slide. So another important political milestone again very quickly happened, because we received financial support from the European Commission. And first, the European Commission actually was convinced to support financially the project, not only after the project received regional character and there was political support from the region, but much more important that the project attracted a strong support from international research community. And the concept study during 2017, at the same time, concept study for SEAS was created, and the main role for that had Siva Maldi, and that was presented at ICTP Institute in Trieste in front of European Commission, and that was a big trigger for European Commission to say, yes, we will support this project. So we received the first 1.5 million without any competition, without any call, and then later we received another 5 million to start the second phase design phase, not only to start but actually to finalize with the support of the first 1.1 million via competitive call. So you see phase shows competitiveness in Europe. This is exactly because it was in line with pan-European dimension. Another important support, and this is also some message for you that you should probably embrace, came from, again, from European Commission, but connected to economic investment plan for the Western Balkan, not yet used, but SACE became the only research and medical project part of economic investment plan, which is actually part of a much broader initiative, which is called Global Gate Initiative. And that Global Gate Initiative, Gateway Initiative, is something which you can also use yourself. And for example, only for Western Balkan region, 9 billion euro is appointed up to 2027, with the goal to extend to 30 billion euro to 2030. So please take into account that this support for all kinds of economies, highway, railway, etc. But innovation, of course, are important if you bring properly your project. So next, because it was in line with pan-European. Next. Yeah. So what I want here to underline that you can go next slide. So what I want here to underline that what is the backbone of SIS. The backbone of Connect is actually international research support. And today, if you talk about science diplomacy, people mostly spend time to define, to bring the best definition of science diplomacy. But I think the best definition of science diplomacy is science done by initiative is something, and this is actually what then shows with 120 nations working together. And this is exactly, even we had tabulation of political support and still ongoing somehow weak, I will bring that point to you, but what is the backbone of this is strong international research support. So we managed to attract 18 support of 18 research infrastructures in all carbon cancer therapy clinic to work for us to design a new compact design of a new medical accelerator. You will see later which institution designed. So what I would like to underline by international research at the beginning to talk about science and survival, and for really establish this project, we need to build up a strong bottom-up approach. So next. But I think the best definition also. Okay, so now we come here to cancer. Cancer is the second leading cause of death globally, and according to World Health Organization, 10 million people died in 2020, and unfortunately the fact is such that 400 children per year develop cancer. while cancer research was declared by European Commission as one of the 5 missions in the EU Horizon Europe program, cancer is presently entirely absent from the European research infrastructure. So you don't have any single-site research infrastructure, single-site, large-scale research infrastructure which is focused on cancer therapy, and this is exactly where SACE would like to address that. So next. And now I want to show why caviar-charged particles are superior to any other radiation in chemotherapy, although I'm sure that most of you know about that. So in this picture, what you see here is the dose, which is delivered along the length in tissue, depth in tissue. And in this particular picture, the tumor region is marked by red arrows. And so what you can see from this picture is, by conventional radiation, photons and electrons, the largest dose is developed at the entrance of the body, then you can continuously go down and then exit of the body. But what your eyes see is that the largest dose is deposited on the healthy cells, while little on the region of the tumor, and then you don't have any of these metastases. So now different from X-rays and electrons, heavy charged particles have beautiful properties. They hardly any deposition of the dose, and all of a sudden the full dose is deposited at the single point. Now these particles travel in virtual straight lines and stop at a specific penetrating depth, delivering a high dose precisely at the end of the ion path, and this is called break peak. And so by changing the energy in synchrotron, you can achieve that the energy deposition is exactly in the tumor volume. So you can see here these two break peak, red and green, so different from protons. Ions have much larger dose because it's proportional to charge square, Z square. And what is also very nice about ion is that radio resistant tumor can only be treated by them. It cannot be stimulated by protons. And what is beautiful about this radiation is that you can reach tumor wherever is in the body, and even if the tumor is very close to the sensitive type of organs. So in the next slide, I just will quickly go through. I mentioned that many techniques GSI were developed before treating the first patients. One of them is the raster scan technique, and this technique, together with moving break peak by changing energy in synchrotron, allows to treat any shape break peak of the tumor with precision 1 millimeter. And let's go to the next because of the time constraint. I don't want to take so much of your time, so I just want to here emphasize the power of this cancer treatment, effectiveness and survival probability. So on the left side, you see a comparison between ion therapy, proton and conventional radiation for a particular type of tumor. It's called choroidomas, like skull base, and his probability of survival patient after 5 years of treatment. So what you see is that with carbon ions you reach probability of 90% survival. With conventional radiation type, there is a probability of survival only 20% after 5 years. On the right side, you can go to the next, is another example of salivary gland tumor, and the result shows that the survival probability with ions is 80% compared to 25% with conventional radiation, but it's also shown that patients that go through 50 years you reach 100% nearly. So next time, so I just next. So what I convince you, I assume that hadron therapy is the most powerful method to treat patient, but still is a niche in cancer therapy, and the main factor is price. So if you want to have a powerful method to treat cancer, you need to invest 250 million euros, but probably today it's even 300 million euros compared to 2 million with conventional radiation. For example, 2018 worldwide, 22,000 patients were treated with hadron therapy, in contrast to 25 million patients were treated with conventional radiation. Next, on the right side, you can go to the next. Yeah, but actually this is opportunity to develop next generation of ion therapy facilities to expand access to ion therapy for much larger number of patients, and this is exactly the goal of SACE. With the help, as I mentioned, of support of European Research Center and clinics, 18 European Research Center and clinics from 14 European countries, and here is a list of them. They extend GSI for presently existing hadron therapy. Europe hit now with Australia and but many other research centers and companies are currently working on more complex and more cost-effective medical accelerator for using carbon ions, incorporating new R&D innovations for treating cancer like flash therapy. And SEAS is beneficiary partner with this, but at the same time reference users. So next, soon we'll come to the end. I don't know how much time already. So I show you here what is currently going on. CEN, which is called CENX Ion Medical Machine Study Program, together with a large number of international partners, are working towards new generation of accelerated cancer therapy. One option is improve synchrotron by adapting many features, including much faster, more type of tumors. As you can imagine, if you have a movable organ, you need to be faster to extract energy than the speed of moving of organs, but also to adjust to this new technique of flash therapy. In any case, this improved synchrotron, which still uses warm magnets, is going to incorporate a new design of gantry, which I mentioned incorporating warm magnets, 600 tons. It goes down to much like less weight, but it's going to be superconducting gantry. And the second option is fully superconducting machine, including the synchrotron, and then you can see that the size goes down by size, of course, price goes down, and then something in the future, it's not for sales, it's total linear accelerator. Next. GSI, alongside many international research partners, advancing innovative flash radiation therapy, and this is a powerful weapon in the fight against cancer because it will allow to kill tumor in one second. Why? Because flash is ultra high radiation dose delivers in a very short time. We talk about dose rate larger than 40 grays per second. For comparison, conventional radiation dose rate is 1 gray per minute, and it's very nice to see here that, for example, flash therapy was on the top cover of the Nature review of clinical oncology, but that is also nice to see on the right side that at ASTRO meeting, which was organized in 2018-19, there was a survey what are the most attractive research in oncology. On the left side, you see there was no flash, and all of a sudden in 2019, flash became the most important topic, and it's no surprise. Next.
Can you wrap it up? We are over time.
It is now my second last slide. So I just want to tell you, if you are going to go to build a large-scale research infrastructure, you need minimum 10 years, and then next says has the potential. This project now has potential to be a flagship project for EU enlargement. I talked about breast implantation, and then my last slide. I want to congratulate Galileo and everyone involved professionally in efforts in the development of the Caribbean and beyond through large-scale research infrastructure projects. And my advice to you, you need to ensure political support, but be careful because in policy there is no sustainability. But if you at the same time build strong bottom-up approach, I think you have a good chance. Thank you so much, and sorry for not being able to share my slides.
No, if you can stay a little bit more, I know that people will ask some questions in the chat, so if you're feel free to answer them, and let's keep the conversation going. So let's move on to the next presentation. It should be John Susini from the. Can you share your presentation, Dr. Susini?
Has potential to be flagship project for.
So let me present to you a little bit. Dr. Susini holds a PhD in chemical physics from the University Pierre and Marie Curie in Paris, in France. In 1989, he joined the ESRF to work on X-ray optics from synchrotron beam lines. In 1994, he spearheaded the design and construction of the X-ray microscopy beam line, ID21, and subsequently assumed responsibility for its user operation. In 2000, he expanded the microscopy facilities with the development of hard X-ray microprobe and an infrared microscopy facility at the beam line. He recently relocated to Soleil Synchrotron in Paris, where he served as design director for life science. Today, he's going to be talking about the French synchrotron Soleil and his upgrade project at a glance. The project, the floor is yours. If you have a problem sharing your presentation, Dr. Susini?
No, I don't know. Can you see the screen in the presentation?
No, we don't see anything. You have to go to France. 1989. There is a small box with the arrow up. In 1994, there you are.
Okay.
Design of construction of the X-ray microscopy beam line.
Okay, so thank you very much for the introduction.
And subsequently,
I'm very pleased to share with you some general information about
the microscopy facilities
Soleil, which is located on the nearby Paris. And the idea is not really to go too much into the details of the chemistry details, but more or less to first introduce you with the synchrotrones, and second to more or less by a few statistics to show the impact Soleil has on the French project.
The floor is yours. If you have a problem sharing your presentation, Dr.
No, I don't know. Can you see the... So, Soleil is a French acronym which stands for Optimized Intermediate Energy Light Source from LUR, and LUR being the laboratory for the use of electromagnetic radiation. You see here, it's a real picture of the synchrotron here and the different premises surrounding this. Okay, so thank you very much. Soleil is one element of a very, very long history and tradition in the field of synchrotron radiation. It started in 1955 with the first linear accelerator, the 1.3 GeV accelerator, which is not far from the location of Soleil today, which followed by a number of developments, and one important one was in 1963, the Professor Yvette Cauchois, who recorded the first X-ray absorption spectroscopy data using synchrotron infrared mode at Frascati near Rome in Italy. And that was really one of the very first scientific applications in synchrotron radiation. That followed with the construction of an entire lab dedicated to system radiation called LUR, with 3 different machines, accelerator. The first one was ACO, the second one was DCI, and Super ACO. Two of them stopped operation in the beginning of this century. In the French Alps, the European synchrotron radiation facility started its construction in the 90s, in the operation, you know. And in 2001, both major research agencies in France, CEA and CNRS, signed an agreement to create the Soleil Sincrotrones as a company, a private company called Soleil, and its construction started in 2000. You can see there in this middle picture that Soleil is located here, and it's embedded into a very large academic infrastructure campus called Paris-Saclay University. We like it multi-kilometer campus with different halls of research. A few figures about Soleil. So, as I said, Soleil started in October 2001 with 2 shareholders. The European CEA holds the company based on the investment budget and the construction budget of about 600 million euros. And as of today, Soleil benefits of an annual budget operation budget 65 million euros. And with the 2 other companies, and CEA, at the level of 72%. In terms of staffing, Soleil has 360 permanent positions. Although Soleil is a French research center, we exhibit 30 nationalities around the world, and we have, of course, a very important academic programs with universities, several postdocs, trainees, and so on, but also a number of close to 100 associate researchers coming from different places, which are permanently assigned to Soleil research. Finally, in terms of operation, Soleil is what we call mid-energy storage wing, the company, 7 GeV, investment budget, and mid-size, 354 meters circumference, 29 instruments running simultaneously, and of course, 24/7 operation basis with a very high level of reliability exceeding 98 at the level of 70. And Soleil is providing 5,000 hours of lead time every year. Soleil has 360 permanent positions. Very specific attributes of Soleil is the spectral range, since you can see on this picture that the spectral range used at Soleil spans from the high infrared, UV, VUV, standard X-rays, a number of soft X-rays and hard X-rays, associate researchers, meaning that we cover the spectrum, and of course that translates into a wide variety of characterization methods. Soleil is through the 29 instruments we have mid-energy storage wing, and the main techniques, it's not very surprising, are X-ray diffractions, spectroscopy, 29 light regimes, infrared, UV, and X-ray, a lot of photo emission and circular equations, and of course imaging, radiography, and tomography in the X-ray. And Soleil is providing 5,000 hours of lead time every year. Very specific. The portfolio of techniques also translate into a very broad range of applications. Soleil is part of the national strategy for the large-scale infrastructure in France, and we support again a large range of disciplines, nuclear-oriented, some instrumentation, gas phase and molecular cluster, astrophysics, quantum materials, food science, biology, medical diagnosis, innovation with hospitals, health, environment, energy, and earth science. So our mission is fourfold as a large-scale national research infrastructure. We have, of course, a mission in terms of user support and providing service to the largest possible user community, cutting-edge research lab with also a very strong in-house research, state-of-the-art instrumentation without cutting-edge accelerators and designs is difficult to support the range of application of the user community, but also, quite importantly, the social commitment, education, and outreach programs in order to disseminate in a more efficient way the scientific picture to the online communities in So let's go a little bit deeper in some aspects and through different statistics. In terms of user program, every year Soleil more or less ranking 1,500 submitted proposals. We can accept less than half of them. Our mission is in terms of capacity. 3,000 users from 900 labs are coming every year with Soleil. More and more, we would access more support providing service at home. Nevertheless, the mission to control the experiment user community, remote access. We have also very strong program with industry. Since every year we have more than 170 projects with industry of proprietary research. In terms of partnership, actually we are active in more than 180 scientific partnerships of different formats. The number of projects granted by the national research agencies, the number of technology transfer to SMEs, and let's go a little bit deeper in exclusively related to statistics. Every year, the data recorded at Soleil produce 700 publications, which means that in practical terms, since the start of the user program, Soleil published more than 10,000 articles. Every year we have 150 articles with impact factor exceeding 9. And something which is quite specific of Soleil is we have a number of papers involving more than one beamline, meaning that we try to develop this culture of multimodal characterization on that. And finally, as I said, we have also a commitment in terms of training platform and educational platform. We are partner of 66 universities in Europe. 90% of the project involve PhD thesis, meaning that most of the project listed here involve PhD students. We welcome 4,000 visitors every year, which correspond to a total of 30,000 visitors since the very beginning. And we used to welcome and train about 30 apprentices every year on the technical side. If I come back to the science and the scientific program, the access of Soleil is based exclusively on the competitive access based on scientific excellence. We have several access modes, including for industrial research, but in this case it's paid access. We have 2 selection cycles every year, and if your proposal is accepted, Soleil is providing a financial and technical support. But of course, all the data recorded at Soleil actually must comply with open science policy and fair policy, meaning that after an embargo period, all the data are open to everyone. We have 6 peer review or proposal review committees, and you see here the breakdown of the different scientific domains or topics, starting from diluted matter, electronics and magnetic properties, matter and properties of materials, chemistry and physical chemistry, biology and health, and ancient material, environment and health. And you see here more or less the pie chart and the breakdown and the weight of the different disciplines or topics since the beginning of Soleil. And you see that it's pretty well balanced over the 4 main scientific domains. if we compare now with the different domain versus the publication, you see that we are very successful in life sciences, and then follows by the different the chemistry, physics, and physical chemistry. Soleil is not providing only beam time for the French users, since here you see for the 5 years the evolution of the number of proposals and the number of users in the different European countries, but also in the world, Canada, China, Brazil. What you can notice here is, in fact, it's quite interesting to note that the heavy users at Soleil are coming from countries having a synchrotrons on their national land, meaning Italy, Spain, Sweden, Switzerland, United Kingdom, and United States. Meaning that it's clearly the impact of having a synchrotrons in your country make your community much stronger to compete for, let's say, synchrotrons abroad. In terms of industrial and proprietary research, okay, the activity is slowly taking off now, with an average of 170 projects with a paid access, and you can see that most of this access are related to pharma industry, meaning that is structural biology, aiming at solving or resolving macromolecular structures involved in drug design in most of the cases. Let's move now to the hot project at Soleil, which is the Soleil 2 project, which is a 10 years program aiming at upgrading not only the source but the entire facility. Just a quick introduction here, where it's clear that in most of the synchrotrons now are thinking about this upgrade. I'm taking the example of ESRF that I know pretty well, with this, let's say, evolution of the brilliance as a function of the time, of the lifetime of the facility. And it's pretty clear that at ESRF we have seen over 35 years an increase of 9 orders of magnitude of the brilliance. Another point of consideration is the fact that the different generation of synchrotrons follow this S-curve with a clear, let's say, technological discontinuity, and it's clear that the fourth generation is a new discontinuity in the technology used on this storage ring for synchrotron radiation as a light source. Why? Because the brilliance is this invariant characteristic of the beam of the source, which intervene, in fact, in most of the, let's say, on the most relevant parameters for an experimental data collections, meaning that the coherence flux, where B is appearing here, the time resolution, where B is appearing here, and the signal to noise ratio. Meaning that maximizing the brilliance and the coherence, in fact, requires to minimize the electron beam emittance, because you can see that the average brilliance at a given wavelength is, of course, defined by the number of photons you have in your beam, but also the emittance of your source here. The emittance is an invariant equal to the product of the size of the source multiplied by the divergence of the source. So we are now, let's say, witnessing a completely new landscape for photon science with this new type of fourth generation sources. So you have two types. The first are the greenfield synchrotrons, like MAX 4 in Sweden at Lund, or Sirius in Brazil at Campinas. And we heard about that in the yesterday and the day before. The SRF has a completely different strategy and introduced a different way to achieve this low emittance by keeping the same infrastructure and changing the storage ring inside the concrete tunnel. This picture here recalls you that all the synchrotrons in Europe follows now this strategy by trying to beat the emittance limit And Soleil is one of the very, let's say, very ambitious programs with only 53 picometer radian emittance, while the others are a little bit higher. So what is the possible strategy to reach a very small emittance? Again, as the product of the size times the divergence, you have only two parameters. Either you can decrease the energy of the storage ring, of the electrons circulating in the storage ring. But of course, it's something you don't wish to do in most of the case, because if you decrease the energy, you are going to change the spectrum, the emission spectrum of your machine. So the most considered solution is to, in fact, increase the number of magnets in the storage ring, since you have a big effect with this cubic power here. So we are moving to the double band achromat to the multi-band achromat by, in fact, replacing 2 or 3 magnets by a large number of magnets. But that, of course, is very challenging because you need, in fact, to reduce the size of the storage of the magnets inside your storage ring, which has a fixed circumference if you do an upgrade. The net effect of that is today a synchrotron beam is a flat ellipse because of let's say the electrons are circulating on the horizontal storage ring. In the future, with this new configuration, you see that all the photons emitted in this flat ellipse will be condensed, focused in the pretty nice circular beam, meaning that you don't produce more photons, but you have more useful photons. So the big challenge for most of the synchrotrons involved in this kind of upgrade is to squeeze a maximum of magnets within a constrained volume. And the level of miniaturization now is really amazing, since, for example, in the case of Soleil, this is quadruples as of today. You see the size, and you see the next generation of quadruples, same functions, the same power, but you see that we are moving from a size of a cabinet down to a choose box, meaning that it's obvious that we can put much more magnets of this kind than with this volume. Sextuple, this is the large size as of today. This is the next generation of sextuple. Of course, one of the implications are the vacuum chamber, which are much more complex. Today, this is the vacuum chamber for the storage ring. Tomorrow, this is the size, which is more or less the size of a €1 coin. So the compactness and the miniaturization was one of the key elements of this upgrade. What are the expected beam characteristics? First, a big gain in terms of brilliance as expected. The plain plots here are the future performance. The dashed one are the performance of today, so we gain several orders of magnitudes. The coherence will be much, much better. But more interestingly, one of the uniqueness of this kind of upgrade is the fact that the different harmonics emitted by the undulator are much, much cleaner, meaning that it's still polychromatic, but with a very nice shape, which...
1 minute.
Yeah, I'm almost finished. So, on one side, this 4th-generation machine is going to push for wide beams for nanoprobes and base techniques. The pink beam for broadband imaging techniques, because you don't need any more monochromator. You can really select one harmonics and use it. And of course, all the coherence-based imaging techniques will benefit from this upgrade. So, Soleil developed a conceptual design report based on the scientific case broken down in 4 different pillars: advanced material, sustainable energy, environmental sciences, and health and well-being. And this is more or less where we want to push the 29 beam lines we have currently. My last slide is about the program and the timeline. A very important point, which is highlighted here, is the fact that it's not only an upgrade aiming at enhancing the performance of the instruments and the accelerator, but it's also to change the paradigm in terms of business model. I think the new synchrotrones are also a bit greener, and you see here comparisons between the current water consumption, electric consumption of Soleil 1, and the power reductions we are anticipating in terms of water and electricity in a couple of years. So starting next year, we are going to start the constructions with, of course, a new accelerator, but also several modernized beamline and other which will be refurbished, and a very aggressive R&D instrumentations, and of course the phase 2 towards full performances. We hope to open new scientific opportunities by having the entire portfolio of beamlines refurbished. The take-home message here is in terms of collaboration opportunity, is that Soleil will be a very nice, let's say, training camp for new engineers and new scientists to discover the potential of the fourth generation sources during this construction phase, when we have at the same time very experienced people, but quite innovative projects. With that, I thank you very much for your attention and for having listening. And I'm, of course, open to any questions through the chat later on. Thank you.
Thank you very much, Dr. Soldini. Thank you very much. Any question from the audience? We can have only one question. Lawrence.
Thank you for this very nice presentation. I guess I would ask the same question that I asked Giorgio, is that during your shutdown period, will some of your people be looking for opportunities to be like visiting professors, perhaps in Africa or Caribbean or wherever?
Yes, actually, it can work both sides, meaning that, of course, people will be less busy. Although, as I'm sure you noticed that we have a pretty heavy refurbishment program for beamlines. So, but nevertheless, they will have more time for traveling and let's say sharing experience with others. But let's say on the contrary, we will have also more time and more capacity to welcome people, let's say on spot, to see also, let's say, a facility in construction. So I think it can be a win-win situation for the two scenarios.
Okay, thank you.
Thank you very much, Dr. Susini, for your kind presentation. So let's move on to the next one. So can you stop sharing, Dr. Susini?
Yes.
So our next presentation will be Dr. Simon Connell from the African Light Source. Can you share your presentation, Dr. Connell?
Yes, I can. Can you hear me?
Yes, we can hear you. Yes.
Okay, I'm going to share.
So let me present to you while you are sharing.
Yeah, so, I'm about to share.
Okay. There. Professor Connell.
My presentation full screen?
Not yet. We see your screen. Can you go directly to your PowerPoint?
Yeah, you should see it now.
Do you have two screens or only one?
No, I only have one.
That's strange. When I'm
you have to bring your PowerPoint to the top.
Exactly.
It is.
And it helps. I think it helps if you go to presentation mode first, then share.
Okay, let's try that.
Maybe it doesn't. I don't know.
So I'm going to stop presenting and try to present again. Okay, I think you should see my whole screen. And now I go to presentation mode. Do you see it now?
Now we can see it. Perfect.
Okay.
Thank you again. So let me present you very fast. Professor Connell is a professor of physics within the Faculty of Engineering and the Built Environment at the University of Johannesburg. He has research interests in particle, nuclear, quantum, and applied physics, nuclear energy, material science, high-performance computing, and innovation. He is the past president of South African Institute of Physics and is the founding member of the SA Participation in High Energy Physics at Atlas at CERN. He has published over 170 papers in international journals and also Atlas author more than 800 papers. Today, he's been talking about the African light source, the project status. Dr. Simon Connell, the floor is yours.
Thank you very much for the opportunity to present the African light source to you today. This first slide has the website of the African light source and some papers, of which the top left one is the one I really want to draw your attention to. And I hope the slides can be shared and then you would be able to click on these links. So I only want to talk on a few things on this slide. Why do we want the African light source? So the main articulation is the Sustainable Development Goals, in which we see particularly African challenges. By that we mean diseases, for example, in the medical area, which won't get the attention they deserve if it's not Africa studying it. Examples could be the hypertension that particularly affects Africans, or you could imagine diseases like malaria, tuberculosis, which particularly affect Africa. Also, recently, there was the example of coronavirus, where there was a big delay in Africa getting the vaccine and would have helped if it had its own intellectual property in that. But you could go further in African challenges. How do we beneficiate our own raw materials? How do we adapt energy systems for our environment? And what about our paleo and cultural heritage? Who's going to study that? So we do identify these particularly African challenges. And once we have identified them all, we ask what is the science that will look at all of these challenges and address them? And then what is the research infrastructure that's going to support that science? Overwhelmingly, one comes then to the African light source. And here I just show you, it's often asked, is Africa ready for a light source? And I want to say we have enormous excellence in light source usage in Africa and also in readiness to use a light source. I want to show you that. Also, without a light source, we have what's called the African science diaspora. An enormous amount of young African scientists leave. So we train them to PhD, to postdoc, and then they actually end up in light sources of other countries. Anyway, a quick snapshot here, you can read down and see what actually becomes success stories in medical interventions. These are particularly African here, that all the pictures that I'm showing here are examples from Africa. And there isn't really time to go into them, but it hopefully gives you an idea of the size of the community and their industry. And here's just a quick example of rock art, which is again in Africa, and we should be studying our own rock art, and the data should ideally reside in Africa. Here's an example which is absolutely amazing. It looks just like a piece of rock. It was broken in half when the prospectors wanted to look inside, but it wasn't really possible to see that there was something in there. Even with standard X-ray CAT scan, it wasn't really possible. But if it was looked at with phase contrast tomography, and I'm sure that previous speakers have mentioned that. Then you would see an incredible story. It's actually a detective story. There's a mammalian reptile and something closer to a mammal, and one has been injured and has crept into the burrow of the other, knowing that it is hibernating. And here is just another example. It's a hominid skull. It's not had the rock extracted, but the rock inside is imaged at the same time as the details of the skull and the teeth. And what's interesting is it got the attention of the South African president. It was able to be sent within a few months to the ESRF to be scanned, and it is an enormous amount of rich science that has evolved, particularly because there was not a lot of destructive cleaning of the skull. Now, we also need to be inspired by competitive industry. I don't know to what extent that's being treated at the conference so far, but there are recorded here over 100 companies co-located at Diamond, and it's not very different at other synchrotron facilities. So we recently had the African Light Source conference for 2024, was at the end of November. And then just showing you a snapshot of the program, of which I put the link there in case you are interested. But there was a beautiful set of 6 talks, and you see these paper clips running down the right-hand side here, and you could go and look at those talks. It was a specially designed session by Ed Mitchell of the ESRF. And just to give you a very quick flavor of them, is that the synchrotrons become a knowledge hub. So they really become a font of competitive industry and of innovation. You see pictures here from medicine, energy, food, microelectronics, and so on. And this is just the incredible range that you get. And the interesting thing is, at the ESRF, for example, and I'm sure for many other synchrotrons, we're in our 2nd or 3rd generation of student released to society. By that I mean professor to student as being a generation, so that those who are now employed in industry are 2nd generation users. That means very, very advanced users that do not need any convincing. And you see something similar to what we showed at Diamond. So here are an enormous amount of companies, in fact, international leaders, which are co-located in the same valley as the ESRF. And something that you're seeing is that students are making startups, and here are 2 of them, and you could find them on the web, and they interface between industry and the synchrotron, and allow industry who don't have experience in it to have the total service, sample preparation all the way through to analysis and interpretation done for them. So those are just a few things that the incredible progress that's being made. In fact, I heard that industry are almost out competing the academics and need to be restricted somewhat. Otherwise, they would outcompete the academics. Is a situation then that wouldn't be very, very good. The other things that we do is hold conferences that I've already mentioned, but here's a page where you could look at the 7 conferences that we've held so far. And then what is the footprint, you may ask, of feeder facilities? So I don't really like the word feeder facility because all of these are X-ray facilities in their own right. And all of them can have a talk on their own, how they were set up, and particularly credit must be given to the International Union of Crystallography's Open Lab project, which has really done very, very many of these in Africa. But having X-ray facilities allows one to train students, and that is incredible research in its own right, but also hands-on training. And one could then, for example, use international facilities remotely. And then if we specialize down and zoom onto the bioscience capacity, I'm meaning here capacity in structural biology, where you can look for targets for developing medical interventions to neutralize pathogens or develop vaccines. And so, whereas these might not all be using synchrotrons right now, they definitely are able to do so. And so you see a spread of activities, and there's a similar map for paleontology and geology and so on. And then there's a developing thinking, which I can say is science diplomacy, is facilities envisaging themselves as being at the least regional. So the only one I'll really mention now is the X-Tech Lab. But while I'm talking, you can read, all the other logos. But X-Tech Lab is in a smart city started by Benin, and it's got several very, very competitive X-ray instruments, and is aiming at the hundreds of students' production per year. You can also find it on the web. It's growing, and it's reaching the dream, the vision of hundreds of students per year. Then also industry, what is the profile of industry? So here's an example of a South African company, but with all the dots around the world, you realize it's actually global, but of course is based mostly in South Africa. And it has booked at one stage 3 weeks solid of beam time at the ESRF. That's paid for beam time, where it doesn't have to publish, and studying catalysis. And when you can glimpse, if you can glimpse the work, it's exafs, Zanes, and done at an extremely high level, and not requiring university participation with the in-house scientists. From here, I want to move on to what we call the strategic task forces. We launched them this week. This week we launched them, these 3 strategic task forces. So launched their reports at the African Academy of Science General Assembly and Scientific Conference, just closed yesterday. So that is why I couldn't deliver the talk yesterday, because the network was just too bad in Nigeria, where we held the conference. But nonetheless, you see 3 items, and these go beyond the capacity building, the network building, the bottom-up community-driven initiatives. These now become instances where we really need African governments, where we're actively in conversation with several African governments, and showing them the reports of these strategic task forces, which is aimed to ignite conversation about these. So you see the African beamline, so it could be plural as well. And at our own conference in November, we have 4 offers to have African beamlines at various international facilities. You can have up to 4. And it's very exciting for us to talk about what beamlines these could be. And at the African Academy of Science conference, there was enormous excitement about a beamline for agriculture, for plants, and also for indigenous medicines, finding the active ingredients and so on. And that, what's exciting about that is it catches the intention of Africa, because it would be very African, the indigenous medicine component, and putting that on a scientific footing, and even heading to clinical trials once the active ingredient was found. So that could be really something that would ignite the African governments. But of course, there's so many. There's the paleontology, there's the mineral beneficiation, and so on. And then the buzzwords that you find everywhere else, like energy and so on. So we would be looking at international facilities, and I'll just mention Sesame as one very leading place, which is in our time zone, and which has space and so on, where we could discuss an African beamline. And we've seen that this was a very, very important part of other countries as they move towards establishing their own synchrotron. An incredible success with national beamlines at other facilities, but ours would essentially be a regional African or even Pan-African beamline at another facility. And then we would also be very interested in the LEAPS concept of virtual beamlines to leverage other access from an African beamline. So collective African memberships of the International Advanced Light Source. I just want to say, don't forget, there's leadership in astronomy from African countries. The square kilometer array is a $2 billion infrastructure, and it's built on schedule, and it's performing very, very well, and it's getting front covers of Science and so on. And just the other day, I saw that it had the most sensitive gravitational wave murmuring spectroscopy of any, looking at in the thousands of pulses within the galaxy, and using them, the timing of them, to hunt down the structure of the gravitational waves, and maps of these have been produced. And the square kilometer array is really contributing to that, and its core is African. So with that as a basis in terms of large scale infrastructures, we want to build on that. And we need collective African membership of international synchrotrons to learn the governance of these and the science diplomacy aspects. And then I'll go a bit more into the African regional infrastructure. Just quickly flash you up some. Here's all the accelerator physics capacity audited in Africa. You can only see really in the speed I'm going to go that there are 5 countries with accelerators, and about the same with capacity and instrumentation and control systems. And then what really stands out is medical Linux, over 450, and dotted all over the continent, and leads to a synergy between being able to run all of these medical Linux better if we can train accelerator scientists who can keep them running better than they are, and they are existing facilities. And then the science diplomacy aspect, I only show you one of 3 examples where it's had profile at the Africa Union. And you see here a call on member states to support the initiative. And just another thing, we launched, it says to launch, but I could have updated it. We did launch the conceptual design reports, now open and available for download. And we did that a few days ago in Nigeria. So it's a 388-page document with about 130 authors. The most important author is Sekazi Ntingwa, and many thanks to him. He devoted about a year of his life to managing and editing all of the authors. But I want to say it's plonk this heavy tome on the desk of a policymaker, and I think it has impact. It shows we've thought carefully about what we want and been able to conceptualize it. And then together with this group, we've forged partnerships, as you see there, and we working on a UNESCO resolution. It's already present in draft, but you can know that it's not something really scientists can do. It must be done at ambassadorial level. And we've had several conversations with the Kenyan ambassador, who will who has undertaken to mobilize all the African ambassadors to UNESCO. Anyway, back to the infrastructure that I mentioned, Strategic Task Force on Infrastructure. This basically gives us a menu of different price tags of things that could be bought and put in Africa. And so African governments can literally start spending. And with this increase in infrastructure of a small scale, then of course it's obvious to you all you're doing training. And they start right from the humble small lab X-ray facility going all the way up to the light source. I was watching the talk on STAR, and STAR is very beautiful to me. I have seen quite a lot about it because of my friendship with Luca Serafini, and we intend also to have STAR in Africa and to be a partner with Calabria because of that. And so far, NEXA, our Nuclear Energy Corporation, has offered an existing building which has a concrete slab of 100 meters by 30 meters, which is big enough for housing STAR Africa, and it's all under one roof at the moment, a very, very high roof with a gantry. So this could be a very, very important start for them to put that on the table for us. And so we are in a advanced stage, and we are looking at the fundraising for this. Also, I want to announce we have drafted a MOU. It was supposed to be signed. Maybe it's already signed in the hours since I last looked up, but I think it's imminently signed between the African Academy of Science and the African Light Source. So this is a very, very important step, that science academies legitimate the experts who are the community-driven engine that is pushing for the vision of the African Light Source. And so we did photograph ourselves signing, but there was still one language item of a small nature that we were just harmonizing. But we expect to be able to hire professional full-timers from 2025 because of new money coming in. Will be the first stable funding that we receive. And so we look forward to 2025 to be a very, very, very big year for us. Now, maybe you didn't hear about this project yet, but I bring it to your attention. It could have been a whole talk at this conference. It's INT 0104 project of the IAEA, Technical Cooperation, and it's to enhance transnational collaboration among light sources and expand the user base. So it launched this year, 2024, and it's starting the spend in 2025. So 2024 was the design stage. The report is out. You can download the report. Says what we're going to do. The most important thing is to establish a training platform, and we will invite all those who would like to democratize and make available their training material to put it on this one common platform, and to use a specially designed artificial intelligence. This is all to be funded, to be able to extract material from this training platform, which will then have petabytes of material. And then also funded our mapping exercises for countries without synchrotrons, as developing countries, to look at how will they match the existing expertise to the existing light source opportunities, to the challenges that their country face, and so doing persuade their government. So we expect a lot of mapping exercises and a lot of training. And one of the things I would like to say that we in the African Light Source want to do with the IAEA platform, and it's written into the proceedings of the workshop, we want to make a Pan-African university. And we're very happy if, let's say, the Caribbean or any other partner joins us in that. We want to make a virtual university out of it. So not just training material.
Can you wrap it up, please?
Yeah, it's very close to the end. We want that training material to be accredited in each and every country in Africa, so that it lowers the threshold to building these things into university courses formally. And we have a lot of material on governance and financial models and so on. And just to flash up, really just the last one, 2035, you see on the right there, the first spade must go in the ground. And that will be at some site. So that's our timeline. This is my last slide. And this is really a jazz song by one of our famous musicians, Hugh Masekela, his song is called Tumamina, which means send me, and you can see in the writing there. So it's a call to all of us to put our shoulders to the wheel and work towards these various light sources that we want to build. I'll end there. Thank you.
Thank you very much, Dr. Connell. Due to the time constraint, I will look at a fast question.
Hello, Simon. Good evening. Thanks for the very nice and stimulating talk as usual. And also thanks for reminding that we share a vision of compact light source development at NEXA in South Africa. But I have a quick question for you, Simon. I'm sure that now in the CDR, you have a budget structure for the African light source. Can you tell us, let's say,
yes,
not just the total amount, but at least how it is distributed among various items of the project, at least?
So I think just roughly it will be $1 billion, and it will be a third in the civils, a third in the staff, and a third in the instrumentation.
Okay.
And then there will be another $1 billion over 10 years. And that's the operations and the people and the development.
Okay, thank you.
And we want that to predominantly come from African governments. That's the main reason of the 2035. It's not to train young people. We believe the young people are already there, or as soon as we put the spade in the ground, that's already a few years, they will be coming. Looking at the example, like Brazil or something like that. It's not 2035 to train young people or make up our minds or anything. It's to do a thorough job raising this to the profile of African governments and changing the thinking of African governments to invest in science.
Okay, thank you very much, Dr. Connell. So our next presenter will be Massimo Ferrario. Is Massimo, can you share your presentation, please?
I'm here, yes. Can you hear me?
Yes, I can hear you.
Okay, so I try to connect, and it's really nice to see all friends here like Patrick, Leo, and I hope soon to meet directly. Select the window, entire screen. Allow.
So Massimo is currently the senior scientist of INFN, coordinator of Spark Lab at the Frassati IFN laboratories, and he's also the project leader of Eupraxia Spark Lab design study, which is a plasma beam driven for the Eupraxia project. In the last year, Massimo has been working in the field of high brightness photoinjectors pre-electron lasers, and advanced accelerator concepts, including plasma accelerator. He's co-sharing, giving workshop series with the title Physics and Application of High Brightness Beam. And he has given 2 workshops in the Caribbean area, one in Cuba, another one in Puerto Rico, which will bring you back, Massimo. So yes. he's going to be talking about the Eupraxia project, a plasma-based accelerator. Massimo, the floor is yours.
Thank you. Can you see my slides?
Yes, we can.
Okay, fantastic. So I can start. And thank you for the invitation to talk about a subject that I like very much, that is the Eupraxia project, that is actually supposed to be the first user facility based on a plasma accelerator, or at least this is our goal and the intention to open up a new technology for the future, for the next decade at least. The motivation are quite well known. You can see from this very well-known Livingston diagram the evolution of the maximum energy achieved by accelerators over the years. And you see that in this logarithmic scale, the increase of maximal energy grows exponentially. But you can see also that from time to time, you have to jump from one technology to another one, because a given technology reaches saturation. For example, you can see here Sincrotrones, after a very fast rising start, then they reach saturation. They are still used today, but they cannot, of course, achieve higher and higher energy. So now, after the invention of synchrotrons, colliders, and so on, we are in the range of LHC machines. And the question is, what is the future? What next about LHC? CERN has already proposed to build the FCC machine, that is a quite large machine, that probably is the largest possible machine based on the current technology. And so the problem is what can we do in the future? And maybe the future is going in the opposite direction, to have a very compact and cost-effective machine like the one based on plasma acceleration. And you can see here the same plot showing the recent progress in the laser and beam-driven plasma acceleration. And after the proposal of this technology and the discovery of the cheap pulse amplification by Gerard Mourou and Donna Strickland, you can see that there is a very fast increase of maximal energy achieved by plasma accelerators, well beyond now the GeV range, and is still growing. So there is some hope that we can enter in an interesting area of applications. And for this reason, some years ago, we decided to start with a proposal, a project for a new high technology user facility based exactly on plasma acceleration, using laser or LINAC as driving beams. And the goals are clearly to shrink down the facility size, improving also the sustainability of the accelerators, and to propose some application, not only for scientific purposes, but also for industrial or medical application, and in particular to drive a short wavelength free electron laser, paving thus way the future linear colliders R&D. The principle of plasma accelerator, maybe you are not completely familiar, but you can see that this is a very nice picture taken at Berkeley. And it represents a module of plasma accelerator. It's essentially a plastic holder. Inside there is a capillary, typically made by sapphire. And inside this capillary, there is a hole with a 1 millimeter diameter, for example, in our case, in which we can fill a gas. The gas is then hydrogen, in our case. Then the gas is ionized via a discharge through 2 electrodes located at the extreme end. And then you can create a plasma that is essentially an ionized gas in which you can excite a plasma wave separating the electrons from the ions in order to create a region of high density component, single component plasma, where high electrostatic fields can be produced. Maybe this scheme better represents what happens inside. So if you have our plasma after the discharge, the ionized gas, then you inject a drive pulse that could be a laser or an electron beam. The drive pulse starts to separate the electrons from the ions, and the electrons start to oscillate transversely. And for a short time, open up a bubble of high density positive charge. Here you can obtain the gigawatt per meter accelerating fields useful for accelerating another bunch. Maybe this animation can better explain what happens inside. This is the driver you see enter inside the plasma, and the electrons start to oscillate transversely and creating this bubble where you can inject the beam. The problem is that the size of this bubble is quite small. For example, in the case of a density of the plasma of 10 to the 16, the plasma wavelength, that is the longitudinal size of this bubble, is of the order of 300 microns, and this is quite small. We have to be very careful to inject the second bunch at the proper position in order to be accelerated on the wake of the drive pulse. And also the transverse size is quite small because of the separation of electrons and ions. And so this is quite challenging. The size of this plasma channel is of the order of the capillary cross-section, the human hair cross-section. So this is very challenging. Nevertheless, we are testing in around the world both two options, the laser-driven, in which the separation occurs thanks to a laser, or the beam-driven option, especially here in Frascati. We are working on this solution. You see that essentially the physics results is the same, the formation of a bubble where the electrons can be accelerated. The goals of Eupraxia are listed in the conceptual design report. Essentially here are the goals, the dreams of Eupraxia. These two are already under implementation here in Frascati, a free electron laser and a betatron radiation source. I will talk to you about these two topics later. There are also development of high repetition rate laser and new technology for laser in other institutes. And there is still some other option that could be included in the future, for example, positron beam generation and acceleration, and components for linear colliders, and also for a Compton backscattering source. We decided to use the free electron laser as a first demonstration of the capability to run a complex machine with a plasma, because FEL is a very well-established technology. It's very useful, especially at a short wavelength for discovery in the biophysics or in atomic, solid-state physics, many applications. But is quite a large machine. You can see here the XFEL DAISY. The undulator area is here, the user area here, but you still need a quite long LINAC of the order of a kilometer in order to achieve the energy of about 15 GeV needed for driving an Ekstrom free electron laser. This is the reason why we are excited to demonstrate that it's possible to replace such a long LINAC with a capillary as the one I've shown you in the picture that was actually using producing a 10 GeV electron beam in the same configuration. And you can see here the results of the plasma technology with respect to the RF technology. And you see that the recent results in terms of maximum achieved energy is already in the so-called FEL territory for driving a short wavelength free electron laser. And so this is the reason why we push ahead our project, also with a good background in the experimental demonstration of the possibility to drive free electron laser by using plasma accelerators. You can see here these papers have been, and the experiment has been done 3 years ago, showing the possibility to drive a free electron laser with a laser-driven system in China, in our by our colleagues in Shanghai, but also by a beam driven, as we did here in Frascati 2 years ago. And this somehow opened up the way to demonstrate the feasibility of a free electron laser driven by a plasma accelerator. Of course, there is still a lot of effort to complete, a lot of R&D to do, especially in the generation of high-quality electrons beam, laser development to achieve enough interesting repetition rate. In our case, we are using an RF LINAC, and also here we should try to improve the repetition rate. But there are also a lot of progress in this direction, and the number of applications are certainly wide. For this reason, we established some years ago a wide international collaboration, essentially in European collaboration, with about 54 institutes from 18 countries in Europe. And we succeeded to provide a conceptual design report of our facility that has been accepted also by the S3 roadmap. That is an important award for us, because states that this facility is considered important for the evolution of the infrastructure in Europe. And thanks to this award, we succeeded also to find enough financial support to start with the free electron laser here in Frascati. We have got about 180 million euro for the free electron laser demonstration, plus other 20 for the beta-ton radiation source. So this, the idea is to develop a distributed research infrastructure with two pillars. One in Frascati, where we are building the beam-driven plasma user facility, and the second one that will be a laser-driven facility, still under discussion among 3 candidates where to do this. Good candidates are in UK, Czech Republic, and again in Italy, in Pisa. And then there are a number of laboratories, excellence centers that will collaborate to the construction of this distributed facility. In Italy, there is the headquarters of the European collaboration, and also the beam-driven pillar, as I told you before. This is the new building that will start to be digged by the end of next year. And inside, what we hope to install is a LINAC like this one, better explained here, in which we are the plasma module here at the center of the building. The plasma is driven by a 1 GeV X-band RF LINAC with a high brightness for the injector here. So the plasma double essentially the energy of the incoming beam. And then we have the undulator beam lines followed by the photon beam transport and the user area. Just a fast review of the main component of this machine. The photoinjector is very similar to the existing Spark Lab here in Frascati, or LCLS in Stanford, where we want to generate both the driver beam and the witness beam by using the technique that we have developed here based on the velocity bunching and the laser comb. And, with this, we can generate both the driver with a 200 picocoulomb charge typically, and a witness with around 30 picocoulomb, with the high quality needed to drive a free electron laser. Then this beam is injected in the LINAC, in the 50-meter long LINAC. X-band technology has been chosen because at present represent the frontiers of high gradient RF frequencies already available. And in collaboration with CERN, we have designed and we are testing X-band components for building the LINAC as needed. Then the beam is injected in the plasma. Of course, the plasma is the most critical part. Still, we have to be careful in order to preserve the high quality electron beam as we have at the entrance. Test facilities here in Frascati where we can train ourselves to match properly the beam to the long plasma channel, in this case, about 40 to 60 centimeter long, because our target is to generate a 1 gigavolt per meter gradient inside this capillary. But this is in principle enough to double the energy of the incoming beam from 1 GeV to 2 GeV, or different energies if needed by the specific applications. So you can see here the first test, the first application is designed to have a beam at the exit of 1 GeV in order to drive the free electron laser in the water window. And you can see here the start-to-end results made by simulations showing that we can actually obtain interesting parameters for driving the free electron laser. There is also the option using the full X-band LINAC, but of course our goal is to demonstrate that we can do the driver with the driving the FEL with the plasma itself. After the plasma, the beam is injected in the undulator chain. We have foreseen 2 beam lines. One is called Aqua for the soft X-ray generation of 4 nanometer wavelength beam. This is an interesting wavelength because it's the water window and allow people to do testing biological samples. That is very interesting. And we are expect to use Apple X undulators with the possibility to change the polarization along the machine. The other beam line is the range of the wavelength is 50 to 100 nanometers and is expected to work in the seeded mode in order to stabilize also the better radiation emission with a different target of users. I can skip this. And you can see here the expected FEL radiation parameters for the short wavelength. The tunability range is from 3 to 10 nanometer, and a photon per pulse that is not extremely high, but is enough for our users, at least they claim this. A photon bandwidth that is of the order of 0.3%. For the other beam line, we have a 50 to 150 nanometer tuning range and these parameters that you can see. After the FEL, the photon beam must be diagnosed, must be manipulated in order to clarify the quality of the photon beam. Need monochromators, split and delay lines, and then we can transport after monochromators or polarization measurements to the user area. So this is still under development, this region, because it's quite important and not fully under the expertise of the Frascati group. So we will do in collaboration also with Elettra and other facilities. For the scientific case, we have a number of users that are declaring interest in the usability of the water window free electron laser pulses, essentially for coherent imaging of biological samples, and also for the usual application of X-ray spectroscopy, Raman spectroscopy, and studies of photofragmentation of molecules. For the area beam line, the target is different, is a wavelength that is more suitable for a gas phase investigation, for example, atmosphere, aerosol, also molecules for, again, for medical applications. Another important source that we expect to drive with the plasma is the so-called beta-tone radiation source. The beta-tone radiation is there under development in the Spark Lab tunnel. So this is a machine that is already running. We have just received recently financial support of 20 million euro, 10 of them dedicated to the development of the beta-tone radiation source. And essentially, we need a high power laser to excite a plasma wave in a gas jet. And during the excitation of the plasma wave, the laser also can capture electrons and accelerate on the wake, as you can see in this simulation. Here is the laser driver, and these are the electrons that are captured in the bubble. These electrons are captured from the plasma itself. So the gradient here is so strong that even the electrons of the plasma can be accelerated, of course, with a quality that is not very high. But what they do during the acceleration is also a transverse oscillation, as you can see here. These electrons are oscillating in the transverse direction. And during this oscillation, they emit radiation, also in the X-ray region. And we want to enhance this emission in order to use the beta-tone radiation.
1 minute, Massimo. 1 minute.
Okay, I'm all finished. To extract X-ray radiation from the plasma. The spectrum of the radiation, unfortunately, is quite a broad spectrum, because even if it behaves like similarly to a free electron laser, the problem is that the equivalent undulator parameter in this case depends on the gamma of each single particle and the position, the transverse displacement of each single particle. So each particle will provide a different line in the spectrum, and so at the end, what you observe is something like that. Nevertheless, it's a very interesting radiation, because the range could be in the order of 1 to 10 keV in our case, and ultra short, of the order of few tens of femtoseconds. So in between the synchrotron radiation source and the incoherent radiation. And you can see a possible application are imaging of samples that we will do for demonstrating the possibility to do this kind of imaging, but also to test ourselves about the possibility to do coherent phase contrast imaging, 3D computer tomography of biological sample, with a clear possibility of using for medical application, like they did recently at RAL, showing that they have been able to produce a compact tomography of a human bone with a resolution that is better than the usual X-ray sources. Okay, so this is our time scale. For the beta-tone radiation source, we expect to finish the commissioning, start the commissioning by the end of next year after the installation. To finish the use of the beam after the commissioning. While for the Eupraxia, the goal is to provide the first photons by the end of 2029. Okay, with this, I can conclude saying that we have achieved enough confidence to provide a user facility based on plasma in the next 10 years.
Thank you, Massimo.
Okay.
There's a question, Patrick, that wants to ask.
Yeah, sure. Massimo, exciting talk. Good to see you here. Thank you. On your timeline there, when do you think you'll be able to do the first synchrotron radiation-based experiment using your plasma-based accelerator?
Using the beta-tone radiation source,
or the plasma one.
The beta-tone radiation, that is plasma incoherent radiation, we hope to do by the 2026. This is with the FEL, the first experiment will be done in the 2030. So in five more years from now.
Okay. Perfect. Thank you very much. Let's thank again. Keep the conversation going in the chat. We are moving on to the next speaker, which is Dr. Eneli Monerjan. Did I say that correctly? Who is a research fellow in physical and electrochemistry and a SAS instrument scientist at the Helmholtz Center in Berlin in Germany. She obtained her PhD in physical and electrochemistry from Tartu University in 2008 and research focuses on operandos studies and structural characterization of lithium-sulfur, sodium-ion batteries, and supercapacitor using SANS, SACS, and WACS techniques. So, Annelies, the floor is yours. Can you show? We cannot hear you. We cannot hear you nor see your presentation.
Can you hear me?
Now we can hear you, yes.
Oh, perfect. And then I'm trying to share my screen. It's always very difficult. Can you see my screen now?
We can see your PowerPoint.
Sorry.
Give it to this in slideshow.
Swap. Okay, now probably you see correctly.
No, we're still seeing the PowerPoint. One way to do it is unshare your presentation. Don't press escape.
Okay.
Just go to the Alt tab to your browser.
Yes, screen.
Stop the sharing the presentation, and then redo it. Share the windows, but to the slideshow, not to the PowerPoint presentation. Go to the slideshow.
Oh, sorry. Okay.
If not, did you send your presentation to Lawrence?
No, it's okay.
Okay.
Screen. Can you see that now?
We are seeing the PowerPoint, not the slideshow. You're sharing the slideshow, the PowerPoint, not the slideshow.
Oh God, that's very strange.
Just keep the slideshow running.
Yeah.
Alt tab, keep the Alt bottom.
Can you see that now?
No. We are still seeing the PowerPoint. What I'm trying to give you is the instruction just to share the slideshow, not the PowerPoint.
Yes, I do understand it, but problem is that I have 2 screens, and that's why I can't change that.
Okay.
That was the problem. That's otherwise it will be easy if it will be easy. Sometimes it's not so easy.
Another thing that you can do is give the presentation as that and move manually the PowerPoint.
Can you see now? Still not.
No, it's still in PowerPoint. I'm sorry.
I'm really sorry. Sometimes it's very easy. No, I can't.
Did you send me your presentation? Do I have it?
It's very big. It's extremely big. It's yeah.
You can put it in a Dropbox. I think there's plenty of space there.
It's really big.
You can send a link so they can be downloaded by Lawrence.
It's guys. Let me try. Let me try it.
Do your thing.
Sorry. It's supposed to work, and it should not be so difficult, but apparently it is difficult. Oh God, why is it today not working?
And I think at the very beginning it was, and then it just went.
Mm-hmm. Can you zoom a little bit that
I will
that
just,
screen?
yeah, because I can, I can do it like this. Is that good? Can you see that?
I'm seeing the PowerPoint.
Yeah, I do understand that you see the PowerPoint, but oh God, it's never happened so much. It's always was very good, and now it doesn't happen. Oh God. Yeah.
We have had people presented that way. Just make
Yeah,
the
that's why I'm thinking like is that okay?
Yes, keep
And
it as that.
you
Yeah.
can see
but,
just that
but,
one, and I
but
Yeah.
make the
I will,
images on the left smaller. Yeah, there you go.
yes.
That's fine.
That's fine.
Yes. Okay, wonderful. Thank you so much for your patience. I really didn't expect to have so many technical issues on my side. I'm apologizing for that. Anyway, greetings from the Berlin and also from Bessie's side. I'm kind of representing here the synchrotron and also the neutrons. So I'm totally changing the gear from very fundamental physics, going to exploring the batteries and using the scattering technique, not only the synchrotron based, but also the neutron and other large scale facility. So what kind of challenges we are facing? All around the world, we are facing, of course, the energy challenge, and this energy challenge is also lies on the HB heart. So means that we in the Bessie we try to accomplish more and more techniques which can provide more information about from XE2 to operando. So you have different multiple length scales, you have a more mechanistic understanding, and also the lot of beamlines have been now more and more aligned to the operando measurements. I'm talking about a little bit of SACS instrument, which we have at BTB lab and also in HEB. Little bit of beyond lithium-ion battery, because you know that today what you have in the pocket, in your laptops or in your cell phones, the battery is already very good. However, we are still having the challenges, and which kind of challenges we have. Scattering technique, of course, what I'm going to use, and electrochemical analysis for this storage mechanism. So the challenge of the transition is, I think I'm not the only one, also not the European one. We are facing lack of raw materials. And if we are talking about solar panels, we are facing gallium lack. And if we are talking about the batteries, there are even more related to the lack of the chemicals or metals. Namely lithium, cobalt, and nickel. And that's why we have a European Green Deal, and of course a lot of actions have been going on, and not only the European pace but also the worldwide pace. And most critical part of that is that we are operating, of course, a lot of materials, but we are also limited. So means that we have already listed 14 critical raw materials in 2011. But the list is growing, and it has been already increased by 34 critical raw materials. So means that we have a lot of contributions to do and find the crucial points how we can improve any energy conversion or any storage materials. And Bessie here not only can help to do that. So what is our landscape? Scientific landscape is more and more oriented already the energy conversion materials research, as you can see from here. And mostly the proposal number of the batteries are increasing rapidly. And the driving questions with what actually the scientists are coming to the synchrotron is, can this technique, spatial or temporal resolution, monitor changes effectively? And also, how do changes in material chemistry or electrode, would it be then negative or positive, varies affect the properties under operating conditions? And most importantly, at what length scale we have to take care of that. And is this electrode integrated into the system, or is the other components also significant from the analysis point of view? And here you can also see a lot of beam lines which are already operando experiment ready. So it means that if the user is coming to us, we can also point several beam lines where you can do the operando measurements. It means that you can really online and real-time monitor your materials. It means that we have a multiple facet approach, multi-length scale possibilities, and learning about the mechanistic insights. And most importantly, the approach from ex situ to operando. So if we go to the small angle scattering, then I think the technique is not very difficult. You can, beauty of that is that you can use the X-rays and neutrons for that. You have very simple symmetrical setup. You have a sample in between the beam and detector, and you can vary the distance between the sample and detector, which gives you also different length scales and information what you are looking for. So the neutrons is very easy. You can play around with the contrast matching, which is well known in biology, and also the drug results. But if you do the battery research, it's also not very well known, but it can be used as a contrast match, and I will come back to that later. If we're talking about the X-rays, you can also use the anomalous small angle scattering in order to play around with energy, and you can then approach the interested metal particles in your system. Why I use the small angle scattering is really because of the approach of the different length scales. So because in the batteries, okay, electrochemistry is one thing, but where the electrochemistry is affected, is it now the nanoscale or macro scale? Then this is giving the information the most properly. So it means that we are aiming to understand so this microstructure on a very atomic layers, but also the micropore structure and even the particle size. So, and the instrument what we have in Bessie and the BTB lab is actually the typical setup of the RSAX or SAX measurement, and you can approach then till very wide range of the energies. Plus, you can play around with energy, as I mentioned, and also contribute information for anomalous small angle scattering. So, if I'm going now to the for the batteries, then I'm looking for really information about the carbon materials. So these are two typical chemistries of the beyond lithium ion batteries. One side we have a sodium ion battery, which is related to the carbon materials, and the carbon materials either a soft carbon or a hard carbon. And on the other side, we have a lithium sulfur battery, which is also accommodating sulfur inside of the carbon material. So these both electrodes, would it be the negative or positive, is also very important contribution from the carbon side. And this carbon material is more and more difficult to design, but it's at the same time very easy to design, that you can tune that in various ways, and then according to your needs you can have a perfect carbon material. So if I look at the small angle scattering on a worldwide, and it will be the small angle scattering, how many chemistries have been studied with that, then I have to say that it's not so much, because the small angle scattering in one hand it's quite easy, straightforward technique. However, the battery research, it's still in the baby steps. So the most important is like, is the electrode really being studied as a part of the system? And are there other components very important, like if I can use the contrast matching at all? and is the external parameter battery being managed? For instance, if I charge my battery and if I'm charging so fast that I can't really monitor that, then most of the information will be lost. Then it's also instrumental point of view. Is it instrument spatial and temporal resolution capabilities is actually what I want to monitor? Can I see everything what is I want to ask or answer the question? And is the system now open or closed? Because there are also batteries which are flow batteries, and means that you are you can also study that and take the components out of that. And most importantly, from an electrochemical point of view, is really the steady state. In the case of electrochemistry, battery is never really in a steady state, so that actually adds another challenge to the researchers, how to then get information out of that. So its modalities are ex situ, in situ, operando, and time to time people tend to in situ and operando, although the operando is quite, I would say, sexy word to put in the titles, but you really need to understand the concept behind that. Is it then in situ, rather quasi-operando, or so on? I will come back to that later. So if the carbon materials is tunable, then we would like to know how much we can tune and which direction. So see here the amount of the carbon powder, and with what you can actually cover almost the football field. So you see the area, surface area, almost 2,000 square meter per gram. So you don't need much of the material, but this material accommodates a lot of ions and also is very useful for the reactions on the side. Plus, it is also, if it has graphitic areas, is very good electron conductivity. So the thing is that small angle scattering is an amazing tool or technique in order to understand the structure on the really nanoscale level. If you look at now the images on the both sides, then they look totally different. There is no similarities. However, if you go to the nanoscale, they are very, very the same on this actually nanoscale. So means that in the first place that either would be the small scanning electron microscopy or transmission electron microscopy, it will not give the full picture, and then you might miss some very crucial information. About the tuning, then you can start from the one carbon and tune with either the temperature or the chemical changing or the doping. You can really tune the carbon from really, really amorphous to the almost graphitized material. So if we go a little bit more to the sodium-ion batteries, then the carbon choice is really easy because it's very expensive. You can tune, as I mentioned, and the surface area is also very large. But now it's a question, is the surface area really important key parameter? Do we really need that? So there are a lot of graphitizing and not graphitized carbons which have been tuned and tested in sodium-ion batteries, and there are also quite many storage mechanisms of the sodiums. And there is a hypothesis that, okay, the sodium wants to intercalate and then find a very nice closed pores, and then it will be quasi-metallic state, and then it's cozily then it's stored. Now it's a question, which kind of carbon is most suitable, how this intercalation happening, and how this carbon should be looking like. So we have been taking a look at quite a many hard carbon materials. We have been tuning them, trying to understand also the carbon nitrile nanocomposite by the chemical vapor deposition. If we close the pore or artificially change the pore sizes or close the pores, how then the storage mechanism is changing. And we definitely can see changes in the this small angle scattering patterns, as you can see also here. And it really influences also on the nanoscale the storage mechanism. If we go further, we wanted to really know the correlation between the electrochemistry and then now the storaging, and wide range, because you have a typical sodium ion batteries, you have a sloping capacity here, and then you have a plateau capacity. And the sloping capacity is really defined also how this sodium ion is intercalating in and where is this then stored. And small angle scattering and wide angle scattering is a perfect tool to expand a very wide area, not only the microstructure here or the micropores, but you can quasi in all length scale understand what is happening on your material. So we did the correlation. So we did the small angle scattering on the with neutrons and also with wide angle X-ray scattering. So we try to understand on a very lengthy length scale what kind of parameter of the structure is playing a role. Here, unfortunately, now you can't see because they are overlapping with each other. But the thing is here, if I'm moving that away, then you have a possibility to understand the lateral extent. So lateral extent is really on the graphine's sheet length on these materials. But it's not only defined. There is another Rundel length which describes the curvature. So we learned that ratio between this lateral extent and the curvature, how often this curvature comes for in the material, will play a role. On top of that, we also learned that the interlayer spacing is dynamic parameter, which will change during the charge and discharge. However, the lateral extent and the curvature parameter is fixed all over the time of period. So we saw now the 4 different materials and also saw the trend and empirical change. So interaction between this dynamic and the interval of the static parameters of the lateral extent and curvature really supports then higher plateau capacity. So you can really store more sodium inside of that. We went even more further because we wanted to know that, okay, if the sodium sees now the armchair or zigzag edge, which would he or she like more? So where will go? So this, in that sense, the studies are ongoing. The preliminary results are here. So the energy is really different compared to the armchair or zigzag, and we see that the zigzag is at the moment more comfy for the sodium. Coming for another example is lithium sulfur battery. So you see already here that everything and a lot of things going on at the same time. You have a lot of capacity fading behaviors here. Irreversibility, the precipitation, 12 electron transfer reactions, and phase changes, because we're starting from the solid state sulfur and going to the lithium 2s, which is also solid, but everything in between is liquid. So we will change even the phase. So now it's a question where this where is the mechanism is taking place? Is it taking place inside of the carbon material micropores, or is it going to be on the surface? So we turn to the neutrons. We have a contrast match with carbon with a deuterated electrolyte, and by doing so, you can the sulfur and lithium 2s becomes more visible. And this is how it looks like. Then we had 2 weeks of neutron beam time on the small angle scattering. And you can see the electrochemical wetting, which is comes very nicely visible, plus the formation of the sulfur and the lithium 2s precipitation. And it really systematically happens all over the period, and it's very, very, very stable. So now it's a question, when is it happened and where? So the protocol is like this, that you are charging and then you kind of quasi-stopping, and then we also measured the impedance measurements. Then we again charged, and then we did several cycles. And before that, we needed to understand what is the state of the open, porosity of the carbon, and if now the precipitation takes place, then we learned that during the charge process, the sulfur particles are pretty big, so they will not fit into the nanopores. And if the lithium 2s is precipitating, it also doesn't take place in the nanopores. So this was our main finding, that yes, even though we put the sulfur inside of the micropores, it will not take the phase changes inside of the micropores. It comes out. If we come now to the electrochemistry, which is very tricky and it needs the steady state conditions, especially the electrochemical impedance spectroscopy, which I did in between, then you can see that if you are open circuit voltage or at the discharge, then you have a very big, like a semicircle with a tail. So it means that you have at the beginning, the electrochemical wetting has not taken place properly. If we go now to the further state of the discharge, like a second discharge, you can see that already kinetics is taking place much faster. So the semicircle has been decreased quite a lot. Plus, you have two processes taking place instead of only one. So you have one semicircle, you have a one time constant process is going on, and some diffusion limited processes. But if you go further, then you have already two separated processes going on, plus diffusion.
1 minute, Nelly.
Yes, I'm going. And then impedance will show us together with scattering, and you can definitely see the change. So we try to fit now the length of the impedance plus the scattering. So always the question: if the observation which we are making is operando conditions from the electrochemical point of view, or it's also operando point of view for this spectroscopic technique what you're using. So this I always ask. Doesn't matter which scientist I'm speaking about, and for myself as well. Of course, we are facing a lot of scattering contribution challenges, and this is not unknown for anyone who is doing the operando measurements. So you have anisotropic behavior or the contribution, also some beam damage phases. But if you compare now the small angular neutron scattering or X-ray scattering, you also see that there are different effects from different layers. If you're interested to know what we are doing further, we are also hiring, and we just started the lithium sulfur project, which we are going to do on the DRL level 5. So if you're interested, check us out and LinkedIn. And also, if you have any questions regarding lithium sulfur batteries, then yeah, I'm happy to help you out. With that, I thank you for your patience, and all my collaborators, and also taking a little bit of time and making advertise of the LEAPS. We are going to have a LEAPS Innovation Battery Research Forum 2025 in January in HEB, so in Berlin. You are more than welcome to submit the abstract, or if you're interested to come along and just listen what we are doing with synchrotron and batteries. Thank you very much.
Thank you very much, Dr. Emily. I will ask everyone that please ask their question in the chat due to the constraint of time that we have. So we are going to move on to the next presentation. And Dr. Hark, please answer the question from the audience. Thank you very much for that. We're going to be moving for our next presenter, which is Dr. Hans Christian Will. Is Dr. Hans Christian around?
I'm here. Can you hear me?
Yes, I can hear you. You can
Great.
start sharing your presentation while
I will try.
In the meantime, I'll be presenting you as well.
Thank you.
Dr. Hans Christian Will did his PhD at the University of Hamburg in 2003. He has worked at the beamline as a beamline manager at Petra 3 and DESI Hamburg from 2010 to 2019. He has been in different committees at India at DESI, steering board at the Hartley steering committee. He has several publications, and today he's going to be talking about the Petra 3 at DESI, brilliant opportunities for solving grand challenges by modern research using cyclotron radiation. Dr. Will, is that the correct way to do it?
Yeah, my name is Hans Christian Wille. Yeah, that's all good. Thank you very much. Thank you very much for a kind introduction, and it's a pleasure to be here. Thank you also for inviting me, and best regards from Hamburg. So I'm trying to give you a quick overview about Petra 3 at DESI, what we are doing also in terms, especially in terms of maybe solving grand challenges. One of them you already heard in the last talk is, of course, about energy. And so I hope you can see my presentation in the right mode, and I'm going to move on. Let me check, is it fine? Yeah. So this is the overview of the Petra 3 synchrotron. It's actually a third generation machine running at 6 GeV. We have a rather really nice emittance value in the vertical scheme already, and the horizontal scheme is not yet where we want to have it. As I said, it's a third generation machine. However, it's the largest synchrotron radiation source in the world with a circumference of 2.3 kilometers. We are running 25 beamlines. We have 2 of them still under construction, and we give about 5,000 hours to our users at each of this beamline for research. The reason why our ring is so large is actually that Petra has a long history. It has been built for particle physics in the very beginning, and there was also some breakthroughs like the gluon discovery in the 80s. It was then a pre-accelerator for a larger ring, and only since 2010 it's actually running as a fully dedicated third generation synchrotron radiation source. We are also planning for upgrading our source like others have already done for fourth generation source, and we are planning to have the shutdown end of 2029 and then be back in business in 2032. I'll come to that later again. So in view of DESI, this is the campus. You can see this is our Petra ring, but this is not the only thing that we have on site. We're also running actually the machine for the European XFEL. We have our own low energy free electron laser, the first one in the world, as you already heard today. And we have a lot of different excellence centers and cooperation partners like the Center for Structural Systems Biology, the European Molecular Biological Labs. And we are working together close with University of Hamburg, Max Planck Society, and also the Helmholtz-Zentrum Hereon, and especially Sweden and India. If you know a little bit about synchrotron radiation techniques, actually we are basically serving all the methods that you can think of in terms of diffraction, scattering, spectroscopy, and imaging. The red ones that you see here are the beamlines that we are still going to build. I'm not going into the details here, but if you have a question, please let us know if whatever experiment you would like to perform, I think we will find a solution in the X-ray regime. Just a little bit about the statistics. So Petra 3 is a national source actually, and we are of course not only serving national users, but almost a little bit more than half of it are still national users. However, almost half of it are also coming from all over the world, and we are serving about 7,900 user visits per year, and from over 44 countries actually. Coming to the advantages of synchrotron radiation, you probably all know, but this I think is really impressive if you compare it to the X-ray tubes, which are a little bit higher intensity nowadays. But you can see the impact that the synchrotron radiation sources have in terms of the average brightness. The first, second generation, the third generations where we are still located here, and then the upgrade even gives it another boost. And actually, if you want to have an idea what this means, if you think of a microscopy experiment that we do today with 1 second exposure time, that would actually take about 30,000 years at a standard X-ray tube. So a little bit about methods. We have heard about scattering, small angle scattering, and of course you can study structures using different methods with different resolution. One of them is scanning microscopy that can be combined with tomography. And actually it can not only be combined with tomography, but you can also have different contrast mechanisms like X-ray fluorescence, absorption, or diffraction, and in the future maybe even inelastic scattering. Contrast. So what you actually do is in this here, you focus your beam down to a small spot, and then you still rotate it to do tomography, and you get a combined resolution scan with that. I'll come to that in a minute. So scanning microscopy is, of course, one of the main advantages also in the X-ray regime is large penetration depths. You can do in situ and in operandi studies, as we already heard in the previous talk, but you can also do then a 3D bulk analysis without destructive sample preparation. And as I said, you add analytical contrast of several different methods. You can be element specific, you can see the chemistry, and you get structural information at the same time. There's still the so-called mesoscopic gap, which says that basically there's a difference between what we can do by focusing in the end and the atomic scale, which is a factor of 100. And actually there are many interesting physics and chemistry phenomena that we would like to study exactly in that range. So we are very much looking forward to the upgrade of our machine to cover this gap. Let me give you a first example. This is imaging. Here, actually, it's the 3D virtual histopathology of cardiac tissue from COVID-19 patients. That was done by phase contrast tomography at our Beamline P10 in collaboration with the University of Göttingen, Mainz, and Copenhagen, and other centers. So what you actually can see here is that there, in the heart tissue, there's a strong difference in the segmentation of the vascular system. Actually, the vessels are very well oriented and constant in diameter at a, let's say, a healthy patient control tissue compared to the ones that was actually infected by COVID-19. There, actually, the deformation is strong, and also there were large deviations in diameter as well. This has all been done actually by a tomography, as I said, and the resolution that was achieved there is about 160 nanometers, and you can see it really can scan through the tissue, and then the interluminar pillars could be identified for examples. Let me give you a second research on coronary research. I have to mention that actually at the very beginning of the pandemic, we, I think, were very rare centers that actually did not immediately close down. We did for a few weeks, all beam banks except for a few, which were actually doing this study that I'm presenting here. It is actually a study using molecular scattering techniques to screen the large number of possible drugs for deactivating the SARS-CoV virus. And this is actually a study that has been performed in a large cooperation with from DESY, the European XFEL, the Heinrich Pette Institute, Helmholtz Zentrum Berlin, University Hannover, and Caltech. The scientists were on site and preparing the samples day and night, and actually within a few weeks they scanned about 7,700 different samples, and they had a considerable number of hits of 38 were actually the so-called heat, which is a complex structure, is catalytically split by protease and blocks the active site. And this is, of course, might be a basis for medication against the COVID-19. This is a very successful thing and an excellent collaboration. Now, of course, talking about the sustainability and the grand challenges, one of the large interesting research areas is catalyzers. And the good thing, of course, of X-rays, again, here is that you can actually here really go in situ and in operando, because you are not limited by not being able to look inside a chemical reactor, for example, as you would be by optical light. So what you can do is you can combine imaging and spectroscopy methods, and because most measurements of the operating catalysts cannot really resolve local details. So what you're trying to do is that you image oxidation states in the catalyst in an in situ or in operando fashion. As you can see here, we have a capillary with glass wool, and then you put in the gas that you want to have, you heat it up, and you have an outlet, and you can analyze what is actually going on at the exhaust and make an element analysis in the end. And then you can study these things in operando. And this is what you can see here. Here you see the temperature rising. The ignition temperature for this process is 290 degrees. And here you can see the H2 and O2 current in the analysis. It suddenly drops when the ignition starts. And then you can see that the H2 is slowly going up. And these kind of things you can basically directly image, and you can see in what states which parts of your catalyst are in real time. And this is, of course, due to the fact that you have the sense, so the sensitivity to the oxidation state given by the spectroscopy technique that you are combining with imaging. Another thing, again, about catalyzers is very interested. You can combine very high resolution imaging with the contrast of the element sensitivity of X-ray fluorescence. The question here was really in a catalyst particle, like fluid catalytic cracking of crude oils, that is where the catalyst is embedded in a zeolite particle, and they wanted to understand the poisoning due to traces of iron in these oils. So what you can see here is actually picture with high resolution tomography of this particle. You can see the iron contrast at the iron K edge and the electron density. And then what you can do is actually, you can, in the end, scan through the entire particle and get the distribution of different elements here marked in color, and see what is actually ongoing with a resolution of about 100 nanometer, scanning through this single particle in a catalytic reaction. Then another, of course, also important topic is semiconductor industry, high resolution imaging by plethysmography. This gives you quantitative insights down to the nanometer regime. Why would you like to do that? Well, it is, of course, very interesting to get information about the actual content of a ship to quality control. You want to see whether the ship is really built as you would like to have it, and also national security is an issue here, because you actually want to see what is actually on the ship, maybe when you buy it from an external company. So one of the issues and challenges, of course, if you now have seen the field of view that we are able to see at the moment, and you see the dimensions of the real ship, like an M1 ship here, for example, it is actually only a very small portion that we can do now. And at Petra 3, it would actually take about 3 years to scan the entire ship with this resolution. But at Petra 4, with a 500 times higher brightness, we hope to be able to scan this ship within the several days only. So I don't have to explain probably about diffraction and powder diffraction, but as you know, you get a very specific scattering pattern from each material, and this you can combine with imaging again if you actually do scanning X-ray diffraction imaging, where you scan with a, let's say, 100 nanometer to 10 micrometer beam size through the object, and you actually look to a specific spot where you know this is very specific for a certain element. You can scan and see the element distribution in an object by scanning. And actually, I don't have to introduce the field because it has just been done, but battery research is, of course, one of the very, very forefront research topics at the moment. And here, for example, a group of scientists was interested in getting local information on the lithium distribution during charge and discharge of a standard battery, and they could really see they could actually really see the distribution in the cathode or anode, and see what was actually the amount of lithium with high resolution by using this this diffraction-based imaging technique. Talking about catalyzers and electrochemistry, I think this is a very nice example where actually researchers we are looking to a corrosion-resistant metallic material that is used, for example, in chemistry, also in rockets and everywhere. These materials show corrosion resistance that is based on the so-called phenomena of passivity. Passivity actually is driven by the fact that a small layer of oxygen is actually formed that prevents these materials from corrosion, even in very, very aggressive environments. But there's also a phenomena that is actually leading to a strong decrease in this passivity, and this is the breakdown process, and this is something that they wanted to study. And what I explicitly like about this is this multimodal in situ concept, the approach that they used here. They actually studied this by different X-ray techniques and also electrochemical techniques. So what they did, actually, they were able to see the thickness of the passive film by X-ray reflectivity. They could study the chemistry of the passive film and the change of the metal lattice by grazing incidence X-ray diffraction. They could see the concentration of the elements by X-ray fluorescence, and then also the chemistry of the surface in the electrolyte by X-ray absorption spectroscopy. And all this actually in situ. This is a fantastic example of the complementarity of all these techniques and what you can mean by in studying these processes when they are actually happening on the surface. And what they actually found out is that there's a strong change at the pH 7 around between 700 and 800 millivolts, and and this happens at pH 2 at around 900 millivolts, and the water splitting provide photon which change the pH value near the surface, and in the end they were able to see that the oxygen evolution reaction, which is actually the water splitting process, onset coincides with the loss of the passivity and the severe metal dissolution. And the typical transpassive breakdown alloys where C6+ is postulated to be dissolved at a high anodic potential is not observed here, and this actually the oxygen resolution reaction plays an important role in the mechanism of the breakdown, and it needs to be considered when studying these corrosion effects in these types of materials.
2 minutes.
Thank you. Okay. Good. Yeah, that's fine, because that was my last example, and I just wanted to mention our upgrade program, which is actually called Petra 4. Where we actually really pushing it to the limit. We call it the cross-scale view of structure and function of complex systems in nature and technology. So the real X-ray microscope for chemical, biological, and physical processes. And what you see on the left is actually that this is the beam that we have today in Petra 3. And this is what we expect to have at Petra 4. So that's more like the point light source and a huge increase in spectral brightness all over the entire photon energy range. And we will go down to about 20 picometer radian emittance. And the diffraction limited X-ray energy will then be right high up here. And we are very much looking forward to that, because that will really give opportunities to do things that we can do today hundreds of times faster, or to really close the gap from the diffraction to the imaging resolution. I just wanted to mention that we are not only going to have a brighter source, we are already planning for also having access to our sources in a much, much faster way. And this is actually already tested this year at Petra 3 at 5 beam lines. And we could actually then have access to beam time at the fastest that we did today. It was only 8 days between the proposal and the actual beam time, which usually takes about 6 to 9 months or even longer. And this makes us a very flexible scheme. And we can also combine all kind of different proposal schemes that we have into one simple access proposal. And this, in our view, is the future, very much also fitting to short-term important scientific questions and the fast access for industry. So I don't think I have to summarize along everything that I've told you. Let's just let you read this, and then I think I'm at the end, and thank you very much for your attention.
Thank you, Dr. Will, for this amazing talk. I will ask the audience to ask their question using the chat, just to be able to make the time. And so there is a change in the agenda. Now we are going to moving on to Dr. Professor Adele Trabelsi. Is he around? And Dr. Will, just check if the chat is going to be making questions.
Okay, thank you. Thank you so much.
No problem. Thank you for everything. Is Professor Adele Trabelsi on?
Hello.
Hello.
Yes.
Oh, there you are. Are you ready for your?
But I think there is a talk before me.
That was the change. We move you up. Okay.
Okay. I wasn't advised about that.
Yes.
So let me just put my presentation and share it with you.
Okay. Perfect. What I'm going to be presenting you real fast for everyone to know you. Professor Adel Trabelsi is Director General of the Tunisian National Center for Nuclear Science and Technologies, for a second mandate after having managed the CNSTN from 2004 to 2010. Between these two terms, he has been Director of Physics of the Physics Department at the Faculty of Science of Tunis. He's also associate researcher at CERN, based on Geneva, Switzerland, where he acts as a team leader for the Tunisian High Energy Physics Group. He has a PhD from the University of Paris Diderot and has conducted research at CA Paris-Saclay and CERN. So he will be talking today about Tunisia's role in a long-awaited synchrotron light source, a gateway for Africa, MENA, and the Arab world. So, Dr. Adel?
Yes, I'm trying to share with you my presentation.
Yes. in the Google Chrome, there should be a small square with the arrow up. You have to press that button.
Yeah, okay. Okay.
Just a question, have you sent the presentation to Lawrence?
I don't see it here.
Okay.
Excuse me.
I'm sorry if I have some trouble with my presentation.
In the meantime, I will tell the audience that please do not leave. There are several presentations in the afternoon, very interesting ones. So I know that it has been a long day, but the great presentations are keep coming in these last days on this Syncrotrones in the Caribbean and beyond. Dr. Adele?
Yes, I'm sorry, but I have some concern with my presentation.
What are you seeing in your computer? No.
Okay, I think I have, so I have to share.
Dr. Traversi?
Yeah, I'm trying to share my presentation. I can't. I have some trouble.
Okay.
So I will do again.
What we can do, if you like, if you can send the presentation to Lawrence. I think there's a Dropbox link that we send to all the presenters, to all the speakers, that you can also, if you feel like.
I think it's okay now. Okay.
There you are.
Do you see my presentation? It's okay?
Well, we see it on PowerPoint.
Okay. Still the PowerPoint now?
It's still in PowerPoint. It's not in his slideshow.
It's the
If
same
you feel
problem.
like that, that's okay.
And now?
I don't see anything in my...
There we go. Oh, and then just go to the little screen, slideshow, little screen, pull down screen button.
Do you see my presentation now?
No, we only see the PowerPoint. What you can do is actually to present your presentation like that, just go manually by slide.
Okay. Okay. So let me share. And now you see my presentation?
We only see the PowerPoint. What you can do, don't leave the slide, the slideshow. Don't leave the slideshow. Don't press escape. Press Alt, the Alt button, and tab, and select the browser that you are in.
I am making the presentation from the PowerPoint. I can't. Okay, I will present like this. I have no choice. So I am dealing today about the Tunisia role in a project of synchrotron light source for the MENA region, Africa and MENA region. I present myself. I am Adel Trabelsi. I am Director General of the National Center for Nuclear Science and Technology in Tunisia. I am also particle physicist, and I have been collaborating with organizations like CERN and the French Commissariat of Energy, Atomic Energy. So I would like to present my country, Tunisia. Tunisia is the most north country in Africa with a population of about 12 million persons, a GDP of $50 billion. So we are located in the southern river of the Mediterranean Sea in front of Europe. And this is a strategic location for Tunisia. So the Tunisian National Research System is based on 4 components. So the research component, we have about 40 research centers located in 11 technoparks. And among this research center, we have around 500 laboratories covering different fields of research, and also supporting units. For the educational component, Tunisia has 13 universities, totalizing 200 public educational structure institutes and 75 private higher education institutes. For the human resources in Tunisia, we have around 12,000 permanent researcher, professor in the university, and 270 students. And we have also supporting organizations that are mainly the center that provide HPC and high-speed internet connection for the research centers and universities. We have also funding agency and a center for providing connection to databases and documentations. So I show here the main research center in Tunisia.
Excuse me, sorry, but I only see the first slide.
Yes, Sunny.
Sorry?
We only see the first slide. Now we can see the slide you were talking about. Okay, don't put it on presenter mode. Just move the slide as you go on. We suggest you to do that, please.
Is it okay now?
Yes, now it is great. Okay, yes, that way. Thank you.
Okay. So the breakdown of laboratories in Tunisia by fields are, we have 50% of laboratories working on STM and engineering sciences, and the other half is about health science and agriculture and social sciences also. So the strategic objectives of the scientific research program in Tunisia are divided in different components covering the needs of the country, mainly about strengthening the higher education and research system. So the aim, as I said, is to support the excellence in scientific research and innovation, establish research and innovation that are impactful for the components in the country, enhance the efficiency of research and innovation system, and strengthening and dissemination of research and innovation ecosystem at the international level. So this program is supervised by the Ministry of Higher Education and Scientific Research. So the performance indicators of the system in Tunisia has been steady progress. It's mainly in scientific research, as I said, in engineering and in STM fields. So in Tunisia, 70% of the scientific publication are in the Q1 and Q2 classification. And Tunisia is classified among the most, compared to its GDP and its population, the most has the most publication in Africa. So we see here the evolution of the scientific production in Tunisia. As you can see, there is a steady progress of this production, and also an increased quality of scientific production. So the distribution of scientific publication by fields in Tunisia, the main components and the main fields are engineering, computer science, physics and astronomy, mathematics. We can, if we combine that, we see that the STM field has about 75% of the scientific publication in Tunisia. So Tunisia is well classified and well ranked in the Global Innovation Index among African and Arab countries in that region. And we have a progress of this rank from year to year. Also, Tunisia has a strong presence of women in the field of scientific research. It's ranked as the first country in Africa and in the Arab world in terms of percentage of women acting in the research field. By university, we can see here the rank of the Tunisian university in scientific publications. So we have a progress of this rank for all the 13 universities that I mentioned in Tunisia. The ranking of the Tunisian university is recognized among the various ranking system. We will see that in detail later. So the impact of the universities in Tunisia compared to the SDGs. So Tunisia is University of Tunisia are well ranked in that field. And as you see, during the last Shanghai ranking, the University of Tunis Al Manar is ranked among the 900 to 1,000 rank. It's among the few university ranked in Shanghai ranking system in Africa and in the Middle East. So for that university, we are well ranked in the mechanical engineering and chemical engineering, energy science, and most engineering fields. Tunisia is a partner of Europe in various research programs, mainly the Horizon programs, the last one, Horizon Europe. And Tunisia has the possibility to participate to this program like all European countries, and we have a very good rate of acceptance of our projects, which is about 16%. We have also bilateral cooperation with countries in the regions, most of them in Europe, but also we have collaborations in Africa with neighboring countries and with South Africa. I would like to present an example of such a program, which is named the Partnership for Research and Innovation in the Mediterranean area. In this program, Tunisia plays a great role. As you can see, we have 78 projects, which is comparative to the number of projects validated or accepted for European countries. So among these projects, Tunisia has successful projects in both sections, Section 1 and Section 2, with a high implementation rate. So what is the role that Tunisia could play for an upcoming synchrotron light source for Africa and MENA region? So Tunisia has a powerful system of scientific research, and that can be used. So we consider in Tunisia that a synchrotron light source could be a powerful tool for scientific research. It could also provide beam for to study material science, biology, chemistry, and physics. And we think that implementing such tool in the region could enable cutting-edge research and technological innovation. So the role of synchrotron light in scientific advancement for the region will impact various fields like material science, medicine, environmental study, and nanotechnology. And sorry. So in the MENA region and in Africa, we have a lack of advanced research of infrastructures. We have limited access to synchrotron facilities. There is 2 small facilities in the region, one in Jordan and another one that could play that role in South Africa. And we think that the strategic geographic location of Tunisia, the well-established scientific community, and the leading institutes and the research center could provide an opportunity for Tunisia to play a role in such program. So in our country, we see that such facility would be a tool or a mean to support regional scientific collaboration, to develop high-level expertise and training in synchrotron related fields, and to position Tunisia as a hub for scientific research in MENA and Africa. We think that such program or such opportunity could strengthen collaboration in Africa and MENA countries. This could be a joint projects and research initiative, and could be also a regional advantage in sharing knowledge and resource. So we expect from such a project to strengthen scientific capacity in Africa and MENA region, and to enhance the state of art of this research tools. So we see also an economic and social benefits from such facility. This could boost the economic growth by supporting new industries and innovation by synchrotron-based research, and also to attract international investment and in research and technology. Also, we see also societal benefits by addressing regional challenge in healthcare, environment, and technology. So such a program will represent challenges and opportunities. The challenge would be also, unfortunately, the high initial investment and the technological and operational challenges that will face African countries. The opportunity are the international partnership and the funding opportunities and the expansion of scientific community in Tunisia and the surrounding region. In conclusion, we see Tunisia playing a pivotal role in establishing a synchrotron light source. Tunisia has a potential as a gateway for advancing research in Africa, MENA, and the Arab world. So what we expect is support for continued development and international collaboration to see such an important facility implemented in the region, in Africa and the MENA region. Thank you.
Thank you very much, Dr. Traversi. Thank you. I invite all the audience to put their question in the chat so that we can continue to our next speaker. From now on, this is my last. This was my last intervention as the session chair. I'm going to pass the torch to Dr. Lawrence Norris, who's going to be your next host as a chair in this afternoon's session. Have a great afternoon, everyone.
Hi, good afternoon. So we are going to move. We swapped two speakers, right? Who's the next speaker, Leo? Is it Max or Juliana? Say again?
I think it was Puig, then Juliana.
Okay. All right, got it. Okay, that was.
It might help if we share the program on the screen and get a brief overview.
There were some changes that I haven't, at least on my screen, I haven't made.
Yes, I think it's Puig.
Okay, so Dr. Puig, are you here? Is he here?
Apparently, I just received a message that they are making an adjustment for the connection. They would need 3-4 minutes. Perhaps we can ask some question to Dr. Traversi during these 2-3 minutes.
Well, there is a comment in the chat from Luca. I don't know if Luca, would you like to speak directly to Dr.
Yes,
Andres?
It would be better. Luca.
Oh, yes, of course. Thank you. Good evening. Yeah, I was just
but Dr. Traversi is left.
He left. Ah, well, okay. So
He is left.
Well, so I mean, okay. I think the comment that Luca would make was, what do you think the effect of compact light sources would be in terms of Africa actually having a third or fifth generation light source. Do you think it would push the date back of that eventuality happening, or would it
Well, let me
increase the
tell
number
you a
of
story.
users, or what?
Let me tell you a story.
Okay.
You know where the first free electron laser was operated in the world? 1996. In the basement of the UCLA physics department by Professor Claudio Pellegrini using a compact light source. So you can see what this game can take you and where it can take you.
Right. Right. Okay. Understood.
I know because I was there. I was a visiting professor at UCLA physics department in that period. So the very first experiment of high gain was done with a very compact accelerator that clearly didn't offer to the community a photon beams to do research, but it was necessary to develop the physics of the machine in order to get the LCLS 10 years after and the XFEL 12 years after to run, to operate, and to offer to the user community the photon beams. So, okay, this may be a metaphor. The metaphor is if you want to develop a research infrastructure using advanced radiation beams and you don't have the $1 billion needed to start with a synchrotron light source, you might start with something that can offer you in a couple years in a small laboratory, small research infrastructure, the option to do already some physics with the machine. I don't know if this fits with the African light source. That it is you.
I understand. I'm going to say
if this fits, but it looks to me like a cheap, quick option to start doing something.
Yeah.
I mean,
right.
Lawrence, Simon is not here, and I would love maybe if you would comment because the African Light Source Project is much more advanced than the Lamista GCLS. Has there been any serious discussion in the AFLS about a compact light source?
Yes, and I would say there are two schools of thought. That they're a good idea. It's a way for each university or whatever set of universities to have a facility, for the facility to be regional, to have the facility to have teaching duty cycles as well as research duty cycles. Even like in the Munich case, I mean, in the Munich case, I mean, they can configure the machine that it even has clinical duty cycles. So it could actually, it could make billable hours and sustain itself in that way. The other school of thought is that politicians will say, okay, well, we're giving you your compact light sources. That's enough. You got it. Don't come back.
It's a discussion that must continue, Lawrence. Our speaker is here, so
okay,
you can take it away.
Is that, let's see, is that Professor Puig? Dr. Puig? Is he here? You ready to go? So let me start the introduction just in case.
Sí.
Okay, so our next.
Muy buenas tardes.
Our next speaker is.
Señoras y señores.
Go ahead.
Distinguidos miembros de la comunidad científica. Vivimos una época de grandes retos para nuestra región y para el mundo entero. Nos acosan la guerra la pobreza, el hambre, extendidas migraciones. El ser humano ha desarrollado su capacidad para entender la naturaleza, pero también, desgraciadamente, ha desarrollado la capacidad de destruirla, literalmente hablando. Las amenazas son exacerbadas por un fenómeno que podemos calificar como el mayor desafío de la humanidad de nuestro tiempo: el cambio climático. El cambio climático no solamente amenaza las formas de vida que hemos alcanzado, sino que también constituye en sí mismo un llamado urgente a repensar el papel de la ciencia y la investigación científica en la construcción de un futuro sostenible para la humanidad. Hace 2 siglos, el libertador Simón Bolívar hizo una afirmación que siempre hemos vinculado a la política, pero que hoy, mirando lo que ha sido el desarrollo de la humanidad, podemos usar con relación a cualquier área de la vida. Y es que el talento sin probidad es un azote. Nuestro talento científico debe estar acompañado de un compromiso ético hacia la protección de la humanidad, de la vida y hacia el cuidado del medio ambiente. No está de más decir aquí lo repetido hasta el cansancio en muchos otros escenarios. El cambio climático representa uno de los mayores desafíos científicos de nuestro tiempo. Ante las situaciones creadas por el uso desmedido de los combustibles fósiles, la deforestación y la explotación intensiva e insostenible de los recursos naturales, que ignora los límites ecológicos y compromete el equilibrio de la naturaleza. Ya lo advirtió en su tiempo José Martí al señalar que el mundo sangra sin cesar de los crímenes que en él se cometen contra la naturaleza. Esa sangre corre por la voracidad humana en la actividad económica que genera escasez de agua y su privatización, que destruye la biodiversidad, que abusa del uso de productos químicos en la agricultura, que alteran los alimentos y degradan la calidad de los suelos hasta hacerlos inutilizables. La ciencia, expresada por los integrantes de una comunidad científica con compromiso ético, nos ha permitido desentrañar las causas profundas de esta crisis climática global y nos permitirá, por tanto, desarrollar soluciones innovadoras para proteger la vida en el planeta. Dijo Martí, y lo cito de nuevo, que la mejor manera de decir es hacer. Y este momento exige que nuestras investigaciones científicas se traduzcan en acción, en este caso, en acción climática. América Latina y el Caribe enfrentan retos particulares. Somos una región rica en biodiversidad, con extensos bosques, altas montañas, ríos caudalosos y una gran biodiversidad. Pero también vivimos en una región extremadamente vulnerable a los efectos del cambio climático. En el trópico enfrentamos huracanes cada vez más frecuentes e impredecibles y cada vez más destructivos. A lo largo y a lo ancho del continente debemos atravesar sequías prolongadas y olas de calor. En todos nuestros territorios observamos la pérdida o la degradación de ecosistemas vitales para incontables especies endémicas. Es esencial que nuestras investigaciones científicas consideren cada vez más esta perspectiva regional única para ofrecer soluciones adaptadas a nuestras capacidades y a nuestras necesidades. La construcción de conocimientos científicos sobre el cambio climático no es solo una tarea de los científicos, sino de toda la sociedad. La tecnología puede llegar a revolucionar la forma en que investigamos las causas y proponemos soluciones a los problemas. En nuestra región, donde la biodiversidad es inmensa, pero los recursos para la investigación son limitados, entiendo que la creación de un sincrotrón representa una oportunidad histórica. Como bien ustedes saben, un sincrotrón es mucho más que un acelerador de partículas. Es una herramienta que puede transformar nuestra capacidad de investigar y proponer soluciones concretas al cambio climático, pues se trata de un instrumento que permitiría, por un lado, analizar materiales y compuestos para desarrollar fuentes de energía limpia, lo que apuntalará la soberanía de las naciones, un área vital para la economía de cualquier país. También permitirá estudiar los impactos de gases y materiales contaminantes en nuestros ecosistemas, ayudando, por tanto, a reducir el impacto de las actividades económicas en la biodiversidad y protegiendo, por consiguiente, la vida de miles de especies que, con su sola existencia y presencia en nuestros entornos, protegen o mejoran la vida, la calidad de vida de nuestras sociedades. Contar con un sincrotrón permitirá desarrollar investigaciones científicas tan específicas y precisas como, por ejemplo, estudiar los efectos del cambio climático en los sistemas biológicos, como los cambios en la fotosíntesis de las plantas, el metabolismo de los organismos marinos o las adaptaciones de las especies a temperaturas extremas. Y aquí quisiera reflexionar sobre lo valioso que sería para nuestro país, para los países del Caribe y para todos los países de la región en sentido general, el hecho de que nuestros científicos puedan identificar conexiones naturales críticas como, por ejemplo, el impacto del aumento de la temperatura en la acidificación de los océanos o la pérdida de biodiversidad. Porque desentrañar estos procesos nos proporcionará una información clave para que podamos desarrollar estrategias efectivas de mitigación y de adaptación al cambio climático, para que entonces busquemos y hallemos soluciones tecnológicas basadas en el entendimiento profundo de la naturaleza. Además, podemos impulsar una mayor colaboración internacional en ciencias, lo que nos permitirá que América Latina y el Caribe reduzcamos la brecha tecnológica actual y contribuyamos a lograr un desarrollo económico y social más sostenible para la región y para el mundo. Porque en el mundo de hoy, específicamente ante las causas y consecuencias del cambio climático, ninguna región del planeta puede trabajar de manera aislada. Por tanto, un sincrotrón regional será también un símbolo de colaboración entre países. El sincrotrón será también, desde esta perspectiva, un motor para alcanzar los objetivos de desarrollo sostenible. Desde energía asequible y no contaminante hasta acción por el clima, este proyecto podría ser un ejemplo de cómo la ciencia y la tecnología pueden promover un desarrollo que sea socialmente justo, ambientalmente sostenible y económicamente viable. En conclusión, el cambio climático nos desafía a actuar con urgencia y a pensar con ambición. Nuestra región tiene el talento y los recursos para liderar la investigación y la acción climática. Y, al terminar, me permito citar de nuevo a José Martí para recordar con él que hacer es la mejor manera de prever. Que este llamado inspire nuestra voluntad de construir un futuro mejor para América Latina y el Caribe, porque, como dijo, y lo cito de nuevo, el libertador Simón Bolívar, la unión debe salvarnos. Es hora de que América Latina y el Caribe se unan en torno a este objetivo común. Muchas gracias.
Thank you for a very inspiring talk. Leo, did you have a question for the speaker?
More than a question, I want... no, hablaré en español y luego traduzco al inglés. Quiero agradecerle mucho al doctor Quid este discurso que tiene un valor especial por el cargo que él tiene, porque realmente en este momento la meta que tenemos en el Caribe, tanto nosotros con nuestro proyecto, como los colegas puertorriqueños con el proyecto Pulse, es de tener una respuesta política a estas exigencias. Y no nos escapa que lo que usted ha dicho es una cosa que reconoce la importancia que puede tener para la República Dominicana una estructura de esta naturaleza, pero también puede representar una manera por la cual la República Dominicana, que ha hecho grandes progresos científicos en los últimos 20 años, pueda tener un papel de liderazgo. En esta reunión, en esta conferencia, ha habido dos importantes presentaciones, una de la doctora Sid, que trabaja con usted, y otra del doctor Álvarez, Moisés Álvarez, que también tiene algún nexo con usted, pero hablaba de otras cosas. Hablaba de temas de herencia cultural, patrimonio cultural. Entonces, esperamos, doctor Puig, que podamos seguir hablando con usted en contacto para ver cómo se pueda concretar esta, no digo compromiso suyo en el sentido de tomar un compromiso, sino compromiso como reconocer que esto es algo que requiere compromiso por parte de todos. De nuevo, muchísimas gracias, doctor Puig. Y in summary, I thank Dr. Puig for this contribution, and I think that this is really first step which may make important the support from Dominican Republic to our project. We were hoping yesterday to have the participation of the Ministry of Science and Technology that for some reason was unable to participate, last moment commitment, but I would say that this presentation, Dr. Puig, compensate us very much for the further day we had to wait.
Thank you, Leo. Is there any other questions for the speaker?
So, Lawrence, the only thing I would ask, especially for those of us who don't speak Spanish, is if someone could very briefly just tell us the essence of the presentation. I know we will post it, and it will be shared with everybody, the English version, but so that we can follow.
Maybe Leo's better than that. I can tell you what I got out of it. But maybe Leo's better, or Victor, or my Spanish skills are. I think essentially it was the world has a lot of problems, climate change, and
Hold on, Lawrence. Leo, you're muted.
Leo, you're muted. Go ahead. Leo, unmute yourself.
Oh,
Go ahead.
I'm sorry. I hope that when I spoke, it was possible to listen to me.
No. Let's say, just repeat yourself really quickly, and we'll move on to the next speaker.
Okay. Let's go to the next speaker as it is, because I think that first of all, my comment was understood or not?
We didn't hear it at all.
Eh?
We did not hear it.
You did not hear. So it's a pity. So if you want me, well, at this moment, okay, it has gone.
Okay. Our next speaker is Juan Sanz, who's going to talk to us about material science with strontium iron.
Lawrence, are you sure that it's me? It's not Juliana Culanti?
Oh, wait,
we have moved her talk.
That's right, we moved. Sorry. Hold on.
Yeah, it's Juliana.
Juliana, yes.
Yes.
Okay, but I'm present in case of.
Thank you, Juan.
Sorry.
Gracias, Juan.
Giuliani, are you here?
Yes,
Yes,
she's here.
Okay.
Can
right.
you hear me?
Yes, from Electra.
Yes. Okay. Just a second. Can you see my screen?
Not as of, it's coming. Yes, go ahead. Yep, there you are.
Okay. So, good afternoon. So, and thanks to Galileo for this invitation. So, I will talk today about X-ray absorption spectroscopy at synchrotron, and I will do some, I will present the technique, and I will present some example in order to highlight the societal benefits of this technique as synchrotron. So what is X-ray absorption spectroscopy? X-ray absorption spectroscopy measures the absorption coefficient as a function of energy. Wait a second, I do the laser, yeah. Okay, so if we have a sample, and then we can measure the intensity before and after the sample, then the absorption coefficient is given by the Lambert's law. In condensed matter, the absorption coefficient looks like this. So it has two main features. The first one is this strong discontinuity here, which corresponds to the photoelectric absorption. And then this discontinuity is a signature of the element because it's an energy that depends on the element. And then there is this oscillatory behavior here, which depends on the scattering of the photoelectron by its environment. And these oscillations are due to the interference between outgoing and backscattered wave. So we can distinguish two regions. The Xanes region, which is the region that I have highlighted here, and it's where we can get information about the local size symmetry, charge state, orbital occupancy, and the EXAS region, from which we can get information about the local structure, such as bond distance, number, and type of neighbors. So this is what we measure at the beamline. So this is what it comes out of the beamline. But we are interested only in this oscillatory part, which can be described by this function. You see, it's a sum of sinusoidal function, and this function contains all the information that we can get from the technique. So the distance to the neighboring atoms, the coordination number, and the disorder from the neighboring distance. Very important. I went to the last slide, sorry. Excuse me. Okay, so very important is the Xanes, which is this part here, and the Xanes has also this pre-peak when present. So from the Xanes doesn't have a easy formula, but it's much easier to measure because the signal is much larger than this part here, and we can get information on the redox of the metal. So you see, this is a series of manganese oxide. So the discontinuity is more or less at the same place, but there are some differences. So we can, evaluating these differences, we can have information about the redox of manganese in this case, or we can have information about the local geometry. Here you see two compounds where titanium is 4+, but when the tetrahedral geometry is present, then we have this strong pre-peak here, which is characterized by this geometry, and the pre-peak is not present when the geometry is different, when you have a centrosymmetry in the structure. And this is something that we can exploit and we can use a lot in the environmental science, for instance, when we deal the problem of chromium contamination. So chromium, you know, it's a metal which is toxic when it's present in hexavalent form. And in hexavalent form, the structure is tetrahedral, and so this presents a strong pre-peak. Whereas when it is in trivalent form, is octahedral, and then the pre-peak is not present. So this pre-peak is really a signature and something that we can exploit if we want to evaluate in water or in soil or whatever the presence of this toxic compound. And then finally, we can have information about the electronic states occupancy. So to summarize, and then I will pass to examples. This is a technique which is as an element selectivity. We can have information on the local structure, electronic structure. So you can see here where when we can use it. And very important, I just want to highlight that with this technique, any kind of sample can be studied, and the information has the same accuracy. It doesn't matter of the aggregation state of the sample. It can be a solid, can be a liquid, can be a gas, whatever you have. And this is a great advantage from this technique. So in synchrotrons, the Nexus beamline is a workhorse, and it's relatively an easy instrument with respect to other beamlines in synchrotron. So this is in a very simplified way, of course. The core is this object here, which we call monochromator. It's like it's a system that transforms polychromatic beam into monochromatic beam. And then, of course, we must have detectors, so we have to count the photons. So we count the photons before and after the samples, and in that case, the absorption coefficient is the log of I0 over I1. But more and more, we experience the need to measure in another geometry, so exploiting the secondary effect of the photoelectric absorption, and we measure in fluorescence mode. In that case, the absorption coefficient is proportional to the IF over I0, and this it's needed whenever we don't have ideal samples to measure. So whenever the sample is too dilute, or whenever the sample is too bulky, and whenever we have a sample which is natural, in which we don't have transmission. So nowadays, fluorescence mode is very much used. So I said that excess beamlines at synchrotrons are workhorse, and I want to show some statistics of the XAS beamline at Elettra. So the XAS beamline at Elettra is one of the most requested beamline in this Italian synchrotron. You see here the number of proposals in the last 10 years. We have more than 50 or 60 proposals per semester. And this is a lot, because we can allocate in normal condition about 15. So there is a higher over-subscription ratio, and so sometimes it's frustrating because we have to reject very good proposal. And also the outcome in terms of publication is very good. So you see that we publish more or less one paper per week, and if you see, the quality also of the publication is going up with the year. So it's really an instrument in which you should have in a synchrotron. I think it's very important to have it. And I want to say also that nowadays there are instruments which are good at the laboratory level, but still they are not at the level of an Nexus beamline that you can have in a synchrotron. Why it's important also to have an Nexus beamline in a synchrotron is because you can target a lot of application in many fields, from environmental science, cultural heritage, medicine, materials. You can do also operando measurements, in situ measurement. You can have bulky environment around your sample. And I want to show some examples of the different fields that I have highlighted here. So first of all is work that we have done some time ago in the XAS beamline, and I'm very passionate about this story of chromium-6. So this is, in this case, the samples were soil near Brescia, which is a city close to Milano, that was contaminated with hexavalent chromium. And so the idea was to use milk serum, which is an electron donor, to try to reduce the chromium 6+ to chromium 3+. So this is in red, you see the data, the hexanes, you see this strong pre-peak, so it's clear that the chromium 6+ was present, if you remember what I said before. So the first three samples, so A, B, and C, they present almost 70% of hexavalent chromium, and D, E, and F are treated samples. So you see that the percentage of chromium 6 decreases to about 50%, which is a good result, but still not enough to cope with the Italian legislation, for which this amount is still too high. So you see that how hexas can be, hexanes in this case, can be used for this topic. Another example, also in the field of environmental science, a little bit mixed up with material science, is presented in this work. In this case, the samples are water. These are contaminated water in uranium mining industry. So this wastewater contains a lot of toxic compounds like arsenate, selenate, and molybdate that, however, can be, let's say, neutralized because they can complexate with a mineral which is called hydrotalcite. Yet, this complexation mechanism is not clear. So we have used hexas in this case, you see these long oscillations, to see, to understand the mechanism. And the mechanism was that these compounds were forming outer sphere-like complexes, and they were surface bound instead of intercalated in the mineral. Again, on environmental science, and again on water. Here we have water contaminated with arsenic 3+, and this is really a global problem, the contamination of water with arsenic. So the idea here is to try to find a way to decontaminate the water. In which way? By copying the nature. Because in nature there is this tuellite, which is a mineral that behaves like a sponge for arsenic. So it contains arsenic 3+, ferric iron. So in that case, what the collaborators here from, this is a collaboration with an Indian group, what we have done is that we have tried to use zinc sulfide nanorods, so nanoparticles, to behave like nucleation centers for tuellite. So we try to use these nanomaterials to boost the mineralization of arsenic 3+. And so this system works, of course, in a laboratory scale for the moment. And these materials that we have created, that they have absorbed the arsenic 3+, we were measured using X-ray diffraction to see that the structure was okay, and we were also measured using hexanes, and we have seen that the hexanes shows that the arsenic is 3+, so confirming that these were behaving like sponges also at the laboratory. I change a little bit topic and I go on material science. So here we have studied this copper, zinc, tin sulfide, tin film solar cells. So these are very complex materials because these are quaternary materials, so they are very much prone to form secondary phases. And these secondary phases might ruin their efficiency. So it's very important to, and the formation of these secondary phases depends a lot on the precursors. So it's very important to analyze using xanes at the sulfur KH, which is the lightest element we can measure at X-axis beamline in Electra. So we have seen that using these precursors, then we have a formation of zinc sulfide as a secondary phase, which really block the absorption of the solar cell. In case we use different precursor in a stoichiometric way, then we have the formation of a different secondary phase, which is a ternary phase in a less quantity, but still this doesn't block the absorption of the solar cell, but let's say boost the electron recombination. So in both ways, this formation of the secondary phases spoil, let's say like this, the efficiency of the device. So other topics, there are a lot of studies in catalysis done with X-ray absorption spectroscopy. This is one of the most common topic that we have at the beamlines. So here we have, the topic is also very important. We have heard a lot of climate change. So in this case, the idea is to do a valorization of CO2, and in particular, do a hydrogenation of CO2 to form very valuable chemicals such as methane. To do that, you need to use a catalyst. In this case, the catalyst was ruthenium on titanium oxide, and the different catalysts were doped with silicon. Why? Because if you dope with silicon, then you enhance or you change the presence of the oxygen vacancies, which are very important for the CO2 reduction, so the CO2 valorization. And so here we have done the measurements as a function of the reaction. So you really do the reaction in the laboratory at the beamline. And so you can see how changing the silicon doping, you can change the vacancy, the vacancy formation that you can evaluate from this peak A2 here, this blue peak. This is in situ. We can go even further. We have seen before the presentation on batteries. We also do a lot of batteries at X-axis beamline in Electra. I just want to show this example because this is a battery which is a solid state battery, and the cathode was copper sulfide. Copper sulfide in solid state batteries has a conversion mechanism. So it's not the usual intercalation mechanism that we have in our batteries of cell phones, etc. So in the conversion batteries, you have really a change of phase of the electrode. This is a problem in some respect because there is a big change of volume, which is something that we do not want in a battery. But on the other side, the conversion mechanism based batteries have very high energy density.
You have 5 minutes.
Okay. So here what we have done these measurements during the cycle, during charge and discharge in operando at copper KH. And of course, when you do this kind of studies, you produce a huge amount of data. So you cannot afford to analyze the data one by one, but you have to use set other methods. So we use a chemometric approach. So we have seen that there are two phases, and you see the evolution of the two phases are correlated with the electrochemical curve. This is nowadays we do something like this in a very standard way. We have also students doing this kind of measurement. So it's very well established topic at the X-axis beamline in Electra. So a change topic. This is not a study that we have done in Electra, but it's a kind of milestone of using xanes in cultural heritage. So here the sample is completely different. Here is the wood of the Vasa warship. So, you know, it's a warship that sunk in 1628 and then was raised in 1961 and then put on display in 1990. So they built a museum around this ship. The problem is that the wood of the Vasa start having problems. So there were crusty patches of salt, softening of the wood. And then this is an ideal case in which xanes can be useful because, of course, the wood has a very poor crystallinity. So it was very important to use xanes to evaluate that first there is sulfur in every depth. So sulfur ready to be oxidized. There is also sulfate, so already oxidized, but there are also intermediate oxidation state of sulfur, indicating a continuous oxidation through the ship. So this is I like this example very much in the field of cultural heritage. So other things, I said so far I was presenting very complex samples. We can study also very easy samples. In this case, we have studied iron, but you can use also very extreme conditions. So we have studied iron at extreme condition of temperature and pressure using diamond anvil cells. So you have to have, in this case, a very focused beam. So we have increased the temperature and the pressure, and we have put our points in the phase diagram of iron. This is maybe as a fundamental impact, but it's also very important to understand the geophysics and geochemistry of the core of our planet. And last, this is my last example. There is also works that we have done and that can be done ex-sus beamline on other in the field of medicine and life science. Here we have studied a copper complex, which can be used as a cytotoxic activity along many tumor lines. So, and the idea here is to try to correlate the activity of this material, the cytotoxic activity, with the environment of the copper. So the activity of the material critically depends on how the copper is bond with the organic ligand around. So this is also another application that is becoming more and more frequent at the beamlines doing X-ray absorption spectroscopy. So this was almost my last slide. So I summarize here. So X-ray absorption spectroscopy is an X-ray technique allowing the local and electronic structural characterization of practically any kind of materials. It is beneficial for many disciplines and for a large community, scientific community. Is a must-have in a synchrotron, and of course is still very much a technique very much linked to synchrotron sources. And with this I thank you. This is an aerial view of Elettra in Fermi and on the beautiful Trieste Gulf. Thank you very much.
Thank you. Any questions for the speaker? I have just a quick question. When the work that you did on the ship, how did you get the sample? I mean, I guess you have to shave off a piece of the ship and
Okay, so this is not a work that has been done in Elettra. This is a work that I wanted to show as an example for cultural heritage. But I know the person, one of the author of the paper, and yes, they could take some of the sample. In cultural heritage, this is very critical because people don't want. But this was, I mean, it's a huge wood,
Right,
so they could take a piece of wood, and they took the wood at different depth.
Gotcha. Okay.
But in cultural heritage, this is really a critical point.
Yeah, the sample handling is fascinating.
Yes, and the beauty of the synchrotron and the beauty of this technique is that this is not destructive. So it's not like ICP-MS, for instance, in which you have to take you can really take the piece and put in the synchrotron. Of course, when you have big tables, for example, big pictures, no, this you cannot do. But for pieces or like coins, also you don't have to take. It's not a destructive technique, so it's very useful. Yeah.
Okay, well, let's thank the speaker.
Thank you.
And let's move on to the next speaker, which is Juan Angel Sanz.
Is it here?
Yep, who's here? Who's going to talk to us about material science and strontium iron iridium oxide. I'm sure that has a mineralogical name or not?
Sorry? No, it has not a mineral name. Sorry.
Okay. All right.
It's so complicated. It's called FIO.
FIO. Okay.
Yeah.
And a key thing that I'm seeing in your bio is how you're going to talk to us about how multiple techniques can tell a complete story. So please go ahead and take it away.
Yeah. Thank you very much, Lore, for the nice introduction. First of all, I would like to thank, you can see the presentation. It's okay?
Yes, it is.
Yes.
Okay, thank you. Well, first of all, I would like to thank the organizing committee for giving me the opportunity to present this work. As Lauren mentioned, what I'm going to present is how to address a material science problem from several synchrotron radiation technique point of view. So first of all, I will introduce the high pressure techniques and why the string conditions are compatible with the synchrotron radiation. Dr. Aquilanti showed us just before me that it was a nice preliminary study of how the high pressure can be addressed with the synchrotron radiation. And I will talk about this material, this double perovskite, and why it was there was some controversy in the structure of this material and how we address it with the synchrotron radiation. For this, we studied this material. We studied the structure of this material at ambient conditions, and we tried to solve the scientific controversy about the structure at ambient condition that were in the literature. For this, we need to apply high pressure as well in order to distinguish which are which is the structure that we can find at ambient conditions. And we also use helium as pressure transmitting media, and we observe some changes in the behavior of this material in the presence of helium. And I finally conclude with the conclusions. Well, the high pressure is a valuable tool because we can modify the interatomic distances between the atoms, we can increase the interaction among them, and we can observe, we can change, so we can tune the properties of this material. If we check, if we focus on the most used instrument for applying pressure is the diamond anvil cell, where we can see that there is a metallic gasket and with a hole, and in the hole we put a sample and a calibrant in the middle of two diamonds that are face one to each other. So we fill this hole with an hydrostatic medium, and the good thing is that it's completely compatible with the synchrotron radiation. So because it's quite transparent to the X-ray, infrared, and UV, the diamonds are quite transparent, of course, at a high energy, and we can perform several techniques in the sample. We can measure the absorption spectroscopy, source synchrotron most power source, X-ray diffraction, X-ray fluorescence, as we saw in the previous talk. But why to study this material, a perovskite? The perovskite is this kind of a structure. We have two cation positions, and the perovskite is quite interesting because it's present. This structure is present in the inner Earth, in the inner part of the Earth. It's also a study because it can form a solar cell. It has a photovoltaic response, and also has multiferroic. In some of the perovskite, we can find ferromagnetism, ferroelectricity, ferroelasticity, and both combination of these materials. So it's from the technological point of view, it's quite interesting. But this perovskite can be formed with several elements with completely different structure. The fundamental structure is the cubic phase, but with a slight distortion, we can have tetragonal, orthorhombic, even the clinic, that is the most asymmetric structure that we can find. So if in which structure is growing, synthesize the material depends on the size of the cations that are forming. In this case, the difference between the double perovskites and the perovskites is that instead of having only one atom, only one element in the B side position, we have two. So we have double instead of ABX3, we have A2 B prime X6. In the particular case of this material, the strontium, iron, iridium, oxygen, there were in structural controversy in the literature. And the experimental study that we could find in the bibliography, we could find that with X-ray diffraction, there was some cases, some papers where they were saying that it was forming this material in this monoclinic or in the triclinic structure. However, in another one, there was this structural phase that was with another group that it was showing that the X-ray diffraction, they obtain a good analysis, a good refinement with this structural space group, structural space group. As well in this one, but in this one there was they were proposing that it was the triclinic structure, and again another paper with this monoclinic structure. Regarding the theoretical studies, we observe as well that some papers saying that the triclinic is the more likely structure, but they have similar enthalpy energy with the monoclinic. It means that it was not clear at all, even if this group was saying that it was the triclinic structure. For this, we try to answer this structural controversy. For this, we measured high-resolution X-ray diffraction in our samples, in our sample of this material in ALBA, and we could index the structure to different phases. For the monoclinic P21/M, we obtain this M20 figure of merit. As high is the value it is better. For the monoclinic I2/M, we obtain this value. This means that it's more likely to be in this structure. However, for the T-clinic, we have that this is the most probable structure. However, performing the rival refinement with the three of these phases, we observe that we have for the monoclinic similar quality factors for the rival refinement. So it was not conclusive at all. For this, we perform high pressure X-ray diffraction measurements at the ESRF in the beamline ID15B. And we observed the evolution of the X-ray diffraction patterns with pressure. So the first thing that we could observe is that there were in some black peaks, we could see that there was a splitting of the peak when we increased the pressure. This smooth variation of the with a smooth variation of the diffraction pattern. So when we try to fit the X-ray diffraction pattern, experimental X-ray diffraction pattern with the monoclinic phases above 6 GPa, where the splitting appears evidently, there were no possibility to fit the experimental pattern with this structure. For this, we need to have a first-order phase transition or the coexistence of two different phases. This first-order transition was not verified by theoretical calculation. For this, we use a triclinic structure, and we could observe that we could fit all the diffraction patterns with a smooth variation of the equation of state. Here we have the experimental results. This is the fit of the equation of state, and the solid line is the theoretical calculation. We can see that the Bull modulus, the compressibility of the material obtained by theoretical calculation, is a good agreement with the value obtained by the experimental data. As well, this is the lattice parameter and the evolution of the lattice parameter and the angle. And we could see that the angles of the T-clinic structure is quite close to the 90 degrees. That's why we have all these problems in the literature to identify this material. At the end, we could propose this structure, and we could uploaded present this structure to the Cambridge crystallographic database. We perform as well the X-ray absorption spectroscopy, where Dr. Aquilanti made a nice presentation of the basics of this, the fundamentals of this technique. We perform these measurements on diamond, United Kingdom, at the I-18 beamline, and the first that we measure is the shinies, because we wanted to see the inner transition in this material. The main peak, that is called the white line, is due to the 2p to 5d orbital transition. That in the case of the iridium, we can see that the 5D transition, they are separated into two levels of energy, the T2G and the EG, that is doubly degenerate and triple degenerate. And these orbitals, these levels are as well separated by the speed-to-orbit coupling. If we perform a second derivative of the white line, we could see that the bimodal character, and we could obtain the evolution of the crystal feeder splitting with the pressure. As well, if we measure not only the L3H, but the L3H and the L2H from an equation, we can obtain the evolution of the spin-orbit coupling between these orbital states with pressure. We perform as well exhausts. Here we have the exhaust oscillation that we saw before in a nice result, and we could obtain the average iridium oxygen distance, interatomic distance, that correlates quite well with the values that we observe experimentally with the X-ray diffraction and even theoretically with ab initio calculations. Okay, the pure material is completely characterized. So then we measure this, we put as a pressure transmitting media, we put helium. We observe that there is a smooth variation as well of the diffraction peak. We observe exactly the same, you can see here exactly the same splitting of the black peaks. And we could perform a quasi-Rydberg refinement. And when we compare our results with the results obtained for the pure material, we could see that below 6 GPa, we observe exactly the same behavior, but above 6 GPa, there was a volume jump at this critical pressure that we could fit with an equation of state. And if we compare the results of our material with the non-penetrating pressure transmitting media, and with our results below 6 GPa, we obtain that they are quite similar. The pull modulus is in the order of the result. However, above 6 GPa, the result is the pull modulus is lower. But this is strange because the material becomes harder with pressure. So we analyzed as well the lattice parameters, and we could slightly see some changes, but there were so large uncertainty that we were forced to repeat the experiment. We repeat the experiment, and then we could have better results. We could observe that the jump is not a 6 GPa. We could precise that it was a 5.6 GPa, and we obtained, as you can see, below 5.6 GPa, a similar result to the values of the non-penetrating pressure transmitting media and the experiment before, and above 5.6 GPa, we could obtain the same, probably the same pull modulus than before. Here I have the evolution of the compressibilities of the different lattice parameters, and then what we propose is that the helium was inserted into the crystalline structure of this double perovskite. For this, we perform electron density map from structure factors, and we could see that there was these points. There are electron densities that we could see that they were in the center of the cell and also in the corners. We checked that in the literature, these electron density points was used in the zeolite, in porous material, to determine the position where the gases are hosted in the material. Clear, if we perform a lattice plane of the 2D representation, we could see that the electron density around this position, it has a radius of that gives rise to a volume of 14 angstrom cubic angstrom, and then there is enough room to host helium inside, comparing with the volume of the helium, taking into account its van der Waals radius. However, everything is not perfect, and when we try to simulate this pressure-induced helium trapping by theoretical calculation, we could see that the volume jump that we observed, that it was around 0.25%. It was very small compared with the theoretical, the one reproduced by the theoretical calculation when we put helium in this crystallographic site. It means in the center and in the corners. If we put only the helium in the center, there we reduce the jump, but it still is larger. And we put only in the corners, we reduce a small more the jump, but still cannot reproduce. It means that in our interpretation is that helium is not occupying the 100% of the crystallographic site. Okay, but however, the compressibility is sorry.
Yeah, 4 minutes.
And okay, thank you. So if we compare the compressibility of the theoretical calculation is much lower than the one that we obtain above 5.6 GPa. What is maybe is a good explanation that why we don't have we cannot obtain the same volume jump, and why we consider that the helium is not entering inside the whole material is because there is a lack of clear transfer channels. And just to finish, we have this. We have characterized that the helium is inside because there is no other explanation of the volume jump, and we check if the position of helium was modifying the properties of the material. For this, we perform Mossbauer spectroscopy measurements in ID14 at the SRF, and we could see for the pure structure with pressure transmitting, non-penetrating pressure transmitting media, we could see that the spectra is changing in between 0, 6, and even with a more splitting of the main peak at 14 GPa. This is related to the increase of the quadruple splitting of the around iron. And if we compare with the result with helium, we could see that this is changing the magnetic response of the iron in the different material. If this we consider that this an effect that the helium is reducing the effect of the local environment of the iron oxygen 6 octahedra on this material. So just to finish the conclusions, we have unambiguously identified the ambient conditions and structure by using high pressure. That is, we have characterized the compressibility of this material with thanks to as well to the theoretical calculations. We can see that the helium affects the compressibility of this material above 5.6 GPa, and with the electron density Fourier map, we have identified the potential location for helium within the structure. And we also, that this is a nice result, is that for the first time we has observed that the helium, that is a complete inner element, has modified the magnetic properties of the magnetic characterization of one material. And just to finish, I would like to thank all the collaborators from the SRF, Alba, Diamond, and my collaborators on this project. And thank you all for your attention. I think I did it on time, no?
Yeah, you did. Thank you. Any questions for the speaker? Excuse me. Any questions for the speaker? Let me just ask a quick one because we do have 1 minute. When you go to if you would go to a larger volume gas, so from helium to, I don't know, krypton or something like that, would you think you would be a different state of matter? I mean, a different phase of the subject material?
No, the only thing is that with a larger gas, I'm pretty sure that the gas has not entering the structure. So you will have a completely non-penetrating pressure transmitting medium. It means that it will be like using metal ethanol water that I'm using. We also measure the same material with argon, and in preliminary results, we observed that there was no volume change apparently. We need to check more. But apparently there was not a volume change at any pressure, so it means that the gas is not entering. So it's completely.
Gotcha. Okay, thank you. Let's thank the speaker. Congratulate him on his good work.
Thank you very much.
And our next speaker, excuse me, our next speaker is Savara Artikova, who's going to speak to us about sustainable development in Uzbekistan. She is a particle physicist by training, with a background at the University of Heidelberg and Max Planck Institute for Nuclear Physics, and has since is involved in work. She's the initiator of the Central Asian Synchrotron Light Source Project. Are you here and able to show your screen? Is she here? I don't see her, actually. Yikes. Or was one of the other co-authors supposed to speak? No? And then, all right, let's move on to, so Franklin is here.
Yes, Franklin just joined.
Yep. Hello, Franklin.
Hello, can you hear me?
Yes.
Okay.
Actually, if you could share your screen, we can go directly to your talk.
I was giving up because I did not receive the link until literally.
Just now, yeah, sorry, probably.
So,
just a quick introduction while you bring up your slides. Franklin Carrero Martinez is a Senior Director for Sustainability and Global Development at the U.S. National Academy of Sciences. And if you have your slides ready to go, you can start your talk.
let me see. Can you see my screen?
Yes.
Okay, so thank you very much for the invitation. When Jorge approached me to share this, one of the things that I was very humbled and honored, because I'm not an expert on synchrotron, but I will share my perspective on what I do at the academies and my career, and a few perspective of what I think big projects like this could use in order to be successful. Let me put my career in perspective and why I'm here. So I used to be a professor at the University of Puerto Rico in Mayagüez from 2005 to 2014. I was also a visiting professor at Duke University. I did a mini sabbatical at MIT. Then I switched to a policy role at the Department of State. I was the science attaché at the U.S. Embassy in Mexico City. I worked at the National Science Foundation. Then I went back to the State Department, where I was the acting deputy science advisor to the Secretary of State. And then about 7 years ago, I moved to the National Academy of Sciences. I'm going to present on my personal capacity. This is not, not the opinion of the National Academy of Sciences or any of my previous employers or the affiliations. And as I mentioned, Jorge reached out because I published this article about a month and a half ago in the Journal of Science and Diplomacy. The title is of that paper, it's Science Diplomacy in Latin America and the Caribbean, the convergence of science, policy, and diplomacy to solve global challenges. So I did this in collaboration with Marcela Ojira from the Institute of Climate Change Research in Latin America. They're based now in Panama City. And Carlos Matsumoto, who sits in the Science Ministry in Brazil. In the article, there were a few things that we wanted to highlight. So we know that Latin America is a leading producer of renewable energy, critical minerals that are essential to clean energy technology and other developments. This is strategically important these days because, as you may know, there's blockades and critical minerals and other things, and the region is poised to make a big impact in this area as a strategic supplier of some of these minerals. We also know that the Latin American countries are amongst the least prepared to adopt or adapt cutting-edge technologies, such as a synchrotron. And one of the things that we noted, and also some UN reports have noted, that there's the risk of losing current technological opportunities for low carbon, AI, and a host of other technologies. So I'm very happy that there's a group of individuals that are thinking of how we can reverse that trend. Unfortunately, there's some significant challenges that we note in the region. It's one of the areas or around the globe with the lowest investment rates in science, technology, and innovation. 85% of the total investment, excluding the US and Canada in this calculation that the UN did, 85% is concentrated in Brazil, Mexico, and Argentina. That was a statistics in 2018, the latest that we could find. And we know that those numbers have changed from 2018 to now. That number has gone down. We know also that scientific collaboration across the Americas, intra-Americas, it's also relatively small. So there should be a strategic priority that is articulated not only from the scientific community in countries from the region, but also to other parts of the world. And we argue that science diplomacy could provide a platform for countries across the region to contribute to collective progress within the region. That's one of the main arguments of the paper. But what is the science diplomacy? How do we define it? So we see it as a convergence of science, technology, policy advice, and foreign relations. And the policy advice and the science and technology component includes not only government, but includes also private sector, includes academia, and includes other parts of society that have to converge in order to make this work. I have a diagram that I want to present briefly to show and convey this point. So this is how we see science diplomacy. So this is from a US-centric perspective. So you have the US government with their policy priorities, and you have a foreign government that could be, and we can make this general. So it could be the government of Mexico with the government of Brazil, however you want to slice it. It's just a point to illustrate. So where you have the policy priorities of two governments, that intersection point, that's what we call diplomacy. Similarly, we have the priorities of the scientific community in the US or another country with a third country. That intersection where you have the science priority, where you have that's what we call science collaboration. And then, of course, you have between the scientific community of one country and the scientific community, or the government of that other country, we have an interaction. That interaction goes in a two-way, and sometimes multiple ways, just simplifying the diagram to just convey the concept. So we have scientific advice, lobbying, and advocacy. And of course, we have government establishing priorities for funding and priorities for policy and directions. We saw that big time during COVID, that pretty much everyone aligned themselves and their research to work on issues related to COVID and address the global pandemic. So that interaction happens, but it's also happening in other countries. So now when we have the scientific collaboration, and we know at times that the foreign community and their foreign governments and the US community and the US government, they also need to interact across borders. That's where science diplomacy comes in. So science diplomacy, strictly speaking, is that tiny sliver of space. That's where these two ovals intersect. So where you have the scientific priorities of scientific communities across multiple countries, together with scientific and policy priorities for different governments coming together. So we see diplomacy, or we define diplomacy as a subtle art, and this is where the tension is between science and science diplomacy. It's a subtle art of understanding how others see a problem and persuading them to see as many of those problems in the same way that you see them, in order to craft solutions that will simultaneously advance the interest of you, the others, and all of the ones, or all of the people that, or organizations that may be interested in achieving your aims. So that now defines a rather tricky area in order to navigate things in large projects like Synchrotron for the Caribbean, makes it a very complex challenge. We can further divide science diplomacy, and this hopefully gets to an idea of the kind of actors that I hope you would consider engaging in putting together something like this. This is now zooming into that those two ovals that I showed briefly. You have the U.S. government, foreign government, scientific community in the U.S. and other countries, and the space and science diplomacy. If we divide that in half, you have people, diplomats, that are working in foreign ministries that have an interest in science, that have an interest in advancing collaboration between countries, that have different areas that they have identified where their governments are making investments. Then you have scientists that have an interest in big projects, synchrotrons, telescopes, and other very large-scale facilities that a single country may not be able to put together. So you have those scientists that their research now starts entering into this space of science policy, science diplomacy, and global international collaboration. Those are two very distinct group of experts that have to come together to align priorities, align wills in order to make something like this happen. At the academies, we have a few activities that specialize in this particular area. But the National Academies organization that I worked for at the time was created by an act of Congress in 1863, signed into law by President Lincoln as a private, non-governmental organization. We're not part of the U.S. government, but our role is to advise the government on issues related to science, technology, engineering, and medicine. And we have, of course, an honorary component of the academies where members are elected by their peers for their contributions to advancing research. Every year, we bring around 6,000 top experts in their fields, from whatever they may be, to help us put together advice, workshops, symposia, and other activities to advance science. I bring that because the complex, this graph is about the US. I know it may be more complex or less complex in other countries, but just for the sake of context, when we talk about aligning wills and strategies, we have a representation here of the US federal government, the different offices that may play a role. We have non-governmental organizations like the National Academy of Sciences, think tanks, and others. We have academic institutions, we have foundations and philanthropic organizations, we have private sector, we have state and local governments, and that's why a science diplomacy strategy, I would argue, would be important for you to consider as you engage and move forward in trying to develop this project for the region. A few things that we've noted in the region that I want to call attention to is that most countries in the region do not have a science diplomacy or science, technology, and innovation investments ecosystem. And often countries in the region rely on external consultants who may or may not have adequate understanding of local tradition, politics, and history. So that sometimes becomes a big hindrance in development of big projects. So I would argue that you may need to consider articulating a long-term strategy for the societal benefits. Why do we want to invest in this? There may be imperative for connecting to educational outcomes so that in the future you can articulate the benefits and sustainability of these investments and others that may come after this. We also know that successful diplomacy initiatives require transdisciplinary, intercultural, and inclusive approach. That includes communication of risks, important to communicate risk, and benefits to all members of society. In a region that has deep religious roots, that may include conversations with religious groups, religious organizations, indigenous communities, and others that may be impacted by and benefited from this project. We will also argue that there's a need for a development strategy to demonstrate stability and commitment to attract foreign funding investments, and maybe even the technology transfer necessary to make this a reality. We know that the region has a history of political instability. That makes it maybe challenging for some to see the need and or the opportunity to invest longer term in the development of these kind of activities. I will leave it at that, but be happy to answer any questions, and thank you again for the kind invitation to be here today.
Thank you. Thank you for your contribution. Are there any questions for the speaker?
I'll just ask one. To the state of the economy, and that is then that is connected to science and the role of science in promoting development and empowering people. Which then just comment a little bit more on that for me, so I can understand.
Marvedina, I apologize, but I could not get the early part of your question. You cut it out.
Oh, I'm sorry, Franklin. I was saying it was interesting that your comment on the political instability. I thought I imagined it more as an opportunity. And I would love to hear your thoughts a little bit more on that, because I see the interconnectiveness with the economic problems and so on, that as a root cause of that.
Right. So I always see a challenge both as an opportunity, but as a challenge. It's a matter of how you frame it. And I agree. You can see it as an opportunity, but it requires that framing. It requires you working together with whoever is in power, whoever is going to put the money, the scientists, the community, in order to put that together. For example, those pictures that I put on my presentation were at the time when I was at the University of Puerto Rico. The students went on a strike. I lost my research, and this is why I moved to Washington. And at the time, the university lost a lot of people. People that were bringing money, people that were making an impact. I've seen that in Mexico. I've seen that in other parts of Latin America. So sure, it's a challenge, but it could be an opportunity. It's a matter of how you frame it and how you work with stakeholders to ensure that you have a stable environment that would allow you to have this kind of longer term investments and opportunities for the region.
Just one more quick thing. Someone had said in one of the previous talks that our best opportunity is to go and convince the people, the masses of the people. Don't waste your time too much on policymakers. I would love to hear your thoughts on that.
That I think that it's a good comment, but I think you cannot ignore the context. For these particular issues, local politics is everything. So if you have people that are connected to their politicians and they're able to articulate why this is important, then that's the way to do it. If you go to rural Bolivia and you talk to the indigenous communities, but they have zero connection to the politician, then it may not be the best use of your time. So I think strategically, you may need to choose who do you engage, as I would imagine that you don't want to wait forever to develop and roll out an initiative and a plan. So I would say that you need to maybe read the room and see where the political will is. Go with the low-hanging fruit first, and then once you have that and others see the things moving forward, others hopefully will see the momentum and join.
I have just one quick question, and that is, what tools and relationships does your office have at the national academies in the Caribbean and Latin America that could help the Caribbean Light Source project and organization, the GCLS Lambestad Pulse Project and SMLS?
So we have from technical expertise in the disciplinary parts of the academies that work across disciplines, from a whole Academy of Medicine that could provide expertise and maybe help communicate and justify why this is important, let's say in that space. others in the biological sciences that may be able to articulate how the region could benefit from having this for, let's say, biological research and other uses. So there's that part. There's also on the policy part. This is the division where I sit, the global policy and global policy and affairs division, where we could have, we do have connections with member states. I was at the OAS earlier this morning. After this presentation, I'm going to go again for a meeting. Right now, they're not talking about this. They're talking about AI. So is there a link? How can you make your agenda visible to some of these groups? I'd be happy to facilitate a connection with staff there so that then you can try to figure out how you can position this project in front of the ministers of science from the region. They're all here in Washington today. Yesterday, today, and tomorrow. They leave tomorrow. Most of them leave tomorrow. So that there's awareness of what are the benefits, and there's awareness of what you can do and how countries could benefit, even if the facility is not in their country. But how would someone from another country would benefit from this facility being somewhere in the Caribbean? That's a question that you may need to articulate, and those ministers who may have an input on funding for the facility would probably be interested in learning from.
Okay.
Antoine has his hand up.
Antoine? You're muted? Okay, go ahead.
Can you hear me okay?
Yes.
Yeah, so thanks for a nice talk. There was a report from the National Academy of Sciences on international talents and basically the need to basically, from the US perspective, to increase the participation of the young people into science in the US, but also worldwide. And I was wondering whether there's a relationship with science diplomacy, in a sense. Like, are there like plans drafted at the government level to facilitate these kind of exchanges?
Well, as you may know, the U.S. is going to start a process of government change, leadership change in the White House. So that means that the answer right now, to be honest, is we don't know. We don't know what their priorities may be. So I don't know, honestly, how to answer that question at the moment. Maybe we can talk in March and see where things stand.
Thank you.
Okay, with that, then our next speaker actually is Antoine.
Thank you.
And let's thank the speaker. Yes, congratulate him on his talk, and we'll be in touch with him. We can consider you a teammate. Okay, so Antoine.
Thank you very much.
Yep, Antoine is an optical scientist at the Advanced Light Source at the Lawrence Berkeley Laboratory, specialized in soft X-ray synchrotron radiation. He is the principal investigator of the Dream Beam project, which is a very nice name, and grew up in the French Caribbean and holds a PhD from École Polytechnique in France. Antoine, if you could share your screen and you can start your talk.
Yeah, actually, I'm not quite ready, but I'm going to do my best. So I think this is it. Yeah, I think this. Can you see my screen okay?
Yes.
How does it look?
And you go to presentation mode?
Yeah, I'm going to try. Okay, can you see things okay?
Yes, perfect.
All right, excellent. So yeah, my talk is going to be a bit technical because we do a lot of fun stuff, and eventually I'd like to get you quite hungry about the cool things that we do and that can be done. And we're looking for talents because there is generally some kind of generational shift, and so we are open for collaboration, and I hope to entice you with all of this. So as some of you may know, there's like a new generation of light sources coming up in the world, the so-called fourth generation light source. And the advanced light source is an existing facility that will undergo an upgrade. And I'm going to talk basically about the upgrade and also about the ALS, just a general context. So first things first, the advanced light source is a soft X-ray light source at Berkeley Lab. It used to be a cyclotron, but it has been retrofitted 30 years ago to basically welcome like photon science. And we have about 40 beam lines like helping people do experiments in many fields of physics, chemistry, how to make small microchips and all these things. So a pretty broad spectrum of experiments, and all of them are doing well. But we actually want to go to the next step and get smaller beams and new capabilities. So we're going to get there. So one specificity about the ALS is that it is soft X-ray, which is not very frequent for a synchrotron. And this is good because with X-rays, you can see through materials sometimes, and you can see with high precision. But in our case, actually, our X-rays, they don't go through materials very much. And actually, we are like sensitive to things get absorbed very, very much by matter. And basically, we can get typically the chemistry of material at very high resolution on a very small scale. So this is an example of people looking at how battery charge and discharge, and you can actually see the chemistry happening in real time. And this is actually using coherent techniques that are still pretty slow. Here, the images are taken over like minutes. And the idea of the upgrade is to basically make these measurements typically 1,000 times faster. So what is the upgrade itself? So right now the ALS has so it's a synchrotron. It has a beam running around, but the beam looks a bit like a pancake, like this shape around. And it turned out that there is a fundamental limit in how small a photon beam can be, dictated by the like some physical parameters. And the idea of the upgrade of the light source is to basically get the generation as small as possible so that we can actually create a beam which is fully coherent. And so right now in synchrotron there's a lot of collaboration, but there's also some kind of a hidden competition or who has the brightest beam. And so for now we are doing pretty well, but all our friends are upgrading, and the thing is we want to keep up and basically jack up the coherent flux by a few orders of magnitude to basically provide the best light possible to our users. So what is really a coherent beam, and what can you do with them? And so the idea is to increase the brightness over 100 times and the coherence. And basically, if you think of light as LEDs, basically like things can get blurry, and it's nice to shine light on objects and look how they look like. But now, when you have a laser, you can actually do many more things. You can actually steer the laser. You can change the phase and basically change the shape of the light to enable extremely complex interaction between light and matter. And basically, the upgrade of the atom light source is basically going from a nice pair of LEDs to basically lasers, but not in the visible, but in the X-ray regime, and that opens a full field of experiments. There are other facilities upgrading or which have upgraded, like the atom photon source Max 4 in Sweden or ESRF. The thing is, because they're operating at higher energy, they actually are not fully diffraction limited. Whereas for ALS, we'll be fully diffraction limited, and we can play a lot with the light. So that's going to be very, very fun. So what does the upgrade of the ALS entails? So well, first we need to upgrade the storage ring to something called the diffraction limited storage ring that basically nudges the electron beam in a much like gentler way. And for this, we need to add an accumulator ring and enable on-axis injection. And we also have like gentle magnets that steer the electron beam, called multi-band achromats. So we need to change basically the whole facility. Everything which is inside now is going to be removed and basically replaced by something much better and more performant. The storage energy, the storage ring energy is going to go up slightly for like technical reason, but not by much. So we're still going to be mostly looking in the sub-X-ray regime. And the electron beam is going to be quite small. Like imagine like typically like a beam which has like a thousandth of the size of a hair, and being almost a half a kilometer wide. This is basically how our beam looks like. So you need very high precision to make it happen. And we are currently procuring many of the components of the ALS. And until now, there was a dark time predicted for 2026, but actually we're going through some delay because the pandemic came in and kind of threw a wrench on some of our plans. So now there's some kind of like reassessment and things that we need to fix. So the dark time is now probably going to be pushed to 2027. But we live in a world that we have to deal with that. So not only there will be like a new upgraded ring with like better light, but we also need to build new beamlines that basically take advantage of this coherent beam. So we are upgrading two beamlines, Cosmic and Maestro, that will basically have the latest, most highest performance mirrors and devices. And a little later on, we're going to add two more beamlines with two branches each to basically take advantage again of the light. So the upgrade beamline will focus on imaging and RPS, and the new beamlines will be scattering and imaging roughly, typically in the soft and the tender X-ray regime. And so one of the key aspects is now that the beam is almost perfect, so we need to preserve it. We spend a lot of efforts in making it good, and so we have developed like a set of new technologies to make it happen. And I'm going to talk about all of this in like final details a bit later on. But one thing is to make sure that when the light hits the first mirror, that the mirror doesn't bulge and then basically destroy the quality of the light. So for this, we need to use spherical nitrogen to cool the mirrors to make sure that they don't move. We also put a lot of effort in making sure that we have diagnostic everywhere in the beamline, so that basically not only you can look at the beam, but also try to understand what is going wrong. Another novelty is that we add adaptive optics to our beamlines to basically make sure that if there is any perturbation, which can be static or dynamic, that we can remove them. And we also want to improve the diffraction efficiency of monochromators by developing ultra-low blaze angle gratings. It's actually a repeat, but this is just a diagram of basically all the diagnostics that we're going to have to make sure that we can provide like optimal beam performances to the users of the advanced light source, and developing all the new technologies. So as I mentioned, so we are developing a critical mirror, and the idea is basically if you have a mirror that is cooled with water, the problem is you're going to get deformation on the mirror in the order of tens of nanometer. And we try to find the best design possible, like putting notches and everything. But even like with the best design possible, we couldn't achieve the performance that we needed. So what we do is to use liquid nitrogen to cool the mirror down to 125 Kelvin. So that basically the silicon at this temperature, actually, when you heat it, it doesn't either contract or expand, it just stays still. And we built a prototype for LSU, and actually it's being tested and actually being procured, and the performances are very nice. Another thing is, I was talking about diagnostics and how we're putting them everywhere, but we're also developing new kind of diagnostics. And wavefront sensors are pretty common in optics, like people use them for like telescopes and such. But in X-ray regime, things are quite a bit more difficult because the wavelength is 100 times smaller than in the visible range, so the specs need to be 100 times better. And so you actually need to measure all these small variation. And the issue with wavefront sensor is also in the X-ray regime that you cannot do beam pickup. We don't have beam splitters. So what we do instead is basically put a grating in the system. So it's actually kind of a clever mechanism in the way it works. But the idea is to do a beam pickup from time to time, maybe every like few seconds, to measure the wavefront and be able to correct it. And we did some measurements, of course, at the LS, at the advanced photon source, also playing with adaptive optics to make it work. And we show that basically now we can have reference sensor that are in the beamline staying at all times, because all the reference sensors that have been demonstrated so far, they tend to be the experiment themselves. They tend to be at the end of the beamline, and then if you want to put a sample after it, well, they're kind of out of luck, and therefore this solution was not used until now. But this one is going to be part of the design of ALSU beamlines, and we expect to learn a lot from that. We also, as I mentioned, adding adaptive optics. So these are kind of getting commercially available and ready for for purchase. And so this is typically a picture of a biomorph mirror. So the beam comes from it goes like along the plane of the slide, and then we have piezo here that we can basically actuate with electrodes and shrink, and basically create local deformation, which are like very, very precise. These are some measurements of the deformation that you can get by actuating each of the sensors, and you can go down to like even like 7 nanometer precision in the motion, and therefore being able to correct your beam. The issue with those is actually that they are so precise that everything matters. And the thing is, so these are based on piezoelectric material, which tend to have a creep and hysteresis and drift. And so that's a big issue. So if you want to characterize them, you characterize the influence function of your mirror, and then try to optimize the beam after that. Basically, you end up with a lot of error. And in order to remove this error, it's actually quite difficult to measure the wavefront in general. And so we took an approach using machine learning to basically create a neural network that understands how the adaptive optics behaves. And actually, this thing worked extremely well. We were able to show that we have residual error below like 1 or even 2 nanometer RMS using this technique. And then that actually provides a way to use those adaptive optics with great confidence. And of course, since they are adaptive optics, not only you can use them to correct the beam, but you can also use them to refocus the beam and create the kind of waveform that you want. And of course, well, we went to the photon source and demonstrated that actually it works, not only using piezo, but also on the beamline. And our colleagues at Oregon are now commissioning after the upgrade of the APS, and are playing also with these tools. And not only it's not a gizmo and a nice paper, but it's also something that's going to serve the user. And I'm very confident that that's going to be quite key to make it work, and add capabilities to beamlines where not only you can like send light on the sample, but also like shape the light and do some crazy experiments with those. And so yeah, like we showed that the specs like work really well, and that's pretty neat. So I was talking about. So something also that we're doing that right now is to upgrade all the instrument controls on the beamlines, because typically on the beamline things are very far apart, and if anything moves, then the beam is screwed up.
Yeah, 5 minutes.
Okay, since we have about 20 degrees of freedom per beamline, it's important to basically handle the key to the machine, so that basically we can optimize the beam without the need of an optical scientist, because we have 40 beamlines and maybe 2 or 3 optical scientists, so we don't want them to be on the floor all the time. So I'm just trying to make my life easier, and actually we show that actually it works really, really well, and basically that can be propagated to all the beamlines. These are like some data also from vendors on the optic that we procured from for LSU. You can see that nowadays you can make mirrors which have extremely good specification. I mean, this is a mirror that basically has a height error less than 1 nanometer RMS. So this is pretty crazy, and those are kind of standard these days. They're not cheap for sure, but you can get them and basically get diffraction limited beam. Just to give you a sense, one atom here is a fraction of a nanometer. So basically, these mirrors are about like 200 millimeter, and they're like almost atomically perfect. So it's quite crazy, and to see how the science goes there. We also have place gratings that are also quite amazing on their own aspects, and with great efficiency. And so I'm going to skip a little bit on this, but yeah, there are a lot of opportunities for new coherent imaging techniques because now the beam is going to be fully coherent. So we can try to create interference in the far field to use the phase to get a much better resolution or much better sensitivity so that we can do faster experiments and more precise experiments. And so this is a lot of computational imaging techniques that we also are pushing and that show great promises. So since this talk is about collaboration, so we're in the US and we have a lot of programs for like US residents, typically SUNY, CCI, and CGSR, and so we're always happy to welcome those. The ALS has a bunch of fellowships. So if you have from another university in the world, you can actually apply for this fellowship. So visit the website and find the information. We are happy to collaborate with new places. Also, yeah, we are happy to welcome internships. So if you're interested, please talk to me. And sometimes we organize a workshop that we publish on lightsource.org. So we always welcome people from abroad. But really, right now there's a general change, and we're looking for new talents from everywhere. As I was introduced, I grew up in the Caribbean myself, and I am fully aware that they're like basically raw diamonds everywhere, and basically like providing opportunities to students and researchers who want to learn about X-rays is something which is extremely important. All right, so conclusion, yeah, so LSU is coming, a bit delayed, but we are kind of ready. I mean, we have many of the new beamlines, actually all the equipment on the floor. Now there are some issues with the accelerator, but that's a different problem. And so we'll have faster measurements, so we can not only do new photon science, but we can also do regular science with additional capabilities. And basically, this new generation of light source is also ripe for a new generation of a scientific workforce, and that's something that we really want to prop up and help with. And we need talents from everywhere to basically be able to answer the needs of science. I have many people to acknowledge. I'm going to skip slightly. It's a bit rude, but we have a lot of collaboration because the synchrotron world realm is actually extremely collaborative, contrary to oftentimes academia where people are very competitive. We tend to collaborate with all the people. This is something that I find really fun in that field, and we also collaborate between fields, which is something very neat. And with this, I'm at the end of my talk. So if you have any questions, I'm happy to answer them.
Thank you for your very nice talk. We have time for one question. Well, we can put the questions in the chat, and since we know you, Antoine, we can always contact you by email.
We have a comment in the chat from Ellie. Great work, Antoine.
Thank you.
Was that? Oh, that's my thing. Jesus. Okay. So let's thank the speaker again. And our next speaker is Dr. Adnan Shihab Eldin, who is he's the former Secretary General of the Kuwait Foundation for the Advancement of Science, and is currently teaching business management at the Vienna University of Economics and Business. He's a graduate of UC Berkeley in nuclear engineering, and has received many prestigious awards, and most recently the second Abdullah bin Hamad Al Attaya International Energy Award, Lifetime Achievement for the advancement of the Organization of the Petroleum Exporting Countries. Dr. Eldon, please, you can share your screen and start your talk.
Thank you very much. Thank you. First of all, I apologize. I don't have any presentation, and I mentioned this earlier to Leo. And so this makes it easier for me. And my talk would not really be focused on synchrotrons or light sources. My understanding of light sources goes way back to the 70s when I was working at Berkeley, at the Lawrence Berkeley Laboratory for a few years, when the advanced light source idea was born and developed and deployed by David Shirley. So Antoine kind of brought back memories in his discussion. And thank you, Antoine. What I wanted to cover is what is the state of funding science and technology in the region, in our region, MENA and Arab countries in particular, and how can we find ways to fund interregional collaboration in advanced light sources, synchrotron research, and in general more than so. So to do that, let me just remind everybody that like other developing countries, most of the MENA countries, excluding Israel in particular, but Turkey maybe, Arab countries, if I focus on the Arab countries, budgets for GDP, budgets for research has been meager throughout the last century and the beginning of this century. And for most countries, the budgets continue to be very meager, with few exceptions, mainly in the GCC countries, Gulf Cooperation Council countries. And if you look at the numbers, and again, if excluding Israel, which is more than 5%, and that's why it's leading in science and technology, not just in the region, but globally. And if you look, you know, Egypt's still under 1%, trying to reach 1%, despite its long history. Kuwait, which has lots of potential, has been sort of sitting around 0.3% of GDP, and so on. The only exception is being a couple of the countries in the GCC, like United Arab Emirates, that has recently been reported to have allocated a total of 1.5%. And Saudi Arabia is above 0.5%, approaching 1%. And what does that mean? It means that most of the countries have not yet really completed setting up their science and technology ecosystem. Most of the countries lack an equivalent of a national science foundation to fund research at their universities and research institutions. Most countries in the region lack even a functioning and independent National Academy of Science. Some of them, they have National Academy of Science, but they are just simply departments of the government. And often they follow the appointment of the chiefs, are, you know, usually dictated by political consideration, and they report directly, and their budget is derived from the governments. So that's science and technology in general, and including the research ecosystem in these countries. Now there have been some good progress. Let me just give one good example from Kuwait, where I was involved in the last 10 years before I retired, which is the Kuwait Foundation for the Advancement of Sciences. And actually, it's not a government organization, and that's the beauty of that experiment. It's way back in the 76. The business community of Kuwait decided, because of the oil revenues, they have benefited a lot from the oil revenues. They agreed with the ruler at that time to pledge to contribute 5% of their net revenues, net profits every year, bottom line, to set up a foundation, the Kuwait Foundation, to help support science and technology development in Kuwait, in the region, and also to develop international relations. Unfortunately, that 5% pledge dwindled to 1% right now, so it took away some of its capabilities. The advantage is that although it's a private sector, but they set it up so that it's chaired by a board headed by the head of the state. So that gave it sort of kind of an interesting position within the country. It's not a state something. So I think what I'm trying to, why I put this example, because I think that's one way of trying to strengthen science and technology is to have the private sector, thriving private sector in some countries, especially in GCC, but some other countries, North Africa, Algeria, and also Egypt, perhaps, other than the GCC, but also in the GCC, to try to model that example. So that's one point I wanted to do. Now, there are similar organizations in the GCC. For example, in Saudi Arabia, there is both a research institution, but a funding institution supported by the government called KAXT, King Abdullah Science and Technology City, which goes back like KEFAS to the 70s. And it has a dual role of funding research, acting like NSF, but at the same time it has national laboratories. It has some laboratories, mostly in science and technology. Saudi Arabia has done some very interesting things. They have followed a course whereby they establish endowment for some of their top universities or top research institutions. For example, KAUST, which many of you know, it's King Abdullah University for Science and Technology, which is a graduate university like MIT, modeled after MIT, has an endowment of a few $1 billion, I understand, and it's growing. Similarly, King Abdullah Petroleum Research Center in Riyadh has an endowment. And so this other avenue is to set up an endowment and make it independent and to secure it against the fluctuating up and down, especially given that in the Middle East, there is political instability. And let me here go back to some of the old Arab states like Iraq, Egypt, Syria, that at one point in time, they were leading science and technology in the region. But unfortunately, because of the political development, for example, in the case of Iraq, because of the Iraq-Iran war, the invasion of Kuwait, and then the sanctions after that, has disintegrated. And there is not much of a science and technology development taking place right now. And especially because what's happening, a phenomenon in the Middle East, in the Arab countries in particular, especially big ones, what's happening is that we're seeing them getting fragmented. Iraq is more or less 3 states, and now we see Syria being torn into several states. We don't know exactly what's happening. We see failed states like Libya, like Sudan, and so on. So the picture is not very bright in terms of science and technology and research. At the regional level collaboration, we have very few good examples of regional collaboration. Perhaps Sesame is one good example, bright example. But let's remember, Sesame did not come about because of regional effort. It came about because of inter-regional effort. Initiative from Europe with some countries in the Middle East, particularly CERN and the European Commission. So there aren't many regional projects that have been homegrown from the region itself. I am not very optimistic that this will change because what I'm seeing around in the region is more fragmentation, even beyond Syria now. Probably what will happen in Egypt is a question mark, and so on. So let me not dwell on the politics. Let me turn to a bit more positive question, is that ask the question, all right, we have some regional project. We do have the Sesame. Now we need to strengthen Sesame and similar projects and also ensure they benefit from other regions, like what's happening in Latin America and potentially in Africa, light sources, and Europe and the United States. Where can we get the funding when at the national scene, funding is lacking? And I think here one has to sort of be imaginative. The first thing one needs to look at, are there potential sources within the region? And there are potential sources within the region. these are mainly the development banks. I give you two examples. One of them is the Arab Fund for Science, the Arab Fund for Economic and Social Development, which is headquartered in Kuwait. They do support occasionally regional projects and even international projects, provided, and this is the cue, provided the governing board says so. And who are the governing board for such institution? They are ministers of finance. And so here, the way to get to have the Arab Fund for Social and Economic Development fund scientific project is to talk to the ministers of finance. That means the ministers in charge of science and technology in the region should be talking to the ministers of finance and pressing upon them the importance of giving directives to the management of the fund to fund regional projects. This is possible. This has happened a few times, but it is not the norm. So here is one example. The other example, for example, is the Islamic Bank for Development, headquartered in Jeddah. Again, the same thing happened. You have to sort of talk to the ministers of finance that oversee the Islamic Development Fund. Again, another example is the OPEC Fund, which is headquartered in Vienna, which is beyond the Arab region or MENA region. It includes all exporting countries. But again, it's governed by the Minister of Finance. And that's the key point that I wanted to share about these regional development banks, how they can play a role. Now, beyond that, of course, you all know that beyond the national agencies, your only resource is to go to international. And international, either you go to international organizations. We have good example. The IEA, for example, has potential. And I notice there is an inter-regional project in technical cooperation at the IEA that supports network of light sources. And by the way, I spent 3 years working as a director of technical cooperation at the IAEA. And I can tell you, if the regional grouping within the IEA, like Arasia for the Middle East, in Asia, I think ASEA, if those groupings within the IEA get themselves together, they can get funding from more than one inter-regional project for light sources. I can assure you. But that requires, again, sort of exerting pressure on the organization, on the IEA, through the national representative, whoever they are, and through the regional grouping, because the IEA technical cooperation, where I used to work, is set up according to Asia, Africa, Latin America, and each one of these grouping has a director within the technical cooperation. And they set up within that director, they have national project, they have regional project, and they have inter-regional project. And they all compete for the same pie, same funding. So it requires some kind of lobbying at that level by the national representatives at the regional level and at the international. There are, of course, other sources internationally. European Commission, United States, China, other possibilities. I think one thing I want to sort of bring to your attention, the possibility of getting funding from the international private sector, especially the high-tech companies. Because I think, like Bill Gates is a good example. If you can get his attention to the importance of doing some research, linking up with his foundation, what he's interested in, either in his foundation or personally. And he's interested in a lot of technology. He's putting a lot of contribution into SMRs, into fusion and what have you. And of course, the type of research that's being talked about, and I listened with interest to all of the excellent presentation, I am sure there is an intersection with not just Bill Gates, but Bill Gates and Zuckerberg and all of those people. So I think that's an important source that one should target at the same time. I think my final remark here is related to maybe what is needed from the scientific community itself within our region or within other region. I think they have to try. You see, the supply and demand in developing countries is very weak because it's weak in terms of the infrastructure, the scientific community, and the funding within each country. So you have weak supply, weak demand. While we've listened with interest to, you have no shortage of great ideas for research in light sources, and there is a demand, and then there is supply, and so that's much easier. I think it's much more difficult when you have a weak demand and weak supply and trying to find a match. And that's probably where I want to stop in my remark, because over 40 or 50 years I've been involved in UNESCO, IEA, OPIC, national science at the Kuwait level. I also worked in the US. And I think I have observed that this is probably not just for the Arab region. This is probably one of the difficult things that people have not focused on. That means, I just listened to my colleague Adel, I think from Tunisia, proposing a light source for Tunisia. Excellent idea. But if you have a light source in Tunisia and you have a sesame and you have a weakness in supply and you have weakness in demand, is that the best idea? Or is it better to try to strengthen sesame and put the resources in sesame? I don't have an answer, but I just put this thing and I conclude with it. Thank you very much for listening.
Thank you for your talk. Are there any questions for the speaker?
Lawrence, I make a comment and just thank Adnan. Thank you, and thank you for supporting this project and your advice. The IAEA was introduced to our project, and as you know, they set with the countries these country program frameworks. And so the IAEA is in fact funding the crystallography school that's coming up in Jamaica at our regional X-ray facility for the English-speaking Caribbean, which is a part of this project. So that's a start, and so hopefully for the next period, the islands and the other Latin American countries can have it put into their country program framework. We have to do it like that. If it's not written into the country program framework, then it cannot be funded.
Fully agree with you.
Any other comments for the speaker?
Yeah.
Victor.
Can
you hear me?
Yes, Lawrence, did you see it?
Can you hear me? Can you hear me?
Yes, yes.
Thank you again for your talk. And I would like to know your opinion about the project. This LAMISTAT project, I don't know if you have heard a little about what we are trying to do to build synchrotron in the Greater Caribbean. What's your first opinion about that? I would like to know, what do you think?
Well, as I said in the beginning, I am not an expert in synchrotron or light sources. In fact, I've spent the last 20 or 30 years of my career working on energy, energy transition issues, energy and climate change, and nuclear power, and especially SMRs. So I am not the right person to advise you about the project specifically. But if you ask me, is there a role for such projects to be useful for beyond the region if you set it up? And I would say yes. I would say yes, there is a role, and you could imagine a plan if you can identify, again, Caribbean and Arab region, for example, both of them are short in supply of research, short on demand of research. That makes an excellent idea to try to bring the two together so you can match the supply and demand in a better way. That's how I would look at it. But it's not going to be easy if you really ask my advice. It's not going to be easy.
Giorgio.
Yes, just a comment about Sesame. I don't know whether you've heard it, but I was scientific director there, and I'm now in the SAC committee, Scientific Advisory Committee of Sesame. Yes, it would be great if other countries in the region do join Sesame, because Sesame is now, I don't know whether you were there, you were attending yesterday, there were a couple of presentations on Sesame. Sesame is producing excellent science at the moment, beyond the fact that it is the idea of science for peace and science diplomacy, but apart from that, it's producing excellent science, and it is would be really an extremely good opportunity for the region. So I fully agree with you that it would be great if others, with a modest investment after all, because they don't need to start with the construction and operation, because that is already there. So with a modest, after all, investment, they could join this good example of international cooperation. Just that.
Yeah, I followed Sesame a lot. In fact, Sesame asked, when I was a director at KFAS, Sesame came and asked for support from Kuwait to join actively. Kuwait was only an observer, and it was
I remember that.
and the reason many of these countries were not able to join is that they were not able to overcome their political differences.
I know.
So the question becomes now, is it possible to envisage the political scene changing? I'm not going to discuss why, but you obviously know, because what's going on, the wars and everything. I could say I'm ambivalent about it. There is a possibility, if things settle down in a positive way, despite the destruction and everything else and the killing, what have you, if there is a way out of this that makes it possible for the countries, especially the Abraham Accord countries, to come and say, okay, forget about the wars, forget about the destruction, forget about the killing, let's start new, and there is a goodwill on the part of everybody. I'm going to tell you, this is not the case right now at the people's level. Maybe possible. So I think it depends what Trump does. I think it depends what Trump does. If Trump can take the leadership and clean things out, take out all of this hatred and killings and what have you, and bring people together in a way where everybody is treated equally, instead of, somebody is superior and somebody is less, then I think there's a good example, a good chance, not only for Sesame. Sesame could be the beneficial of something like this, but other projects can also survive.
Leo.
Thank you, Adnan, for your comments. And I think that there were 2 points which are very relevant to what you're saying. One is that about the development banks, because in Latin America, there are several development banks in different forms, for Central America, for the Caribbean. So this is really a possibility. And OPEC fund is not easy for us because, as you well know, only Venezuela is member of OPEC and not of the fund, actually. So that, but certainly, the idea that funds coming from oil may be used for that, may be used also without the OPEC fund. So what is the bottleneck for this? Is that it is important that our project arrives to the politician who determine what to present to the banks and so on. And for this, really, a meeting like this are very important. And the final comment about cooperation, interregional cooperation. You may not know that in Dominican Republic there is a congress held every year, and in that congress we organized for 3 years a symposium on different topics. Symposium from which, to some extent, this project was not born, but certainly had a blessing. And in a couple of them, we really concentrated on the possibility of cooperation between the Caribbean region and the Maghreb region. There was a roundtable on that 2 years ago. There was the participation of our common friend Monif Zubi. So that really this is something which is in our agenda. And it is very important that people like you, on the other hand, support this idea on the Arab side with your relations. Even if you are retired, you have a lot of relations. The fact that you've been watching us for 3 days is very important. Now, what I think you may help us is, to some extent, putting us in contact following this project.
Well, of course, I've been watching, but I'll be very happy to help whatever I can, and I'm certain that there is a possibility. But I go back to what I said. It's that the scientific community in our region have to go to the ministers of finance and convince them. And therefore, you cannot just do it from your side with my contacts directly. I think you have to find an anchor, 1 or 2 major scientific institutions who are participating, and they have to convince their ministers of finance. I think the lead I could give you is that Saudi Arabia is a good potential advocate that you should be in touch with, especially maybe through KAUST or through KAXT, and I'm happy to give you. The second one is Qatar Foundation. I'm sure you heard about it. I don't have to tell you about it. The Emirate, I'm not so sure, but it's approaching midnight now. I have a marathon, 5 kilometers marathon in the morning at 7 o'clock. I have to be ready. And I've been up since 4 o'clock in the morning. So I'm going to have to quit and stop here, if you don't mind. Thank you very much.
Thank you.
For inviting me. Thank you.
Good luck tomorrow.
Much. And I really listened with interest. So many excellent presentations. Thank you very much.
Thank you.
Bye.
Our next, let's go on to our next speaker, and wish Adnan a good luck tomorrow and best of times in the marathon. Our next speaker is Camilo Delgado, who is from the University of Bogota. He is a physicist and professor. I'm just reading the bio here. Cosmologist, and will talk to us about the implementation of the National Research Incubator in Astronomy and Applied Geography as a guide to create the GCLS Lamistad. Camilo, go ahead and share your screen and start your talk.
Okay, thank you so much. I joined this project since I was working at the Ministry of Science and Technology in Colombia. So I remember when I talked with Leo about the project, and there was the possibility, how Colombia could help. But after that, I joined the team of the Geographic Institute of the country. His name is Agustin Codas Geographic Institute. Also, I'm part of the Distrital University, and I'm part of the Academy of Colombia. So I'm astrophysicist. During my master's, I described the X-ray emission from gamma ray bursts.
Excuse me, do you want to put your slides in presentation mode?
Yes. Are you watching the presentation? Let me see.
There you go.
Okay. Now you can see it.
Yes.
Okay, nice. So during my master's, I was working with this. I described the X-ray emission from gamma reports. Remember, the model is you have a fireball, and the X-ray emission came from synchronous radiation from the movement of the electrons there. And after that, during my PhD, I was working in galaxy clusters. So now this idea of this presentation is how to do a research incubator for this project. During this year, I was leading this idea of a research incubator in a national institute. Sometimes you have some research incubators in some groups, research groups in some universities. This is our bachelor's students at the latest stage of his career, or the master's beginning, no? So I'm going to show you, this experience that I had with this research incubator in astronomy and applied geography. And the idea is to motivate the creation of this research incubator group in our project. So this is the abstract now. So there were many projects that the students were involved, related with the Earth observation, geographic information system and technology, socioeconomic and policy, and land, territory, and climate change. Also, they contribute the FOR for the Intercultural School of Geography for life, and conduct multi-purpose analysis of cadastral database. So I beginning to think on that. It was a meeting of the Young Academy of Science with the Senior Academy of Science in Latin America, and the International Science Council were the organizer of this forum. So I was talking about the importance to make a bridge between junior and senior researchers, independent of the field. Because we should promote the research activities in our countries, and being a bridge between senior and junior researchers. For example, we can coordinate research incubators in science institutes and universities and different initiatives. Because one of the problems of the projects, and also this long time initiative, because you're thinking on this project, it's around 30 years from the beginning of the idea to have the device, all the facility. So we need to create a great bridges between the junior and the senior researchers. So the project was to have the general objective. The idea was how to join the research on geography, applied geography, keeping in mind the developing sustainable goals, to give some solutions to the country, in these fields. So we had some strategy lines of research. So at the beginning, we need to build the document of this research incubator. We need to identify the research lines. After that, we need to make a call. In this case, we received 227 postulations from different parts of the country. It was made in Colombia, and we select 25 persons from all of the country. After that, we did some meetings and also some classes related with these topics, because there was different careers involved. And after that, we give them 3 months to develop some projects with the senior researchers. So we had people from different parts of the country, but also from different careers, people from physics, sociology, science policy, cadastral engineering, geography. And the idea was, I mean, this is the profile. I mean, they are really young guys. I mean, they are finishing their bachelor's careers, and they join from different backgrounds, and they could work together, no? From, I mean, they were in different part of the country, so many of the work were virtually, and many of the activities that we did with them. So after, this is all this is the map, no, that shows where I came from, the country. Some people are the north of the country, so you can see was the welcome day. There was some presence activities, people from Bogota, so we had there also virtually, and they received some training in some important concepts for them to do their researches. And after that, they were involved in the projects with the senior researchers. Also, this is the meeting with the people from outside Bogota, and they had, I mean, this is the result of the project that they were involved. No, their ages were 18 to 20 years old, and really they could give some result for some projects that are national projects in by applying different techniques to analyze satellite images, also how could reach to the territory, and also to make some proposals of the how to valorate the land. No? So this is all the research that I did. Also, we need to, in this case, we submit this project to the National Science Foundation in Colombia, is the Ministry of Science and Technology, and we got the recognition of this project. After that, we join all the team of all the students to do a joint analysis of 3 databases of cadastral database, and they could do it to looking for example, some index for poverty, or related with how the urban area is growing up, and this is the products that they did. So the idea of these research incubators is that the students becomes to be more involved in the project. I call it a spectator, no? They just not watching the research, they are doing the research. It's this learning by doing. And also they present the results that they did during 3 months in different places. At the end, we had the graduation for this process for them, and they did also these maps. And we present virtually in some event in Ecuador, and at the end we produce this paper that we're going to submit some specialized journal. And the proposal is to establish the research incubator of this project, coordinated by the capacity building group. The initiative will engage 2 bachelor's or master's students per country to participate in projects led by researchers within the collaboration. So thank you so much for your attention, and this is the idea that I want to show you now.
Thank you for your presentation. Are there any questions for the speaker? I think a good question to ask is really of the community is if we did some type of scientometric analysis just based on research publications, would we be able to identify research projects as exemplified by published papers that already involve bachelor's and master's students at synchrotron light sources? So first we identify the professors, PIs that are publishing papers at Synchrotrones, and then see what was the classification of the students involved in the project.
Yes, because I mean, usually people begins to the research during the PhDs, no? This is that happens. But something that I notice is that after they finish, I mean, if you see some statistics, half of the people are leaving the field after their PhDs.
Right.
So we need to begin to work with the bachelor students. I mean, we need to put them in a real project. Of course, they're not going to do it. They are just to support some part of the project. I mean, but they are on the project. And I think it's very important for them, and also to continuous decrease the gap. I think, I mean, here if you see different institutes around the world, you are going to find this gap between the seniors researchers and the an early career. So it's something that is happening. I mean, I also involved in other science diplomacy projects. I was the co-chair of the junior member of the International Astronomy Union in 3 years. They're the early career stage of the astronomer around the world, because they joined the all professional astronomers around the world. And we found these problems that is happening, I mean, for early career. So I think we need to discuss, I mean, what is the percentage of early career research of this project?
Right. Right.
I just want to say that. I mean, I'm part of the capacity building. So for the reason I said, okay, we can discuss this into the capacity building, marketing. So for the reason I said, okay, we can coordinate maybe 2 persons for each country, also to join the idea, no?
Sure, sure.
I don't know. I mean, you are the senior researcher.
Yeah, we have colleagues that, I mean, I'm thinking of a colleague that's at Manhattan Marymount University, or in New York City. She's an NSLS2 user, but she's at a completely undergraduate institution, and she publishes, you know, as much as anybody, I guess, at a similarly sized institution. All her students are undergraduates, and most of them are women. So she does work on exafs of ocean water. So, I mean, it's possible to involve undergraduates in synchrotron sciences research, for sure.
So
any other? Go ahead.
Yeah, Lawrence. So I can, I mean, I can give you my email. You can write me, or we can put in contact, because it should be. I would like to talk with this person that you are
okay,
talking about.
Sure. Any other questions?
Yeah.
So let's thank the speaker then. Yep. And then is our next speaker here?
Am I the next speaker?
Yes.
Hernandez?
Yes, you are.
All right.
Okay.
We somehow have.
Yeah. Can you share your slides?
Yeah, I'm working on it. This
okay.
is the first time I'm sharing screen. Okay, got it.
Okay,
sorry.
Let me just say that.
I got it. I know the problem. I'm sharing the window rather than the screen. Hold on.
Okay. I'll just say the next speaker is Rigoberto Hernandez, the Gomes Family Professor of Chemistry at Johns Hopkins University, and is going to talk to us about science and collaboration across borders. He was born in Havana, Cuba, and is a U.S. citizen by birthright. He holds a Bachelor of Science in Engineering, in Chemical Engineering, and Mathematics from Princeton, and a PhD in Chemistry from UC Berkeley. So go ahead, you can share your screen and start your talk.
I'm trying to. Is you see my screen or,
I do.
or not?
I see it.
And do you see a laser pointer? Or not? Science and collaboration across borders, is that what you see? Or do you see
yes,
my...
we see the laser pointer.
That's what we see. That's what we see. And we see
okay, cool. Thank you. Yes, it's a little bit complicated to do this because I don't see what you're seeing and I don't see you now. So if you do want to text or say something to me, please just interrupt me. We won't call that interruption. We'll call that an addition. pleasure to meet with you and your team. I feel like I'm among friends. I was been listening to some of the presentations, and clearly you all know each other, and you don't know me. But Jorge and Leo invited me. Not sure why. But we'll see if there are ways in which some of the things that we've learned over the years help you all. So I'm going to talk a bit about science collaboration across borders. Because you don't know me, I thought I might start by saying a little bit about where I am, my positionality, and who I am. I am on the faculty at Johns Hopkins University. If you've never been to Johns Hopkins University, you might not have known that we're about 3 miles north of a very nice inner harbor of Baltimore. And our campus is, like I said, 3 miles or 5 kilometers, depending on which units you prefer most. It's a very manicured, beautiful green campus. We're located about here, which is not far from Washington, D.C., about half an hour by train or 45 or 50 minutes to 50 to 60 minutes by car if it's on 5 a.m. on a Saturday night. But on a normal time, it could be anywhere from an hour and a half to 3 because of traffic. Philadelphia is about an hour away, and New York City is a little bit further away. The American Chemical Society, I'm going to talk a bit about their work as well, and my role in the American Chemical Society has 2 primary homes in the United States, one in Washington, one in Columbus, where they do their publications, and then they have a number of international offices as well. So it's quite global. You may not know, but this is part of why I think Leo and Jorge invited me. I was just elected to the presidential succession of the American Chemical Society. I will be the president-elect in 2026, in 2025, and the president in 2026. It's really exciting to be the president in 2026 because it will be our 150th year. And so, again, I'll tell you a bit about that. And if you want to know more about me, you can even just scan the QR codes. But you probably won't have enough time because I'm getting off the slide. One last bit. The American Chemical Society does publish a lot of, has a number of journals that they publish and many scientific papers. They also do a number of papers that are related to creating community, like the kinds of things that you do. I don't know if you would publish in the American Chemical Society journals, but this is something that you could do. And part of that is looking for amplifying voices, both internationally and diverse. And so as one example, in the Journal of Physical Chemistry C, George Schatz and started to introduce viewpoints, which were meant to provide, this is back in 2015, to cover broad ranges of topics. And so if there was a point of chemistry in your synchrotrons that you're developing, you might consider amplifying that role in something like these viewpoints. Ted Goodson felt that they could be useful in providing voices to underrepresented physical chemists. Bill Jackson, who was one of the founders of NOBICHE, the National Organization of Black Chemists and Chemical Engineers, and was a former department chair at UC Davis, wrote a retrospective on his life in physical chemistry in one of these viewpoints and was simultaneously published in 3 different journals. I was lucky enough to have an article published simultaneously just a few weeks later in the 3 issues of JPhys Chem C called A Cuban Campesino in Chemistry's Academic Court. I will not, no estoy hablando esto en español, I'm not speaking this in Spanish, porque yo sé que muchos de ustedes no saben cómo hablar, no entienden la lengua, because I know that many of you don't know the language. So, but yes, I am Cuban, I do speak Spanish, and if you want to know more about my own trajectory and how I've worked with students and others over the years, both the theoretical chemistry and computational chemistry in a broader context, as well as what I do with diversity equity, you're welcome to take a look at that article. Finally, because I know that most of you see science first and then the systems or the way to do science second, I want to let you know that I am a scientist. I've done quite a bit of work trying to understand non-equilibrium chemical reactions, and this has involved collaborations with, for instance, Tomikiko Matsuzaki in Japan. We've been developing techniques to look at data science and using data science to look at properties of materials. I forgot to add an article that was just accepted and is now available, will be available in 2 days in ASAP. That's the next bit of work there with my students, Nikhil and Maitrey. We've been looking at how we can describe, using non-equilibrium methods, the energetics of proteins as you pull them apart. We've been addressing the complexity of how nanoparticles interact with biological materials and how we might be able to prefabricate those nanoparticles so as to reduce their impact in downstream waste in the environment. And in the context of the synchrotron work that you're all doing, you're looking for structure, and many of the things that we're interested in require structure. We also look at structure in time. So to the extent that you can also do spatial temporal characterization, that would be very exciting and interesting to me. One last area that we've been very active in the last few years has been looking at the development of autonomous computing materials. These would be materials that would be unlike the silicon that we're using in our microchips, that would still enable us to do computing, whether it's data storage or processing. And one reason why we might want to do this in different materials is to try to resolve the fact that Moore's law and Kreider's law will soon be will no longer be applicable because we won't be able to go any smaller. And on the other hand, because maybe we want to make materials that are portable, light, and light as in not very heavy, and therefore which may not require very extensive computing, but which would require at least some kind of portability. And my team has been very, very active in this work in the last 5 years. And so if you're interested in how we've been using, in this case, polymer network nanoparticles, then I encourage you to take a look at some of our work as well. So that's for Prelude. I know that what you really want to know is how to do synchrotron science across borders. What I'm going to answer instead is how I've worked and done my science across borders, across international and global borders. And I'm going to do this through 3 different stories. And hopefully there may be, some of this may be obvious. I apologize, I wasn't quite sure what it is that would or would not be obvious, but I'll share some of my own stories. The first one involves my interaction through Germany with the Humboldt Foundation. I've been very fortunate, and many of you know that you can apply for Humboldt fellowships from all over the world, including the US. And that allowed me to spend a year in 2006, well, more than a year, over 2006, 2008, 12 months spread over 2 years. And equally importantly, to then later recruit Fyodor Lenin research fellows, those are postdocs, Inga Lusoy and Andrei Junginger, and then later do return fellowships. So all to say that I've been able to go back and forth to Germany, taking advantage of funding mechanisms that exist in Germany to do science that I wanted to do in collaboration with my colleagues. And so one take-home message, which I know all of you know, hopefully you do, is don't be afraid to look at small opportunities, because these small opportunities can add up. And just to give you one example of that, how that adds up, here's a TRACS program. These were these 2 different programs leveraged an EU funding mechanism, the Marie Curie program, or the EU, which is specifically the EU Research Innovation Staff Exchange Program, to allow graduate students to go back and forth between colleagues in Europe and colleagues in the US and colleagues between them. And it's led to quite a large collaboration for me over the years with Tino Borondo at the Autónoma in Madrid, Rosa Benito in the Politecnica, and Jörg Mein in the Universität Stuttgart, which led to training of students. So Andre, who was a postdoc, Matthias Feldmeier and Johannes Reich were both PhD students. One of my students, Galen Craven, who later who did get a PhD, is on the faculty at Los Alamos. A number of students who, through this exchange, are able to learn and do science in a way that they couldn't do just in our individual labs. And so that's one kind of win. Just to give you some example, this is too much detail for all of you, but we've been very interested in transition state theory, and we were able to use the techniques in understanding phase-space physics to characterize dividing states, dividing surfaces or structures that divide between reactants and products in a way that leads to reaction rates that are reaction rates which are exact because the trajectories are non-recrossing. And we developed this into non-equilibrium conditions using a so-called moving transition state where the moving transition state, which you see in this depicted here early on, is only crossed once and only once by the trajectory, whereas it's crossed many, many times in the stationary frame. This has led us to a large number of papers over the years, and this is all I'm trying to do in showing this slide, drowning you with papers. But importantly, these papers involve collaborations with Thomas Barsh, who's on the faculty in the UK at Bath. Not at Bath, sorry, at the UK. Forgetting this university at this moment. Jörg Mein in Stuttgart. And like I said, Rosa Abenito and Tino Borondo. So all to say that one can do science, and in my case, because I'm a theoretical computational chemist, maybe I don't have to be on site. What's really beautiful about the synchrotron is many of you have these wonderful facilities, but you also home people from many places all over the world, and sometimes they can do the experiment either remotely, or they can at least analyze the data remotely, which allows for a lot of exchange that's international. And I think that's one thing that helps your team. So that's the first story. The second story is more about human training and what are the advantages when you start bringing together people with different perspectives. So we've developed a leadership training workshop between 2016 and 2020 called an Academic Leadership Training Workshop, or OUT. And in this Academic Leadership Training Workshop, I know some of these things are a little small, but again, I'm just trying to paint a picture where our learning objectives were to help faculty as they have gotten tenure, now they're associate or full professors, and they want to understand how to be leaders, whether that's in administrative leaders like a department chair, a dean, or a provost, or whether it's a research center director. And so we wanted to help them learn how to become an academic leader, be motivated and prepared for those roles, learn to use skills and tools from the workshop to be more effective leaders, focus on improving their leadership strengths towards extraordinary leaders, know the range of duties and obligations required of academic leaders and be prepared to address them, and then be able to win the job if they got there. We've published some of the findings that we had from the very first workshop in an ACS issue back in 2017, and many of the methodologies that we used back then are still true. I also wrote an article in ACS in Chemical Engineering News. It's an ACS publication on academic leadership skills 101. What's important also on this slide, which you might not be able to see because it's too small, is that everyone who took the workshop, and there were between 25 and 42 participants over the years in each particular cycle, 25 or the most in 2020, 42, they would recommend the workshop. And only a small a number of them, like less than 10%, would have some reservations. In terms of, and the workshop met their expectations, always exceeding or far exceeding with very little exception. And then with respect to all of our learning objectives, which I just detailed, there were 1-point gains on 5.0 scales, both with respect to the knowledge of the objective and their ability to learn. So this was the basis. We had learned how to develop an academic leadership training workshop. And I'm happy to say, by the way, that after a hiatus because of the pandemic, the next workshop will be held in February 2025. And we already have 36 participants who are paying around $2,200 now to participate, not just $900 as in the early events. From that, we decided to pursue, there was a basis for then asking, how could something like that be carried over into an international sector? And the baseline was not just our academic leadership training workshop, but also the new faculty workshops that had been done in physics with the AAPT and in chemistry through Research Corporation for Science Advancement and ACS. So notice that I mentioned Research Corporation for Science Advancement, which is a foundation in the United States that funds research. And I'm mentioning the Fulbright Foundation, which many of you know already in Germany and other sites. And the important part of this is that one other place where you can get funding as you're looking for opportunities is also through partnerships with foundations where there's resonance in what you want to do. So the baseline problem was that there was already success in teach and helping new faculty learn how to teach and learning faculty learn how to lead. And the need, which was posed to our team, was how to accelerate the success of junior professors, assistant professors, etc., in the changing academic landscape in Germany and perhaps other countries. I don't have more than 5 minutes, so I better hurry. Oh no, 10 minutes, I think, 5 to 10 minutes. The existing relationship, there was Fulbright Cottrell Scholars recognizing junior faculty in chemistry, physics.
You have less than 5 minutes.
Okay, cool, thank you. For integrating top-notch research with creative teaching. And the solution was to develop a collaborative that would create these bridges to Germany. The components, again, were create a workshop that was with intentionality, doing leadership and other goals. And the participants loved it. They learned things that they wouldn't have learned otherwise, and they hadn't seen through their training otherwise. And when they were asked what was most important that there was or surprising, they learned there was learning that was going on. There was teaching, academic, networking, all sorts of things that you could expect it to do. This workshop has evolved over time. The most recent one was held in September, and their focus areas were science communication, storytelling in science, and teaching science communication. So all to say that you can collaborate to figure out how to train students well. The third story, which is going to be super fast, is how we can advance green chemistry and sustainability. And this is the context is the American Chemical Society. It's a very big organization. It has a very large budget and a lot of people, 150,000 members, almost $1 million in budgeting. We also publish a lot of papers, many employees. We have an international footprint. And from that perspective, what can you do? You can do things like bring in a successful institute that is advancing sustainability goals. And the ACS Green Chemistry Institute was founded in 1997 and became part of the American Chemical Society in 2001. So again, another possible goal for you is to think about what pieces of what you do can merge or be merged into professional societies if there is a commonality and goal. In this case, the commonality and goal was sustainability. And so the ACS, of course, doesn't just have money to burn, but we can look for opportunities and alignment for funding it through collaboration with funding partner with people who want to with philanthropy, as well as with other institutes like the Center for Green Chemistry and Green Engineering at Yale, and Beyond Design, the Green Chemistry Education. And so this allows us then to think about as a platform how to facilitate global engagement. And that again goes back to what you're all doing. And I want to point out that even just a snapshot in 2025, the ACS through the Green Chemistry Institute and our whole portfolio, we're looking to have a number of convenings all over the world, including the South America, including the Pacific Chem 2025, where many of you may go to, Africa, Asia, Europe, etc. So one thing which is exciting that we can do is to recognize that we can leverage our position to truly be global. You can become a member of the ACS if you're not already a member of the ACS. The membership fees may seem very daunting at $160 for a premium level or $80 for the standard level, but be aware that we now have offerings starting in 2025, which will reduce that contribution to as much as 66% reduce 66 to 50 to 66 to 75% reductions based on World Bank country classifications. So all to say that collaboration can be driven by funding agencies, through foundations, or professional societies. And one thing that your group can do is look for opportunities to partner in some way across there. The international collaboration, of course, enables new ideas, student training, and networks among colleagues. That's why we want to do it. And the keys to success for me and my team has always been trust. If we don't trust each other, we're not going to be able to get very far. And I see that that's what you're developing here in this forum. Create a common language and goals. The common language is not just that we speak Spanish or English or French, but that is one where we appreciate each other when we speak. We've identified what our goals are. Meals, I like to joke that the first thing that ever happens whenever I go to a meeting in Madrid is that we start with the comida or the big lunch in the middle of the day. And because it makes sense, everybody has to come in, and it's the middle of the day, you get there, and then you have the meeting. What that comida does is it creates community. So as you think about the kinds of goals and programs that you do, I know many times they're virtual, but if in person, think about how you create trust and community. And finally, look for engagement. Sorry that's misspelled. The American Chemical Society is, when it's thinking about its members, it's good that we have a lot of members. But what's even better is that most of our members are heavily engaged, and we're looking to increase that. So with that, I know that was a lot to unpack in 25 minutes. I would be remiss if I didn't acknowledge my my team, my students, as well as some of my funding partners. And I'll go back and leave it here in case there's any questions or comments. Thank you for your attention.
Thank you. That was a very nice talk. Are there any questions for the speaker?
Lawrence, if anybody else has one, they can go, but if not, I have one.
Marvadine, go ahead. We probably have the same question.
Okay, I have a comment. Thank you so much. And I just want to let you know, in the Caribbean, we have an active ACS chapter, for instance, in Jamaica, and I know other islands do also, very active. You have some small grants, like travel grants and other small grants that your members and our people benefit from. And so one of the things I'm thinking that the ACS could do in helping us realize this project, which will benefit all of chemistry in so many ways, is to earmark some funds, some travel grants or other small funds, whatever, or even big funds, whatever the ACS can afford. But we could get our young people, young chemists, and senior researchers to visit, synchrotrons. Also to travel to some of these conferences as we try, and workshops, training workshops, as we try to build capacity for the use of advanced techniques like synchrotron sciences in this part of the world, Latin America and the Caribbean.
So thank you for that comment. I'm not in a position right now to to confirm which grants we're giving and how we might be able to change that. But you're certainly welcome to send me an email with what your thoughts are, and I can relay them to our international team and see what's possible.
Okay, will do. Thank you, and thanks again for the great work the ACS continues to do for all of us here in the region.
Thank you. Nice to meet you, Marvadine.
Nice to meet you.
And another thing that I wanted to sort of bring up is that, so it turns out that in May, Commonwealth Chemistry is having its conference in South Africa, I guess a few days after your event there. We've talked about, Marvadine and I have talked about having a sort of Commonwealth Chemistry West, kind of a virtual chemistry conference. Actually, it would be great if ACS could join us in that.
I don't control all of the schedules, but if you shoot me an email, I will relay it to our team.
We will.
I was just going to say one thing for virtual meetings. I know that the ask is a little bit easier, right? Because, for instance, this is a virtual meeting. I could take time and join. I was really honored by that Leo and Jorge thought that it would be useful to have me on this when I have never done anything with synchrotrons. So just let us know what the ask is, and we'll see what we can do. So that we can, our mission is to engage the chemistry community writ large and to help amplify the work that you do. So to the extent that we can do that, we will.
Okay.
So let me just say something to add on to that. So I'm on the scientific organizing committee for Commonwealth Chemistry Congress, which is in South Africa, May 11 to 14. And we have been, Lawrence and I, Lawrence got this idea, and I've been pushing the team and the organizing team to have this parallel session. And I'm not getting much support on it. So if we do get your support on it, I think something in writing or something could help. And we can get you whatever you need to show that there is interest for something like this.
Well, again,
right,
I have to apologize. I mean, as a person, I care about your success. As representing the American Chemical Society, one, I'm not yet the president-elect, and
Right.
two, I can't commit ACS funds or ACS policy without the team being aligned with that. So the best I can say is please send it so that we can at least consider it and make sure that as a team we can try to do the best we can. I can't confirm that we can do it without knowing what the exact ask is, etc.
Well, I think even a talk on laser trapping of transition states would be interesting enough. Sort of an experimental look at some of your theoretical work. We could talk about. I could talk about that at length, actually. So.
That sounds cool.
Okay, Camille, do you have a quick question? Is there any other questions?
I think Camilo is trying to speak, but he's muted.
Oh, go ahead.
Oh.
No, now you're muted. Sorry. Now, I'm sorry.
Now
we can.
Sorry. Yes, I was speaking. So nice to meet you, Rigoberto.
Encantado, Camilo.
Mucho gusto. So the question is, how works the taxes when you have funds from different countries, in this case, and the national requirements? Because I know that there are some funds that they said that the people should be national, citizen. So how works in this case in the project?
This is a really good question. That's a very detailed question, and it very much depends on what you're asking for and how the funds are committed. In some cases, in the U.S., when we give travel grants, even though the individual is international, if they spend the money directly in the U.S., that makes life a lot simpler, right? Because we just reimburse dollars, which are spent in dollars. If there's money that travels between countries, as you well know, that depends on the agreements between those countries. Some of those agreements are related to, of course, the exchange rate, but more importantly, they're related to not just the taxes locally, but the taxes on moving money between them. So grants get a little bit trickier. I know that the ACS, at least from the ACS budget, does provide some grants through the Petroleum Research Fund. I don't know whether the Petroleum Research Fund, you'd have to identify for the PRF a proposal that would make sense for their purview that you would do in your synchrotron group, and it's possible. My understanding is that you can apply from some international locations. And then it just depends. And in order for them to give it to you, you need to have an accounting office that can receive it and deal with all of that. So ultimately, you and I don't have to worry about the legalese as long as we have teams of people in our respective institutions that can handle that. It's not the best answer, but I'm just saying, maybe from my perspective, I try to focus on the science and the training of the people and hope that money comes in.
Jorge, can you go quickly as we get ready for the next speaker?
Yeah, sure. It was only a reminder to Rigoberto again. Thanks for coming. But I know that the presidential year, the president of the American Chemical Society is able to sponsor symposia and national meetings. So if you ever consider during your presidential year to have a symposium on global science and chemistry projects, to remember that our projects have a big chemistry components in all the science that we hope to be doing.
Yeah. Well, Jorge, to that effect, all I can say is please, you go to the ACS meetings quite often, and so I look forward to seeing you at the next one. Just give me a proposal for what type of symposium or topic you want to do. I have it may or may not align with my primary symposium topics that year, where I'm still developing that, but the sooner you get it to me, the sooner you might have some influence on my alignment, right? But also, and in terms of how much I can fund, it's the typical thing is a nominal co-sponsorship through whichever organization you're doing. For more than that, I just don't know yet how I'm spending my budget, and we just have to find alignment on that as well. So I can't make any promises on budget.
Sure. Thank you.
Okay. All right. Well, thank you. Thank you for coming to our events here today, and we will be in touch.
Pleasure.
Let's
take
care.
Take
the speaker one more time. And then let's turn to our next speaker is Dr. Bernardo Gomez Moreno, who is emeritus professor at the Universidad de Los Andes in Colombia. And he is going to talk to us about, he's a high energy physicist, and going to talk to us about the fundamental difference between protons and electrons in synchrotrons.
Thank you very much.
Okay. Yep, you can share your screen. Good.
One moment. One moment. I will try to find. I never use the Google Meet. I always use.
It's the little box down at the bottom with the upward pointing arrow.
Hay una flecha al pie de la mano, Bernardo. Una flechita, hay una mano, ¿sí la ves?
Minuto. Sí.
Y la flechita, hay una flechita al pie de la mano.
And right, there's this way to do it with Alt Tab or something like that.
¿Ya la encontraste?
Sí, encontré.
La flecha, y pulsa la flecha y luego le das clic y ahí dice como compartir toda la pantalla. Entrar screen, tienes que ponerle.
Sí, minuto, ya voy a hacer, qué pena. Yo tengo full screen.
Entrar screen y la seleccionas, le das clic.
My PowerPoint, one moment. Sorry.
I think the thing he's not getting is the button at the bottom that says present now when you scroll over it. It's the box with the arrow in it.
Yes.
Bernardo, hay una cajita al lado izquierdo de la mano. Si haces clic en la flecha que está dentro de la cajita, debe funcionar.
Sí. Un momento. Es que lo encuentro. Yo tengo aquí el archivo de PowerPoint. No sé si ustedes lo ven.
No todavía.
Porque yo tengo abierto el archivo de PowerPoint.
Eso. Y tienes que darle clic, o sea, al archivo, ¿no? O sea, tienes que compartir, ¿no? La flechita que dice ahí.
Yo tengo aquí el PowerPoint abierto.
Eso. Y dale a la flechita que está al pie de la mano.
Cuando abro todo el PowerPoint, entonces no me sale la flechita. Permítame un instante, qué pena. Yo tengo un archivo muy lindo de PowerPoint, pero un minuto. Tengo la flechita. Perdón, un minuto.
¿Por qué?
Pero una vez.
O lo otro es que...
Bernardo, lo primero que hay que hacer, tú ya tienes el PowerPoint abierto, pero lo primero que tienes que hacer es hacer clic en el cuadrito con la flechita hacia arriba.
Y yo hago clic en ese cuadrito y entonces no veo el PowerPoint.
Entonces, no, es que no, se te va a abrir una ventana donde dice que vas a compartir toda la pantalla o solo una ventana. Yo le di a toda la pantalla y lo selecciona. Y abajo va a decir compartir.
Sí. Digo toda la pantalla y entonces abro
y abajo, no, todavía no. Y abajo dice compartir, creo yo. Y cliqueas también ahí para que ya puedas compartir toda tu pantalla.
No se activa compartir. Acá, compartir. Eso es. Y ahora sí, listo. Y ahora sí, entonces, debo poder compartir el PowerPoint.
Ahí está. Y ahora, independientemente de todo, solo lo único que tienes que hacer es buscar tu PowerPoint y cuando lo pongas, y lo vamos a ver nosotros. Genial, ahí lo tienes. Entonces,
¿ahí lo ven?
Perfecto. Genial.
Perfecto.
Muy bien.
Okay, sorry. It took me time. Okay. Synchrotrons in two different worlds. World of protons versus world of electrons. Principles and applications. Now I will talk about proton synchrotrons, not only about electron synchrotrons. There are two different worlds, and I noticed that in this event, when we talk about synchrotrons, we refer to electron synchrotrons as sources of synchrotron radiation. And this is so obvious that people don't mention explicitly that the source of synchrotron radiation are the electrons being accelerated in the synchrotron. The source of electromagnetic radiation is the electric charge that is accelerated. Accelerated charges emit electromagnetic radiation. In the case of electrons in the synchrotron, the electrons emit synchrotron radiation. But we don't mention this. And that we don't mention this, that the electrons are the emitters of the radiation. This shows that we are immersed in the world of electrons. Here is the presentation of the world of electron synchrotrons of light sources. This is the organization of light sources. You see the distribution of light sources in the world. 20 years of this organization. They try to get the information of all light sources in the world. So people in these laboratories with electron synchrotrons, they are members of this organization. But there are also people who, when they speak about synchrotrons, they are thinking of proton synchrotrons. These people are living in another world. They are people from another world. This is the world of protons. And now I want to talk about these proton accelerators. Here in a representation of the Fermilab complex, they accelerate only protons. They use presently the protons from the facilities they have to generate colliding protons with a massive target to generate pions, positive pions that decay and produce, when they decay, they produce positive muons, that is antimatter, positive muons, accompanied by their partners, that is matter, that is neutrinos, muoneutrinos. And they use the beam of neutrinos to study neutrino oscillations, for example. This is the subject now that is very important in that field, studying neutrinos. And they do this with protons, accelerating protons. Now we can think about having an electron synchrotron. If we take the electrons out of the machine and replace them by protons, we don't get synchrotron radiation. And so we can think, if proton synchrotrons don't emit synchrotron radiation, perhaps they are useless. Proton synchrotrons never will deliver synchrotron radiation. Why? Well, the reason is the mass dependence of synchrotron radiation. The synchrotron radiation power depends on the mass of the particles, of the electric charges that are in the case of synchrotron radiation, electrons. The electrons have such a small mass, rest energy of only 511 kilo electron volts. Compare this to the rest energy of protons of almost 1 GeV. Well, more precise, 938 MeV. The mass of the proton is 1,830 times the mass of the electron. And the mass is critical for the synchrotron radiation. The relationship is given here. The power is proportional to 1 to the m to the 1 to the mass to the fourth m to the fourth. And with such a small mass as the mass of the electrons, the radiated power is very large. The lighter the particles, the more radiation they emit. The heavier the particles, the less radiation they emit. And so, in the case of protons with such a high mass, the power radiated as synchrotron radiation is almost nothing, is negligible. And I have here the relationship, and that is comparing the power, the radiation power of electrons to the radiation power of protons. This is a relationship as mass of the proton divided by mass of the electron to the fourth. And this will give 10 to the 13. So that synchrotron radiation by electrons is 10 to the 13 times greater than the power of radiation emitted by protons. That is, in the case of protons, is almost nothing, is negligible. And that is why, well, we can think, what about proton synchrotrons? They are useless, or what can be done with proton synchrotrons? Of course, proton synchrotrons have a lot of applications. I will mention only very fast a few of the applications in medicine, cancer treatment, hadron therapy. I will talk about this. Production of radioactive isotopes for nuclear medicine, for biomedical research, or for industry. Also, in nuclear physics, in particle physics, scientific research, fundamental research, that is the main use of proton synchrotrons. Also to study materials, astrobiology, space simulation, industrial applications. So there are a lot of applications of proton synchrotrons. Also national security is important. Well, but I want to talk about using proton synchrotrons for medical applications. This application started with John Lawrence in Berkeley, the brother of Ernest Orlando Lawrence. They use the first beams of the first accelerators to treat cancer. Well, trying to do this, the first experiments using the accelerator beams for medicine, the years after 1932. Here is a photograph of John Lawrence and Ernest Orlando Lawrence. But the main point is the recognition by Robert Radwan Wilson. Robert Wilson did his PhD in Berkeley with Ernest Orlando Lawrence. He was a collaborator of Ernest Orlando Lawrence, including the participation in Los Alamos project. Robert Wilson. After the Second World War, he worked in Harvard, and there he studied the interaction of particles of several energies. The energies of that time, interesting for nuclear physics, the interaction of the particles with matter. And so he came to the curves I am showing here. This is a very famous presentation of the dose that is given by different particles when they interact within the body of a patient. And he is comparing here photons and protons. That is very important. This is a publication in the magazine Radiology, the journal Radiology. The title of the publication, very famous, Radiological Use of Fast Protons. Well, if I compare here the graphics, the behavior of photons, they deliver energy to the body of the patient, of the person, when they enter the body. Most of the energy is given at the entrance, and they traverse, they cross the whole body of the person, and they enter. They find, for example, a cancer tumor. They deliver energy there, but they continue, and the beam crosses the body of the patient, and they deliver energy. The beams, photon beams, deliver energy to the body at the entrance and during all the time, also when they are leaving the body of the patient. And so they can damage healthy tissues of the person. Compare this with protons. Protons enter with a specific energy that must be calculated previously, because the protons will have a specified range in the body of the person where the cancer tumor is located. This the protons are able to deposit the energy there, depends on the energy of the protons when they strike the body. They give not so much energy at the entrance, because protons are initially very fast. They enter with enough energy to have the range required. They enter very fast, and as they are very fast, they don't have time to interact with matter. The interaction is small, and that is why they will give only small amounts of energy at the entrance, only small amounts of energy. But they give this energy to the body of the person, even if it is small, so they reduce their energy. And if they reduce the energy, they get slower. And if they are slower, then they will have more time to interact with matter. Slower protons will have more time, and then they will transfer more energy to the body. And so they will, for the next step, when they are crossing the body of the patient, they will for the next step, lose more energy because now they are slower. And if they deliver more energy, they are getting more and more slower. And this will give an exponential behavior that is known as the Bragg peak. And at the end, they will deliver all their energy at the end when they have the range in that body. And that is where the cancer tumor is located. So that the proton beam will deliver the energy in the right place. These diagrams show the difference between photon therapy and proton therapy. In the case of photon therapy, the photon beam enters the body, will cross the body. The entry dose is large. They will cross the tumor. They will transfer energy. The photon beam will transfer energy to the cancer tumor, but the beam continues, and there is an exit dose that is still large. In the case of protons, it's completely different. The entry dose is small, just in the entrance. And as they continue traversing, as they continue crossing the body, they will give more and more energy. At the end, they will give all their energy in the place where the tumor is located. That is the range of that proton beam in that matter. And afterwards, there is no more proton beam, so that the healthy tissues in the body will be safe. So that having cancer treated with protons is much better than with photons. And in Latin America, at this moment, we don't have cancer treatment with protons. We only have a large amount of excellent installations, of excellent facilities in the hospitals for radiotherapy, but we have only in the usual countries a small electron linear accelerator. This accelerator accelerates electrons to 6 MeV till 25 MeV. This is enough to produce the required photons when the electrons are stopped through Bremsstrahlung. And so electrons will give photon, the required photon beam. This is the usual cancer treatment all over our region in Latin America. But we don't have, till now, proton therapy. There is in construction now a first facility for proton therapy in Argentina.
You have 4 minutes.
So
4 minutes.
Very, very happy because this is the beginning of a new time for Latin America in medical cancer treatment. Because if one country will have this, we will also have it all over the region. This is very, very important. Here is a diagram showing the effect of X-rays, the photon beam crossing the body of the person, and the damage of the DNA cells in the cancer tumor. But it's much better to use the protons. But much more better is to use ions that are heavier than protons, like carbon-12. This is the best that can be used presently in the world. Here is this image that I took from the Centro Argentino de Protonterapia. It is not working yet, but next year it should start operating with proton therapy. The first installation was designed by Robert Wilson from Fermilab. At that time, he was director of Fermilab. And in Fermilab, the installation was constructed, the Synchrotron for the Loma Linda University Cancer Center. This started in operation, attending a lot of patients during the 90s. So during the last 40 years, it is working. The installation, very famous, the first proton therapy facility in the world, constructed by Robert Wilson. And the image that I have here in the right side shows what the patient finds. It is quite interesting. This is the gantry in Loma Linda. Here, an image that shows the whole installation for medical applications of the synchrotron. At the right side on top, there is the synchrotron, then there is the beam line, the protons gantry, and after the gantry, you will find the patient that will receive the proton beam. Here in this image, there's an installation in Japan. There are two gantries. The gantry is a tremendous installation because the proton beam must be delivered to the patient, to the person, and so there are heavy electromagnets with iron core, very heavy. As it is shown in this image, there are also smaller electromagnets, quadrupoles, for focusing the beam. And this is the gantry. And this gantry has to rotate around the patient because it is necessary that the beam enters the body of the patient, not always in the same direction. The direction should be changed in every time that the patient receives the proton beam. So to rotate this gantry, 70 tons, it's very heavy. You need such a big structure as it is shown here. And when the patient enters the room where he will receive the proton beam, he will find something like this. This looks like Star Trek, like the Enterprise, something like the science fiction, but this is the Heidelberg University Hospital. They are delivering to the patient carbon-12 ions. Now Fermilab, pardon, sorry. CERN is
you're like at 1 minute.
Yes, CERN is using now superconducting toroid, as they design a superconducting toroid to deliver the beam to the patient so that they don't have the heavy magnets. This is a light gantry, it's a compact gantry, and this is something that is a new development for proton therapy or for ions therapy. There are also alternatives because synchrotrons are not cheap, they are expensive, and so there are uses of cyclotrons for delivering the beam to the patient instead of synchrotrons. But what is commercial now is cyclotrons with permanent magnets, and the permanent magnet will give only a fixed energy. And it is necessary to change the energy of the proton beam to reach the position of the cancer tumor in the person. So a fixed energy is not adequate. So it is necessary to introduce degraders, a block that is crossed by the protons, and the protons in the outside will have less energy. But the quality of the beam is not the best one. At this moment, the best installation for proton therapy is the synchrotron. But commercially, The cyclotrons are compact, they are cheaper, and that is something that is produced now commercially. This is a photograph of the installation that will be active next year in Argentina. This is a small cyclotron. It is produced in Belgium, and they will have two gantries. Here in this image you see on top there are two cyclotrons, and then there are the gantries, and then the place where the patient receives the proton beam. Here in two installations, this is what they are offering, and this is something that can be bought commercially. There is also the possibility of having linear proton accelerator for medical uses. That is for cancer treatment with protons with linear accelerator. This is developed in CERN, and now this starts test uses in the United Kingdom. The first time a linear accelerator.
todo el volumen en la computadora. ¿Sí o no?
Can you probably go to your last slide, please?
Yes, I am ready to the last slide. And now we will have such installations, I hope, in Latin America, so that we will have not only the electron synchrotrons, but we will have also part of the proton world with proton synchrotron or proton cyclotrons or proton linear accelerators with uses for cancer treatment. And I am very happy of this. I am expecting this. Well, that is what I wanted to show you. Sorry for the beginning. Sorry.
Okay, thank you. We have time for one quick question.
Ahora la presentación, ¿verdad?
If there are no questions, then let's thank the speaker. And then let us move on to our next speaker, who is Juan Alfonso Fuente Soria. And you are here. Are you able to share your screen? If not, I can do it for you.
Ahora la pantalla completa, toda la pantalla. Okay. Can you hear me?
Yes.
And
okay. Thank you for everyone, and thank you for the organizing committee for inviting me to this important forum where are present a significant number of scientists. The first question I made to me is, what is a dentist doing in this forum?
Do you want to show? Do you want to share your screen and do your slides, or do you need me?
Excuse me?
Do you want to share your screen and show your slides, or do you need one of us to do it?
Alfonso, ¿puedes poner la presentación?
Ya la podemos.
Ponla, que no la vemos todavía.
Vamos a ver,
ahí
perdona.
¿Aparece ya?
¿Ya aparece o no?
No.
Es que aquí abajo está, hombre, esta de derecha, ahí está. ¿Y ahora? Pone presentación con diapositivas desde el inicio.
No,
ahora
no se ve nada.
Bueno, pero ahí está.
Ahora sí, Lawrence la va a presentar por ti, ¿ok? Tú le dices que cuando avance, por favor.
¿Ahora sí?
No, Lawrence la acaba de presentar por ti.
Ahí está toda la pantalla.
No, in this moment, Lawrence is showing your slide.
He just needs to tell me when the next slide, advance the next slide.
Exactly. You have to tell him when they have to change the slide. Yeah.
Dale, pues, dale. Ventana, no. No quiero ventana.
Okay, now.
Toda la pantalla.
You can start his talk. He can start talking with that. He just, if he says next.
No, ya toda la pantalla. ¿Qué pasa?
Selecciónalo. Selecciona toda la pantalla y después compartir abajo.
Abajo.
Compartir.
Was he trying to share? Is he trying to share his screen while I'm sharing mine?
¿Dónde está compartir?
Lawrence, can you take
Ahora sí.
Slide?
Ahora pónganlo.
Exactly.
That's better. Okay, so
now you have to put it. Ahora lo tienes que poner como presentación ahí abajo, ¿verdad?
Aquí.
Presentación completa. Aquí
Ahora.
abajo.
Ahora sí.
No, sí se ve, pero no en pantalla completa. Puedes poner en pantalla completa en tu PowerPoint.
Bueno.
En tu PowerPoint, ponlo en pantalla completa. No, aquí abajo. Abajo al lado derecho. Ahí, exacto.
Alfonso, ¿dónde están los tres puntitos?
Donde llegaste.
Alfonso, ¿dónde están los tres puntitos?
Dejar de compartir.
Y aparece pantalla rompida.
Ahorita ya estás compartiendo. Ya estabas compartiendo.
No, pero la pantalla completa.
Perdón.
Ya estabas compartiendo. Solo tenías que ponerle pantalla completa.
Toda la pantalla.
Pero ya cuando estés compartiendo. Vaya.
No sé qué problema hay. Poner SILAC, presentación SILAC.
No, vaya, allí. Vete ahí abajo a la derecha. Okay, now it's working. Okay.
¿Ya?
Sí, adelante.
Okay. Thank you for the invitation to the organizing committee and the opportunity to share with a significant number of scientists. My first question was, what is a dentist doing in this forum? And the best response I found is the thinking of Jose. I am me and my circumstances, because you can see that the three first positions, I made a plan and then made a campaign to get the position, but the final two, the vice president and president of Central American Parliament, I was not looking that position. I was in my house and I received a call from the vice president saying that the president, because of the situation of corruption and to avoid a confrontation, he decided to resign. And by constitutional dispositions, he needs to propose to the Congress a list of 3 persons. Then say, I have 2. Would you accept to be part of the list? And I immediately say yes, because in Guatemala, the vice president is the one who presides all the government cabinets, including the one of science and technology. Then, in addition to increase the possibility of strength and diversify the aspect of scientific, technological, and the human talent, and finding solutions of greater effectiveness and efficiency for the national and regional problems. This is essential because we need to communicate effectively with the politicians. They know speak scientific language. Then we need how to communicate to boost our main objective about the synchrotron. my first decision was to study measurement, evaluation, and education research in 1974. And we compare and we evaluate what kind of professional are we preparing, for what kind of reality. And we made a special project in Guatemala and Central America. And then I was invited to direct the Pro Latino in Brazil, the Latin American program toward the formation of dentists for the Latin American reality. In the position of Secretary General of the Central American Higher Education Council, I had the opportunity and honor to meet and work with physicists like Fernando Quevedo, the former president and director of the ICTP in Trieste, Galileo Violini, and Carlos Ordóñez, to design and initiate doctoral programs in basic sciences, starting with mathematics and physics in 19 public universities of the region. Dr. Carlos Rudamas is in charge of this program in San Salvador. When I was dean of the School of Dentistry, we made several epidemiological studies to know the reality of the dental situation of the Guatemalan people in dental decay, periodontal diseases, and we made an atlas of development in Guatemalan Indians and no Indians, a study that was supervised by the Center for Ground of Development in Michigan, Ann Arbor. Only there are 3 studies of this type in the world. Here is the atlas, very useful. And when I was in the position of president of the University of San Carlos, the resources for research were increased 5-fold. Wherever we are, we try to give the special value to science and technology and research processes. Then my presentation will begin with the historical series of investment in science and technology in the countries of Central America and the Dominican Republic, where what is evident the few importance that in the practice has this team. After we describe some processes and initiatives that look increase substantially the investment in science and technology, like the creation of a fund, regional fund to boost the science and technology, the inclusion in the plans of government of the candidates, actually presidents of Honduras and Panama, then the plans and programs done by the Central American and Panama Commission of Technology and Sciences. And finally, the first agreement of cooperation in the world from region to region between the European Union and the region of Central America. This is important because we dedicate 12 years for this agreement. Look for the low investment in science and technology in all the countries, comparing with Latin America and the Caribbean and the world situation. It's low, low, low. Guatemala is in gold color. It's very low. Then I proposed the creation of a regional fund for science and technology in the region. Consists of an annual contribution from each of the 8 SICA member states of $5 billion per year during 5 years, which will be administered by a board of directors made up of a representative at the highest level of System of Central American Integrations, the Commission of Science and Technology of Central America and Panama, and the Higher University Council. The countries that make up this region are attached by member states to the Commission for Scientific and Technological Development of Central America and Panama and the Dominican Republic, whose purpose is to stimulate the link between the different national organisms of science and technology, who are the national authorities in the executive branch of its government of the region, responsible for science and technology, and who in turn generate the scientific and technological policy of the region in harmony with the socio-economical policies and programs of the member states. For sixth, the fund seeks to achieve the following objectives. First, increase the quantity and improve the quality of research to contribute to scientific and technological development and improve the provision of services that have a significant impact on productive activity and social development of the region. This is essential for looking at effective communication with the politicians. They have problems and they have new solutions and they need innovative approaches. Then finance the activities contained in the current regional strategic plans for science and technology and innovation. Support scholarship programs, training, and the cooperation intra and extra-regional levels. Support the creation of regional research and development centers whose synergies boosted academic and labor mobility linked to priority problems of a national and or regional nature. Becoming a counterpart fund for the joint management and obtaining complementary resources that enable its sustainability. Final consideration of the fund. For the region can compete better in a globalized context, demand joint strategies of cooperation and alliances, which facilitate insertion of national and science and technology systems and their universities into knowledge networks and centers of excellence at a global level. Now, I'm going to mention the agreement on political dialogue and cooperation between the European Community and its member states on the one hand, and the Republic of Costa Rica, El Salvador, Guatemala, Honduras, Nicaragua, and Panama on the other hand. This is an important agreement by the European part, Belgium, Denmark, Germany, Spain, French, Ireland, etc. It is a great project. It has more than 1,000 pages and several chapters and objectives. They were discussed with all the congresses and all the executive branches of all the Central American countries and the members of the European Union. You can imagine the effort, but the actors were constantly changing. Then we need permanently give the feedback to advance, especially for our project. The process began in 2012 and completed in 2024 in May. Head states of state, congresses, and parliaments. It's a very large exercise, but we have the results. We have the agreements that are of mandatory complement. I'm want to finish with a government level. We have the excellent position because the president of Honduras and the president of Panama have included in their government plan, including an investment in science and technology of 1% of the GDP. The president of Honduras, 22 to 26, is in process to allocate at least 1% of the gross domestic product for investment in science and technology. Then we have the possibility of boost the synchrotron project, but we need to convince the politicians, the Congress people and the presidents, but we have a frame approved with the agreement of cooperation that is region to region. It's an excellent exercise, but we need to look. In example, we can use the excellent material shared in this forum and make an executive report directed to the congressmen, the presidents, and the civil society in order to make an inclusive proposal to advance in a very good way. Thank you very much for your attention.
Thank you. Are there any questions for the speaker? Well, let me ask one question about you said convince the politicians. What are the specific arguments that you use to convince politicians? I mean, how much analysis do they have an appetite for? And you see a lot of nice reports from ministries and whatever, but not backed up by actual budgets. So how do we as scientists actually sort of traverse that fairway of policy and reality?
I think that between scientists is a special form of communication, but we have to understand that the politicians, they have problems, and they need to look for solutions for more effective ways to the problems they have and the population have. Then we need to translate with a special report or executive material to look the communication of the problems of each country or region and discuss with them. We can look for the European Union because they are compromised, and we can look the SICA space too, because Central America is strongly with this compromise of the agreement. Then we need to look, maybe get a fund of this group for making visits and discussions and seminars or workshops with the people of the countries in order to get the approval, because the problem is the initial one. Then at this level, the executive is essential. But for the next years, the sustainability, the congresses are very important. But all the congresses of the country, all the countries, they approve the agreement agreement accord. Then we need to look the points for supporting our purpose. I think that maybe a commission of this group can make executive with the excellent material shared with us, and look the ways and look the contacts to be in the congresses with the presidents, because they meet at least twice a year. Then we can ask for communicating with this. This is the first thing I think is useful for our common purposes.
Understood. Well, thank you for your talk today. If there's no further questions, let's thank the speaker. Leo, did you have a question for the speaker? You're muted.
No se oye, Leo.
Leo, estás muteado.
Desconectado tu micrófono.
No, not special question, except that we must say that Alfonso has been one of the authors of the first article we wrote launching the idea of a regional center, a regional synchrotron 3 years ago. So he actually is part of our project very closely. And I have so many, so frequent conversations with him that I don't think there's need of any special question, only a comment that he's a dentist, but he's been rector of the university, and his experience in the science, policy, and science technology is not that of the usual dentist.
Yeah.
Of course, it is clear from this presentation. So you are dentist just as a side activity, Alfonso.
All right, thank you. Thank you. So I think our last speaker today is Dr. Patrick Kresik. Did I pronounce that correctly?
Yeah, you did.
And he is a senior scientist at SLAC, the SLAC National Accelerator at Stanford University, where he has over 35 years of experience in accelerator systems design. And what he's going to talk to us today is about the photon science program at SLAC and his experiences with scientific education, outreach, and technology in the global community. Thanks.
Okay, I'm just facing the challenge of getting my slideshow shared.
¿Qué dice? No lo escuché bien.
Okay, do you see that?
Estuvo más o menos, ¿no? Puedes quitar el micrófono.
Yes, we do. You conquered the challenge.
All right, thank you. And it's in full screen?
Yes, it is.
Excellent. All right, let's see if I can advance it now. Here we go. So I'm going to give you a very brief overview of the photon science at SLAC. I think everyone in the synchrotron radiation field is very familiar with SLAC. Then I'd like to talk about how Western national laboratories, such as the US, can support new initiatives, such as the Greater Caribbean Light Source, and some personal ideas I want to put forward to overcome the many challenges in building a large-scale facility in new regions. So just one slide I have on the historical background of synchrotron radiation research at SLAC. The photon science program at SLAC is based on 3 major facilities, which I'm going to show you. The Linear Coherent Light Source, LCLS, it's an X-ray FEL. The older Spear 3 storage ring at the Stanford Synchrotron Radiation Light Source, and another machine that we haven't discussed really at this meeting so far, and it's an ultra-fast electron diffraction beamline, also known as UED. So here's an overview of the SLAC site. It has a 3-kilometer LINAC. The first 1/3 of the LINAC is given over to a superconducting LINAC that delivers CW beams, 1 megahertz repetition rate, and delivers them to hard and soft X-ray undulator in the undulator hall located about here, providing X-rays to the user facilities here. In this other view, you can see the storage rings. There's the Spear 3, the smaller storage ring with a very active synchrotron light program. There's also the larger PEP ring, which is unused at the moment, but is proposed by some for an eventual future very low emittance light source. And then there's a very small beamline located on the SLAC campus here, MEV UED. It's a photo injector delivering MEV beams for ultra-fast electron diffraction. And I'll tell you more about that in a little bit. So, history of the synchrotron light program began with a hole in the wall, literally in 1972. This old historical photograph underscores how the Spear storage ring was really built just on the parking lot for very low cost at SLAC back in the old days. And it was used for high energy physics. Spear is the Stanford positron electron accelerator ring for colliding beam physics. Also, 2 Nobel Prizes attributed to discoveries there, the J-psi particle and the tau lepton, both discovered on the Spear storage ring. But other researchers convinced them that the synchrotron radiation light should not go to waste, and so they made an opening in the beamline, and it went to one small hutch here for the very first experiments. A year later, they began to operate full-time experiments in parasitic mode, and then by 1992, Spear was dedicated to synchrotron light experiments only, and it's now evolved into the 3rd generation Spear 3 and serves many experiments and scientists from around the world. There are many different experiments I could mention, but I'll highlight protein crystallography because it's such an important one in societal roles for this kind of machine, where it's being used for creating molecules that can target important proteins in the body, such as insulin receptors, as well as the proteins on the surface of viruses, notably the SARS-CoV-2 virus, and the binders that neutralize the virus have been studied here. And these are some images reproduced after doing protein crystallography analysis at SSRL. And I wanted to underscore that for these kind of studies, you need 8 kV X-rays, and they're being produced by 3 GeV storage ring. We want to keep that in the back of our mind when we think about parameters for a future storage room. SSRL the LCLS rather, carries this kind of research to the next step and combines molecular imaging and crystallography with ultra-fast pulses, allowing us to watch changes in chemical and reactions and molecules as they happen. And one of the most notable experiments, in my opinion, is the understanding that has been gained into what is possibly the most important chemical reaction on our planet, that of photosynthesis. And with the decoding of the molecules, they have been able to identify the energy process that releases the hydrogen atoms from water when in the presence of visible light, which then through various pathways forms the carbohydrates and sugars in the plant cells. So a very significant piece of work able to be done at LCLS by virtue of the ultra-fast nature of the beam. We heard on Wednesday already some of the studies, the cultural heritage studies, and I'll show you these again, just to emphasize that they were in fact done at SPEAR, at SLAC. The two I selected here, one is the Archimedes palimpsest. That means it was an ancient book written on animal hides or parchment, and because this material was precious, they would scrape off the old text and rewrite, in this case, a medieval religious text on the pages. What's interesting about the study that was done at SPEAR is that it revealed actually 3 layers of text. Beneath the religious writings from the Middle Ages was Archimedes' original writing, but on the topmost layer, the book had at one point belonged to a collector who did a forgery in the book and tried to make the book more valuable by inserting some illustrations done in gold paint, not realizing, of course, that the real treasure was the writing of Archimedes buried underneath. The other example is a famous fossil, a dinosaur fossil, Archaeopteryx, where they used the X-ray beam to analyze the structure of what appeared to be feathers in the fossil, and they could prove that these feathers had the same structure and composition as feathers in modern-day birds, confirming the connection, evolutionary connection between this early feathered dinosaur and modern-day birds. This work was pioneered at SSRL by my friend and colleague Uwe Bergman, and I left a reference to a very thorough paper of his describing all these cultural heritage measurements. So the other third arm of proton science at SLAC that I wanted to cover was the crystallography, the nano imaging, and femtosecond time resolved spectroscopy that's possible with the ultra-fast electron diffraction measurement. These are just 4 quick examples that I won't have time to go into in detail, but you can tell that you can get very similar science analysis done with this low energy electron beamline as you can with synchrotron light. There's a lot of complementary aspects and similarities, how one does these experiments, and they're performed with very similar setups as synchrotron light experiments. And they had the added advantage that it's ultra-fast pulses, so it can be used again for revealing chemical reaction processes. So what's the support that we try and give for new international facilities? SLAC has a history of supporting new international initiatives. We've participated in collaborations and proposals for new international initiatives. We do that by hosting visiting scientists and engineers for training in both accelerator and X-ray technology. We've participated in collaborations where we've actually built accelerator and detector systems for others. And we've even gone so far as repurposing surplus equipment from SLAC. But nowadays, this is getting increasingly difficult because of the stricter government export controls. We've seen this map of many times before in the symposium, so I'll skip over that. But I do want to take a minute to give a salute to my friend and colleague Herman Winnick at SLAC. Herman is now at age 92, unable to participate in symposiums such as these, but he's been a proponent of synchrotron light source and a leader in the field for many years. There's a photo of him in his younger days at Wright in front of the first wiggler installed on the SPEAR beamline. He was a proponent of wiggler and undulator magnet insertion devices. And then in more recent years, he was an ambassador for synchrotron light sources in developing countries such as Sesame, which he began working on in 1998. And later, he contributed towards the African light source and the Mexican light source proposals. So we have a lot to thank him for, I think. And so what are some of the challenges facing a new facility? I think the first one is the very large capital outlay for a storage ring facility. There's also a lengthy construction time that is faced in a developing nation before you can even publish the first scientific results. And then there's the issue of how to train and build up local expertise in both accelerator and X-ray technology. You definitely need international help. So then the question is, how do you attract that international participation and collaboration? I think the Caribbean Light Source is doing the right things in seeking both local and international political and scientific source support, but how do we overcome some of these challenges that I listed above? So what I'm going to do is propose a staged approach to the funding and building a synchrotron light facility and science center in small steps. We know all the advantages of having a synchrotron, but the barrier to building such a facility is that high initial financial outlay, and secondly, that long latency between starting the project and delivering the first science. So my approach would be to take a progressive staged approach and propose a smaller initial outlay which has a promise to deliver science within a year or two of construction. What one could do is try and gain experience with accelerated technology at the outset so that students and staff get hands-on experience working with a machine, and the hardware gets incorporated into a future synchrotron source. So what I would suggest is that one begins with the construction of a 2 to 3 MeV RF photoinjector gun, which would serve as an ultra-fast electron diffraction or UED experiment. This eventually becomes the injector for the storage ring, so you're not building something that is wasted. One could also have in that same laboratory one of these new 160 kV liquid metal jet sources that's capable of delivering hard X-rays in 8 to 15 keV range with 10 to the 10th peak brightness. That's what's achievable nowadays with these types of sources. Building these two smaller facilities would result, I think, in productive scientific publications within about 2 years of starting the project. And the initial cost outlay would be about a tenth of the cost of a full synchrotron storage ring facility, and all the components that you do build can be reused for the synchrotron storage ring facility itself. If you compare this to a non-stage storage ring construction project, the full cost commitment has to be made before construction begins. You need to recruit a full complement of engineering and accelerator design staff almost immediately. And you have to rely on on-the-job training or overseas training. And with that, you're not going to get scientific output for at least 7 years, and there would be limited opportunities for students in this time. So the temptation in that case is to lower the initial cost commitment by building a smaller machine, since the cost is proportional roughly to the square of the energy of the storage ring. But then scientific capability becomes limited at the longer wavelengths. And in so doing, it becomes more difficult to attract foreign participation, scientific visitors and consultants, compared to, say, a state-of-the-art facility like the ultra-fast beamline facility, for example. So the science motivation for stage one of an ultra-fast science center is based on the fact that in 23 there was a Nobel Prize for just that field of science. I have some backup slides that show a little more about that, but I don't think I have time to show that today. But I will show you a little more about the UED beamline and what these new tabletop X-ray sources are capable of. This is a photo of the UED beamline at SLAC. It's in fact a straight line, not curved as the distortion in the camera shows in this wide-angle view. It consists of an LCLS type RF gun that uses a laser and a photocathode, and it has sample chambers and detectors on a relatively short beamline. Operates in the 2 to 4 MeV range, fairly low charge, very small spot sizes, 10 down to 10 microns, and the repetition rate can be quite high, 360 hertz at the moment, going up to 1,000 hertz, and can be used for all the scientific applications listed here on the left, which are very similar to the kinds of studies that one would make at a synchrotron storage ring. The hardware components of such a facility comprise of this beamline that I showed you in the photograph, with the electron gun at one end, some beamline diagnostics, sample chambers, and detectors that are very similar, if not identical, to what I used on X-ray beamlines. There's a high-power klystron for the accelerator. There's a laser system. In this case, we use a kilohertz rep rate 5 millijoule Ti-sapphire laser, which is the same laser used on the photocathode of the gun, as well as for pumping the samples in pump probe experiments. We have a control system for synchronizing the laser and the low-level RF timing system. And the electron gun, as I said, is the same gun that's used in the injector for other synchrotron light sources. So the approximate cost for such a facility is around US $2 million, with the breakdown as I've shown on the slide there. I won't go into the details. The other thing I wanted to quickly show you was what's commercially available now with what they call liquid metal jet X-ray sources. So there's a company in Germany, Exilium, who's selling such devices that can produce 8 to 25 kV X-rays with these notably good performance in brightness and flux. Of course, this is not competition for a synchrotron storage ring, but what you have to look at it is, if I do an experiment where I finally get permission to have beam time on a storage ring, it might take me a few minutes to do that experiment on the storage ring. But with such a device, a tabletop device as this, it might take 24 hours. But if you consider you're training students, 24 hours is nothing really in comparison. It yet still gives them good experience and training. These are the kind of experiments that have been done with such sources. The source costs around $500,000 to buy, and if you want to buy a complete and fully instrumented beamline, Brooker, for example, will sell you a complete facility in the $1 to $1.5 million price range. And again, compare this to the cost of a storage ring, whereas this device lets you get started straight away training students on X-ray sources. So the cost of a stage 1 facility in the staged approach is less than $10 million, I think, which would include all the buildings, labs, and the hardware equipment. So in summary, I think SLAC, I've shown, has a world-leading photon science program. It's continuing to expand its capabilities with new cutting-edge facility upgrades. We've had a historical role in creating dedicated synchrotron radiation facilities and pioneering new X-ray techniques and application. We do support the proliferation of X-ray science and the development of new facilities worldwide. We do that through outreach, education, training, and our participation in new proposals. We also have a history of collaboration in building accelerator and detector systems. The challenges facing a new facility in an emerging economy might be addressed, I think, by taking the staged approach and not compromising on the final performance parameters which would determine the kind of science that you ultimately want to do. With that, I'll say thank you and take any questions.
Thank you. Any questions for the speaker?
Lawrence, I have something.
Sure.
Okay.
Thanks so much, Patrick. I just wanted to ask about the dedication of a beamline, because Caribbean and Latin American scientists, as everybody has said, when you write these proposals, you go into this big pool, and there are many good proposals that just don't compete, and get out competed, particularly because we are still growing and developing in our use of X-ray technology, for instance. So is there any way, maybe it's something I'm making a suggestion and you can comment, on a dedicated beamline, maybe we could build together, or maybe some opportunity that can help us in the region, give us some, I don't want to call it preference, some way where we could get some our proposals in, and not necessarily through the big pool where we get out competed. Maybe we, let's hear what you say.
Yes, it's difficult, and I sympathize because it's a vicious circle. You don't get the chance to do the experiment, and therefore the next time you come around, people don't give you the recognition because they say, well, you haven't really tried this before. But my suggestion is, well, if you have some of these small tabletop X-ray machines in your own lab where you've done a preliminary experiment and you've shown, how you prepare the sample, how you take data, how you analyze the results, I think that gives you a leg up when you make a proposal at one of the large international facilities. The problem, as you say, in competing in these large international facilities is they really do get judged on scientific merit. I haven't seen a program where people say, well, we have to give additional help to underdeveloped countries. Science is a cutthroat business and it's very competitive. So it's possibly not what you wanted to hear, Maureen, but that's the reality. Another question, Luca, I see your hand up.
Thank you, Patrick, for your very nice presentation. I'm really happy to see that we are sharing this vision of a staged approach towards the large case facility, with the first phase that is more modest in cost, but that can give opportunities. In your option, you put emphasis on this ultra fast electron diffraction that is, I would say, very well distributed. Also in Europe, we have a bunch of these facilities. I think one in Desi and one in France, as far as I remember. So, but my comment is that in principle, your option is compatible with the option I was pushing of the compact light source. Because if you take your ultra fast electron diffraction gun and you add a single accelerating cavity in order to get to, say, 30, 40 MeV with a parallel beam line for the electron beams, of course, and then you invest another couple million euros for the interaction laser, you get with the same machine the possibility to do ultra fast electron diffraction and high energy X-rays with the Compton backscattering machine. So let's say I'm happy that you share, we share this vision, staged approach, without compromising on the performance, the long-term performance. That I fully agree. Yeah, thank you.
So we have our eye on the end goal, which is this high performance ring, storage ring based light source. But along the way, I think it's important to be able to start doing worthwhile scientific studies quickly and to do it on hardware that people can learn and get experience and that they will be using in the final facility. And it also gives the laboratory credence with the funding agencies that you can say, look, we spent a few $1 million, we're producing scientific papers now. We can make the case that, we're a responsible laboratory that knows how to spend money and do science. And I think that helps in the long game as part of the science diplomacy as well. Thank you.
Exactly.
Leo.
Well, actually, I will say something which is a little bit different from what is just said, in the sense that I agree that the idea of small sources is a good idea from many points of view. However, and we can think about to the presentation of Simon Tonnell this afternoon or this morning. The list is that there are two lists. One is that this will send to an undetermined time, which will never occur, the idea of bigger facilities. But this is maybe not a problem. But the real problem is that the list is that the advantage of lower cost is only apparent because it will be easily acceptable only for countries which are richer, but the countries which are poorer will not have the possibility of participating in it. And so we would fall in a system of national accelerators, not regional, and at the national level, even that may be too expensive. So that I think this is an interesting question which we should think about. I think that the merit for small light sources exists, but then the political implication of a choice like that, the one you were making, Patrick, I'm afraid may be negative for the future of the initiative. But I think we must discuss. I'm not sure that what I'm saying is the truth. I'm just saying that one should consider many different elements and not simply the cost, the easier feasibility or not from the financial point of view, but also many other implications. But this is just. But I would like to conclude my comment with another comment about Slack, because I like to say that there is one person we have not nominated and named during this symposium, this conference, which really has played a tremendous role for Sesame and also supported us very much in the beginning, in the years between 21 and 24. So I would like to ask you, Patrick, to convey our gratitude and esteem to Herman Winnick. His role for what we have been doing has been very important. The mere fact that I know you is a product of our relation with Herman. So that please, I think that he would have been very happy to be with us in this meeting. But anyway, please, I think that I interpret the will and the feeling of everybody here, saying that if we are here discussing this matter, much of them recognized to heaven.
Yes, if I have the opportunity, I will certainly convey that message. I think I also want to bring along the good wishes from Claudio Pellegrini, the father of FELs. He's also very supportive of this project. He wasn't able to be here at this meeting. And I point out that he's also celebrating his 90th birthday next year. So we have a field that is aging nobly.
Right. I did see that. Well, thank you for your talk.
My pleasure.
Actually, I misspoke earlier when I said that there was one that you would be the last talk, because Dr. Abel Moreno is the last talk, who will be addressing us about the experiences of the Mexican light source project. Abel, if you can share your slides and you can begin your talk. I'm really losing my voice at the moment, so.
Okay, so Victor, can you just show my presentation, please? Okay, could you just put in the, okay, thank you. Okay, this is just a short overview of what the Mexican Society of Synchrotron Light is. And at the end of this short talk, I will show you the science policy in poor countries, where you can use the facilities of compact sources moving to the fourth generation synchrotrons. So my name is Abel Moreno from the National Autonomous University of Mexico. So next one, Victor, please. Okay, so the Mexican Synchrotron is just a young society. It's a national organization founded by December 9th in 2019 by Mayra Cuellar Cruz, who is now our president, myself, Luis Segundo Fuentes Cobas, Maria Elena Fuentes Cabrera, Fernando Matias Moreno, who was one of the guys who was pushing the construction of the Mexican synchrotron since the last 20 years. He's at the Institute of Physics, Gustavo Cruz Jimenez, and René Loredo. So the idea of Mexico as a kind of just the second country in Latin America to get a synchrotron, they failed in terms of policy, science policy, because we didn't get the organization as bigger as Brazil did, because it was a kind of scientific problem changing one government to another. And then in the last slide, let me just show you. Next, Victor, please. Okay, so the idea of this group was there is no meaning to get a synchrotron without users. So that's why we decided to create this Mexican Society of Users, just to reinforce the construction of the synchrotron facility. We did organize an international congress in 2020, and then the point is we took a lot of problems. We faced a lot of problems in trying to convince the government of Mexico, the former government of Mexico, to build up a synchrotron in Mexico. We have been working for the last 20 years just trying to look at the right place to construct it. We made agreements with the governments, the local governments, and there were just quite good facilities to reach this big project, but finally we couldn't just construct this facility. Let's move on to the next one. And then Brazil, as you can see just in this slide, is Sirius. Sirius is just the only one in Latin America. And then in order to build up a synchrotron like Diamond or SRF or ALBA, it was really not possible at the moment in Mexico because of the investment. And then all the money from this science policy in Mexico was directed to government projects, which were priority. I mean, the construction of trains and big airports and so on. So that's the synchrotron facility in Mexico passed to the second place. And next one, please, Victor. So, and the point is, most of the users in Mexico were focused on protein crystallography. There are a lot of protein crystallographers in Mexico, and the idea of those guys was to avoid the use of conventional X-ray, to move on to a very complicated medical problems, even passing through biomaterial science to getting the structure of very complicated proteins like proteins just related to viruses. Next one, please, Victor. Next one, because it is just the same actually. And then what is just clear, what we can do just with synchrotron facilities. So in the conventional cases, just the protein crystallization is not a very easy task. So the crystallization of proteins is quite complicated, and thanks to the use of synchrotron facilities, we can get high resolution images or high resolution electron density maps like in the right side for both cases. And then the idea is just put the synchrotron facilities in the development of new drugs, as you can see. And then this is the only possibility to get a very high resolution. Next one, Victor. And then what is the idea of this this construction of the new synchrotron in Mexico? When we saw just the comparison between what could be the facility, well, the feasibility of building up a synchrotron, the conventional one, or just go through the Excel facility, the cost is huge. It's extremely impossible to get in Mexico. Next one, Victor, please. Although the facilities of the X-ray free electron laser is fantastic for just different applications in Mexico. Next one, please. So we compared, the pulses from the XFEL are fantastic in terms of resolutions. Even we can move not only from femtosecond just to attosecond resolutions. For a crystallographer like me, it was completely a dream, because sometimes the main biomedical problems are not only focused on just solving proteins or macromolecular complexes. Sometimes they cannot crystallize. By using X-ray facilities, we need crystals just to get the structure. Next one, please. And then, of course, just to build up this facility, which is just the example from Slack. I mean, we have seen just in a previous talk something related to this in Stanford. So this facility is extremely good. It's perfect for the modern facilities. And for a crystallographer like me, it's just like a dream coming true, because in solution, we can get wonderful resolution. Next one, please. Next, please. This is not, it's just only examples. Of course, there is a lovely story just from the European XFEL facility, because this facility was only possible by just the cooperation of 2 states in Germany, and then they just built up a lovely machine in Hamburg. But next one, please. Okay, so in the femtosecond protein nanocrystallography, nowadays, it's possible to get the structure of very complex systems by using even nanocrystals. And then by using these nanocrystals, we are now able to get the structure of very complicated proteins. But the dream coming true is in the next step. Could you just move on to the next? It's just to see the X-ray free electron lasers focus on a single object, a single particle. So recently in Arizona, I saw the first resolution of a single particle experiment. And the result is, of course, is not really impressive, as it was just theoretically proposed. But at the moment, this is our expectation for the near future. But allow me to say that this is not only a question of having a synchrotron in users, but also nowadays we need just to get facilities of managing big data, and then as well train people, train students in just a collection of computer programs for free electron lasers facilities. So next one, please. Okay, please move on to the next one. It's just how it works. Okay, so now I discovered by the collaboration with Peter Fromm at the State University in Arizona, that there was just possible to build up a compact X-ray free electron laser, which is already shown in here. Next one, please. Which is already here, but I don't know whether this is the video. So could you just move on to the next, or this is the video, Victor? No, it's just a video. Can you push the video? This is what it works. So you can see this is a compact source. So I will show you just the images with just the text in English. Okay, let's move on to the next one. So you can see this is just fantastic. Okay, what is just the cost of a compact exfil facility? As you can see, well, it is about 90 million US dollars. So you can see just this is the price for the accelerator, the lasers, the science station, the X-ray system, the facilities engineering, validation, operational capability, project managing in total. Just by getting this money is 10% of the full cost of a synchrotron facility. Next slide, please. And then why I'm just talking about this short glance of compact sources. So what is the proposal for just build up a synchrotron in countries like Mexico, or even probably in any country of Latin America besides Brazil? But so the idea is like this. Sometimes we cannot convince the politicians to build up a synchrotron, a full facility, which is 10 times the price of a compact exfil, for instance, a compact facility. So actually, the real cost of a synchrotron is just 1,000 or just 1,500 million US dollars. So the point is, for the political point of view, any politician doesn't like to see a synchrotron after 10 years or 12 years without looking at without just taking the opportunity to inaugurate the synchrotron in the period of the government. So the construction of a compact exfil facility takes more or less 5-10 years. And then for a period of 6 years in a government, it can be feasible to build up this facility and then look at the possibility to attract much more money to build up the big synchrotron, the circular source, which is just bigger. But nowadays we have the facility not only just to get a new design of a synchrotron of 4th generation with low emittance. This is a Mexican design already published by Professor Matias Moreno. But the idea is just we can build up a big synchrotron, but starting with a compact exfil facility. This is just my suggestion to convince the governments to believe that this construction of a big synchrotron, a big facility, is feasible in any countries in Latin America, because there is a lot of money. Thank you, Victor. Let me finish, and then I will could you just finish this? Okay. Let me just tell you what happened in Mexico. So after 20 years, it was really disappointing just to get the opportunity. Well, it was really disappointing to see that after working for many years, different groups in Mexico, we just pushed the idea of build up a synchrotron facility, the second one in Latin America. It was really, really impossible to convince not only the politicians, but also the ministers of science. And then the second possibility would be just to see, okay, let's try to support the idea of build up a synchrotron in the Great Caribbean, like all the group, Leo Violini and the group are just pushing. And then allow me to say that as a representative, as a vice president of the Mexican Society of Synchrotron Light, we would like just to be part of this big project, because instead of building up a synchrotron in Mexico, probably we can go through the compact X field and then supporting the construction of any big machine in the Caribbean. So we are not against the idea. We are just in favor of having this synchrotron in the Great Caribbean. But probably if you can take the proposal I'm showing you, probably the best way to convince the government is just probably to build up a small machine and then move on to the big facility. And this is just the idea of my talk. I didn't know that I was giving this talk just because I saw the program this morning. I was traveling and I did arrive yesterday evening, and then I saw that it was a talk designed for me or just planned for me. And then that's why I just was preparing this short overview and what was the idea of our proposal, our Mexican proposal. And thank you very much. And then if you have any question, please let me know and I can just answer. And sorry about that, but I was trying to be just quickly, because the idea of just using your time, I was just the previous to the last, and then I'm the last but not least speaker, but thank you very much. Lawrence, I don't know who is going to sharing my session.
Oh, actually, I'm the chair. Sorry. Is there any questions for the speaker?
Can I?
Yeah, go ahead, Luca.
Yeah. Well, thank you for your talk. I'm really glad to see that you showed a Compton backscattering light source designed by our esteemed colleague Bill Graves at the Arizona State University. That is a Compton backscattering source that is pushed to its ultimate level of coherence and brilliance, because it generates a collective instability via a free electron laser mechanism instead of an incoherent spontaneous emission of Compton backscattering. It's really exciting, but we have to be honest in saying two things. First, it's not has been already experimentally demonstrated, and it is very, very challenging, because the microstructure, the micro bunching that is generating in the beam is very sensitive to any jitter in energy, point instability, and so on and so forth. The second comment is that we have to be honest and compare the brilliance of that X-ray FEL to the levels delivered by LCLS or XFEL. That's because the beam power is much smaller. In this case, we are driving a low energy 20, 30 MeV electron beam, as far as I remember, something like that, compared to the 15 GeV. So the beam power is much smaller, and for the same FEL parameter, the efficiency is much smaller. So probably you will not get the 10 to the 12 or 10 to the 13 photons per pulse in the coherent bandwidth as delivered by the FELs. That doesn't mean that the machine is really exciting and very performant. But I would say that we should be careful in comparing the performances. But I totally agree your vision that this is a compact FEL that would be a real breakthrough in accelerator and X-ray technologies. Thank you for that.
Thank you, Luca. This is absolutely true. So they are going to go, to start just commissioning next year, actually. So, and then they are going to prove not only the femtosecond, just the attosecond facility. But anyhow, so the idea is just not to be focused on this compact XFEL machine. So it's just the beginning of a big machine. So, in Latin American science policy, probably it's much, much better to build up a kind of facility which is smaller, the risk is not very high, and then demonstrate that for the politicians, from Latin America, that these machines are feasible, and then we can move on to the next one, to the big one, which is just much better. And this is just, for instance, the case of Brazil. Brazil built up just the first synchrotron at the beginning, and then when this synchrotron was already finished, it was almost obsolete. So it was just serving the scientific community for a while, and then they move on to the next synchrotron, the Sirius, just to demonstrate that the experience got from the first one helped the scientists from Brazil to build up the new one, just getting not only knowledge, but building up a big scientific park around the first synchrotron. But it's just really, it's true what you said, Luca, and thank you very much. Patrick.
If you were to start off on a small scale, as you suggested, do you have a venue or a facility location in mind where you could do such R&D development work?
Yes, we have it. So actually, since the last 20 years, we have been just getting the support of different governors in Mexico. So the idea was to build up the synchrotron, the big facility, not just the compact source, pretty close to Mexico City, Morelos State. 100 kilometers from Mexico City or less. Probably 50 kilometers from Mexico City. And then the second governor who was supporting this idea was in the state of Hidalgo, which is more or less 120 kilometers from Mexico City. And we have just a scientific park. Even just the land is already available. And there are just not only one facility, there are just many important institutions in that scientific park. So the place to build up this synchrotron is already fixed, and we have all the projects, all the needed paperwork just to build up a synchrotron in there. So the point is, we didn't convince the politicians to build up this big machine, and that's why we decided just to get another way to go through, just by convincing them just to get a small compact source and then move on to the big one. So this is just the idea of my proposal, Patrick.
Very good.
Even your compact source would be much better just to build up something small and then move on to the next one. Thank you.
I have a question. You showed a cost of $90 million.
Yes.
But wasn't that just for the first one?
Yes, it was just the first one.
By the next one, it would not be $90 million.
It's just in between. Just it's a price, updated price between the first one and the second one, up to getting the ATO resolution.
So yeah, because I talk to Tess about this all the time, and so we think that the second one would be closer to 15 million.
Well, at the beginning, the first one was cheaper than this price, but now the second one is just this was the real price.
The first one was 90 million. The second one was going to be like 15.
Can I make a quick comment?
Yes, please, Luca.
Yeah.
Well, the latest version of that machine, in order to get the coherent FEL radiation emission, is based on very advanced X-band accelerating cavities, which are very expensive because of the gradient. The RF power sources in X-band are also expensive. Getting to 1 kilohertz is a challenge. As a particle acceleratorist, I would say that is a very challenging compact light source, and the cost is not surprising. It pays for the very cutting-edge technology that is enabling all the components of the machine.
Right. Right. So that's not surprising for the first one, but the second one won't be $90 million.
Yes, exactly.
Any other questions for the speaker? Well, let me ask this one. So have your colleagues been accepting of this sort of CXL approach to the Mexico light source?
You mean in Mexico, Lawrence?
Yes, in Mexico.
Okay. No, of course not. There was a kind of different opinions. So,
Right.
I mean, Matthias and his group at the beginning were pushing the idea of building up just a conventional synchrotron, but it didn't work. Actually, they didn't convince the government to get the money. And then that's why we decided as a young people to see, okay, let's move on in that different direction. So just the idea was to convince the politicians just to apply for this high technology and then move on to the big one. But this is just the idea, and the young people who are just participating in the Mexican synchrotron user society.
Because we have the same type of conversations in the African light source about compact light sources. And,
exactly.
I mean, there's a science case, there's an economic case, both of which.
But we can build up the two facilities. I mean, starting with this one and then move on to the big one. And then if the politician is just ready to inaugurate, to cut, the entrance and be the first, so for sure the next politician will invest a lot of money. This is just a science policy, it's just the way of the thinking of the politicians.
Right, understood.
Yeah.
Okay. If there are no further questions, then I think we'll move on to the closing remarks. We'll thank the speaker. Actually, we'll thank Abel. Thank you for coming today.
Thank you.
As actually I didn't know that you were so committed to CXLs. So it's near and dear to my heart. But we'll move on now to, I guess, final comments by Patrick and I think Victor, right?
Yes, exactly.
So Patrick, why don't you go first? Patrick? Yep. Okay. You're muted. You have to.
There we go.
Okay.
I was just going to share a few personal takeaways from this symposium. The first obvious thing, I think we all see that synchrotron radiation-based science is a burgeoning field. It's growing exponentially. There have been many new developments in light sources. We've heard about in the symposium about advanced storage ring designs. They continue to improve. We've discussed and heard a lot about compact light sources, both the Compton-based X-ray sources and also from Massimo this morning, plasma wave sources. Big step for synchrotron radiation science has been LINAC-based FELs, but they are large facilities, of course. And then I mentioned in my talk advances in conventional X-ray tubes, which I think play a role for sample screening, beamline setup, training, student publications, all that kind of thing. So one should not ignore them from the field entirely. And likewise, I also mentioned electron diffraction beamlines because of the similarity in science that they can tackle and their relevance in the similarity of the type of machine. We talked a lot about big international facilities, but I think we also made the point that there is a strong case for regional light sources to be able to meet the local needs. And local needs usually focus on things like medicine, biology, mineral and energy resources, and cultural studies. That's a big argument for having regional machines. And also one of the arguments I would use for not compromising on the parameters, performance parameters, being able to do hard X-ray science in order to do these very important fields of medicine and biology. We saw that science diplomacy is an essential factor in building new machines. Sesame is a great example of that. They've really taken this all the way. They showed how science diplomacy helps initiate a project, but one of the harder lessons that we learn from this is that science diplomacy does not always guarantee an ongoing operations budget. That one has to think more creatively how to guarantee that in the future. Support from global organizations is another essential step. We heard representation from several of these during our symposium. They're a very valuable contribution to any initiative for a new light source. Likewise, it's very important that there's collaboration with other international centers. We heard about people working with various X-ray crystallography centers. These help further the cause of any project initiative and should also be encouraged and further acted upon. And then a shout out that I'd like to make that we did manage to state the importance of gender equality in any new project initiative. To not do so would be a failure and understate the importance of a huge resource in our society and a necessary step in emerging countries in the development of their science program. So I'm glad that that was brought up in our symposium. We talked about some of the challenges to be faced in building a new facility in an emerging region. Large cost that's you need at the beginning of a large project. Some people argue that it's very difficult to get over that high threshold. So how do you attack that? You could say, well, I'll build a slightly smaller machine, or no, I'll keep the bigger machine, but I'll get there in steps. The other challenge that we face in these new initiatives is that there's a lengthy construction time. Take the example of the Brazil light source. There was a long time between starting construction and publishing the first scientific results. On these kind of timescales, there are regime and government changes, and so the whole economic climate can change. So being forward-thinking in the planning, one needs to think about how can one get a scientific foothold during the project phase. The next challenge is how in a new country, a new region, how to train and build up some local expertise in the new field of accelerator and X-ray technology. We talked about various approaches like having scientists visit international facilities and learn there. We had a great talk at the beginning of our symposium from Caterina Biscari on how this is done at ALDA, and I think that's very important for the Spanish-speaking world, that they continue to do this training at places like ALBA. Likewise, it's also important to attract international participation and collaboration because that's where ultimately the knowledge, the know-how, the new ideas come from. International organizations are magnanimous and want to support these, but one should think about how one talks about the project as a whole to keep it interesting and exciting for foreign participation. So look for creative solutions that address each of these challenges, choose the size and the parameters of the facility carefully. As I said in my last talk, I think hard X-ray capabilities are very important since they're required for protein crystallography, which is the basis for biomedical research programs, which address those regional needs. So we should not compromise on this capability. We should evaluate compact machines, as Luca has been proposing, but we should weigh the technical complexity versus the advantage of size and cost. As Luca said, sometimes you need not only a laser specialist, but you need a laser guru to get some of these machines to work. And that's a challenge when you're building a new facility. So the other approach was the one I offered, where you take a staged approach, where students and personnel can be trained on smaller machines, yet still produce publishable results in a short time. And those smaller machines should be expandable to a full-sized facilities. And the example I brought up was doing science with an injector beamline for a future ring, plus some tabletop X-ray sources, which would allow for training in techniques and detector technology. So I think the Greater Caribbean has enormous potential. It's really calling out for a new common science center. And I want to finish by thanking all the participants and the contributors. And I think we all wish everyone future success in this enterprise. Thank you.
Thank you, Patrick. That's a very thorough review of what we discussed over the past 3 days. And I think you've captured all the great points that were raised in all the talks. Victor.
Yes, thank you very much. My first reflection is that one thing that I learned just a minute ago is that if I need to write a review, I will invite Patrick because he's done a very wonderful job. Thank you very much. And my second reflection is that we have demonstrated to ourselves, and we need to bring this to the rest of the world, that the synchrotrons are attractive, are really interesting, because we just spent 3 full days with many, many conferences, and we kept a very interested audience all these 3 days. So the conclusion is that at least for a group of people from every corner of the world, synchrotrons are attractive. So that's the second reflection, and we should be discussing how to convey this message to the rest of the world. Third reflection that comes to my mind is that there is no doubt to any of us and any of the people who we have talked to directly that the science behind synchrotrons is really important. Many Nobel Prizes have been related to synchrotron studies, and but in today's world, where this scientific thought, this scientific thinking is not that fashionable, we have many chiefs of state all over the world who believe on their own data rather than scientific data. And we should accommodate to that. Instead of fighting them, criticize them. In Mexico, we just had an election a few months ago where people were convinced by data which were not what we could regard as hard data. So that's a fact. And that's the fact in many places in the world. So the reflection and the challenge for us is how we convince people who have no scientific thinking. And I believe, and after listening to the wonderful talks that we had these 3 days, that we already have there the elements. What people is interested about is climate change, and we have to show them that climate change that is in everybody's mouth all over the world can be, if not alleviated, at least helped a lot by these techniques. That's a message that we should be able to convey. The second thing is migration. Here in Mexico, but that's a fact all over the world, including Europe, not to say Italy, Africa. We have a very urgent problem with migration. How we can help to solve that? And the answer, I think, was given by the then attaché to the American Embassy in El Salvador, who's now just being appointed ambassador to Mexico. And he basically convinced the president of Salvador, Bukele, to change their mind and to open opportunities there. And as a result, in less than 4 years, El Salvador passed from being one of the most dangerous places on earth to one of the safest. And if we are able to say, okay, if we open this facility, not only will be jobs for scientists, chemists, physicists, but also to administrators, to tourism guides, to vendors of everything that you could think of, because that is a need. And one area in which we should not leave behind is what I call tourism 4.0. 4.0 meaning industry 4.0, but it could be also named tourism synchrotron 4.0, meaning that we could encourage high-level tourism for medical purposes, for cultural purposes, other than just lying by the beach. That's a second opportunity. And the third urgent need is gender, that I stress out in my presentation, and I'm very happy that Patrick recalled, because again, half of the population of the world are women. We need to provide them with opportunities, with attraction to the type of work that can be done in synchrotron. So to summarize, development, migration, and safety, along with gender issues, are the things that we should be able to convey to the people who take decisions. And I just signed to by thanking all my colleagues who spent a lot of work in putting together this meeting, and of course to all the authors who were willing to spend their effort, their time, their wisdom with us these 3 days. And by saying that if you ask me in a single word, what we should do next, I will say design an important communications, public relations effort. We should be able not to do more science, which we already have, wonderful science, state-of-the-art science, but we need to be able to communicate in a more effective manner. Thank you very much to everyone.
Thank you, Victor. Leo or anyone else, any very last comments?
I would like to make just 2 comments. I think that one lesson we must keep clear in mind, is that there is no a science for the first world and a science for the second world. And if we are too much worried about the feasibility of an ambitious program, the second world will become third world, the third world will become fourth world. And the second problem is that if one indulges to national tendencies, we lose the only way for changing the situation of science in the world. namely the International South Operation. So my impression is that if we look for solutions which are accessible to certain countries, well, certainly Mexico will survive, but the rest of the Caribbean will not progress. And this, in my view, is something which we must be kept into account and correspond to the idea of collaborating with Africa, collaborating with Uzbekistan, collaborating with Iran, collaborating with Montenegro and all others, because in my view, only a big program for the South can make these things feasible. Otherwise, in 10 years, I will not be here, but you will be saying exactly the same thing.
Well said, Leo.
Well said. Well, folks, we've had a great 3 days. And I think the organizers will probably issue some kind of summary, or we'll do some proceedings, I guess. But I want to thank you all for coming. Thank you, everyone.
Thank you.
Bye from Italy.
All right. Thank you, Jose. It's really late there, I'm sure.
Yeah.
Bye.
Cheers. Cheers.
So organizers, we want to meet probably later, right? Some days later?
Yes, as usual.
Okay. I mean, not right now, right?
Yeah, that's maybe next week or whenever. I don't know.
Okay.
What is Leo saying? Leo, what are you saying?
In Christmas time.
Oh, Christmas is the week after next. You're right, Carlos.
Christmas Day. Okay.
Okay. We'll figure out for WhatsApp.
Hey.
Yeah. Okay. Bye, everyone.
Bye, everyone.
Congratulations.
Thank you for everything.
I think it's been a very good meeting.
Thank you.
Yeah, it was extraordinary, actually.
Extraordinary, exactly. Hey.
All righty.